course, part of the overall drive of this research is the idea that singularities are useful in optics. We've known since the 1970s that so-called singularities in wave fields possess interesting and useful properties. Singularities in the phase of scalar wave fields, which are called optical vortices, possess orbital angular momentum and are used in imaging, communications, and trapping. Singularities in vector fields, which are usually called polarization singularities, provide even more flexibility for applications. And so that raised a question for me: can we make use of even more general singularities in which space, polarization, and time are intertwined? Let me give you a brief introduction to singular optics, just for those who might not be familiar. We talk about singularities of phase appearing in any system which can be modeled by a wave equation. The question, and a great example of this goes all the way back to the 1920s, when researchers Proudman and Dudson mapped out the tidal elevations in the North Sea outside of the United Kingdom and noticed the presence of what they called amphidromic points, where the tidal amplitude is zero. So these isolated points, and the lines of high tide seem to, as a function of time, circulate around those points where the tides don't change at all and act very much, so there's a circulation there, which we would later associate with the term vortex. Now in optics, we didn't recognize these sort of structures for a long time, because when we think of monochromatic waves, we usually think of planar wavefronts. We picture a plane wave, for instance, propagating in a particular direction, and we label all the up parts of the waves as the wavefronts, and those form parallel planes in space. And in fact, researchers use plane waves in most of our approximations and most of our studies, because plane waves are a really good approximation for very complicated waves. And situations where things are not planar are often considered sort of isolated or kind of unusual cases. And a great example is in Sommerfeld's optics book, which was published in English in 1964. He basically stuck together 6 waves propagating with different frequencies in different directions. And he said that if you look at most places in this wave, there are regions several wavelengths in extent which have the character of a plane wave. And then he noted that only the 0 points seem to be the exceptions, where you end up with essentially new wavefronts manifesting at a point where the intensity of light is 0. And he argued that because the amplitude vanishes there, they don't produce any stronger effect than points of varying intensity. And this view changed in the 1970s when Nye and Berry pointed out that those points where the amplitude vanishes and the phase is undefined or singular almost always represent a line in 3-dimensional space. And around that line, the phase has a circulating or a helical structure, which is called nowadays an optical vortex. And this gave rise to the subfield that we now call singular optics. And if you think of optical vortices, there are 2 most common ways that they can manifest. You can have a 0 line, which is perpendicular to the direction of propagation. And that's the case that Sommerfeld and Berry saw in those 2 previous slides, where you have an extra wavefront appear between 2 other parallel plane wavefronts. Or you can have what we call a screw dislocation, where the 0 line is along the direction of travel and the wavefronts ramp upwards, basically like a parking deck in a parking garage. Now, we don't usually look at these things in 3-dimensional space. We measure them in a 2-dimensional transverse plane. And so we tend to plot the phase using colors. And the Laguerre-Gauss beams of order N and M are sort of the typical vortex beams that people study. They have an mth order vortex core that persists on propagation. And you can see that the phase increases continuously. If for an M equals 1 beam, it increases continuously by 2 pi around the center. For an m=2 beam, it increases by 4 pi around the center. We can have a negative order. So for -3, the phase decreases by 6 pi as we go around the center. And for the Laguerre-Gauss beams, you can trace all of this to the azimuthal phase term of the beam, this e to the im phi. And m always has to be an integer value. If we're working with a monochromatic field, the phase has to increase or decrease by an integer multiple of 2 pi. That multiple is called the topological charge of the vortex. There's a nice mathematical equation for it based on the phase, but usually we would come up with other ways of calculating the topological charge instead of trying to do a complicated integral. And it's generally a conserved quantity in wave fields and therefore of interest for things like optical communications. And there's a variety of applications, and a lot of people have since then turned, since optical vortices have proven so useful for research, and overall beams carrying vortices are kind of a subset of this whole idea of structured light, of making beams with non-trivial structures. And you can also turn and look at polarization. And we know that for a monochromatic wave, the general polarization state of a field at a point is elliptical. And that elliptical polarization has a handedness to it. You can say whether it's circulating essentially left-handed or right-handed, or clockwise or counterclockwise. It has an orientation, which I use psi here to define, and an ellipticity. It can be more elliptical or less elliptical. And there are two types of singularities in polarization that we talk about that have some special significance. If the field is circularly polarized, so our ellipse is a pure circle, then the orientation angle psi is undefined, because of course you can rotate a circle and it looks the same. And those points became known as C points. There are also locations or regions where the light is linearly polarized. And those regions, the handedness or the direction of circulation is undefined, because the electric field vector is just swinging back and forth. And those are referred to as L lines. They manifest as lines in a transverse plane. Now, the C points are usually the most interesting ones to study, and they come in certain classes. Just like optical vortices, the typical singularities you see are vortices of charge +1 and -1. Typically, in a field with a non-uniform polarization structure, you find that C points come in certain special classes. There's what's called the lemon, the star, and the monstar. We don't talk about the monstar very much because it's sort of a hybrid singularity that evolves when you start to have an annihilation event or a creation event between a lemon and a star. But in these pictures, you can see the general structure, that the lines here represent the orientation of the major axis of the polarization ellipse, and then the ellipses are shown there for comparison. And these polarization singularities turn out to be very interesting as well. And there's all sorts of interesting things you can study in beams that have non-uniform polarization. To give one example, I see that Miguel Alonso is also talking at this meeting. And in 2010, Beckley, Brown, and Alonso showed that it's possible to create beams that have every possible polarization state in their cross-section, which are called Poincare beams. Now, the state of polarization, we often introduce, and we describe the state of polarization of light using the so-called Poincare sphere. And S1, S2, and S3, the axes here are the Stokes parameters we use to describe the state of polarization. And you can show with an appropriate construction that you get a field where if you look at any transverse plane, you have basically every state of polarization manifesting. In this case, the parameters were chosen to have one of these C points, points of circular polarization in the middle. And in fact, you can see that this singularity is a star, that it's got that sort of three-pronged behavior to it. And incidentally, it also turns out when you look at these non-uniformly polarized beams with singularities in it, you find that they actually do perform better in atmospheric turbulence. Back in 2009 with my student Yalong Gu and my colleague Olga Korokova, we sort of looked at these non-uniformly polarized beams in atmospheric turbulence and did simulations to look at the scintillation or intensity fluctuations of these beams, and found that the non-uniformly polarized beam had a much significantly lower scintillation. And then a year later, I realized, talking to Dr. Alonso, that, oh, what we were working with were Poincare beams that we didn't even know were Poincare beams. We just sort of randomly decided that this looked like a very interesting class of beams. So that background is really to give you an idea that singularities are interesting, they can be useful for applications, and that more complicated singularities give you more degrees of freedom to manipulate potentially for other applications. And this raised the question for me, are there benefits to generalizing further? Can we make fields with even more complicated singularities, and what will they look like and how will they behave? And for this, I turned to a 2003 paper by Kessler and Freund. And Kessler and Freund started looking at singularities of fields where you have two frequencies instead of one. So the electric field vector consists of one polarization state at one frequency, another polarization state at another frequency. And when you combine vector fields in this way with two frequencies, you get what are called Lissajous figures, which are these complicated, repeating but not simple periodic structures. And of course, I dragged this picture off the internet because if you've ever played with an oscilloscope, one of the things you might have done is created Lissajous patterns by combining multiple frequencies in an oscilloscope trace. And so the idea here again is that the electric field vector, if you have two frequencies present, the electric field vector can also trace out a Lissajous pattern. And now that also raises the question, how do you define a singularity in a Lissajous field? So it's possible, just like we can make a non-uniformly polarized field, we can make a field where, for instance, this function, whoops, and I have a grandfather clock in the background, so it'll go off every 15 minutes. It's a good warning that when my talk is running long. The electric field vector E and the electric field vector F here can be different so that the polarization pattern is different at different points in the transverse plane. So if you were looking at, for instance, a monochromatic field, again, we could have a non-uniform field. But you can get also different Lissajous patterns at different points in the transverse plane. And how do we define a singularity? Well, following Freund, a singularity is a point where the sum of the Stokes parameters of the two frequencies has some sort of singularity. And in particular, in analogy with the C points for monochromatic fields, we say there's a singularity if both S1 Stokes parameter and S2 Stokes parameter are simultaneously equal to 0. And following Freund in this, these are some simulations of one of those situations. This is the example from Freund's original paper. You have the Lissajous figures at different points in space. And if you just plot the equivalent of the major axis of these figures, you get a pattern like this. And in fact, Freund and Kessler found fields that had multiple Lissajous singularities together. There was never an isolated singularity. They always came in groups of 4. And this brings me, that was sort of a long introduction to what I've been looking at recently, was looking at the question of, is it possible to make a beam where there's a single Lissajous singularity in its center? Because when we use vortex beams, like Laguerre-Gauss beams, or we use a Poincare beam, we've always got a single singularity in that beam. And that singularity is what we use to carry information or for imaging or for other applications. So the goal was to say, can we do the same thing and design a class of Lissajous type beams? So in analogy, just like Freund did, we introduce a bichromatic field. Now, one generalization that I added is a carrier frequency, and I will say more about this carrier frequency in a moment. But then the goal was, how do we put a single Lissajous singularity in the center of a beam? And we really drew an analogy to polarization singularities. If you make a polarization singularity in a field, a polarization singularity invariably involves one orthogonal polarization state that has an optical vortex of some sort at its core, and then another polarization state that is non-zero. So for a Lissajous singularity local form, we have our two fields, which are at two different frequencies, and each of them basically has its own polarization singularity at the core. And we can be quite general. We can say these states of polarization themselves can be any orthogonal state we want, or heck, we don't even have to have them be orthogonal states. And what you find, you can plot that Stokes parameter field, and you find, in fact, locally that the Stokes field does have
Professor, your mic is mute now. Whatever.
Can you hear me now? Testing?
Yes.
You can hear me?
Yes. Yeah, we can hear you now.
Okay, I don't know what happened there. Let me try again. And whoops, okay, hopefully we're back and you can hear me.
No, Professor, we can hear you now.
All right. It's a modern technological era. You never know when things are going to be weird. But okay, so the Lissajous singularities we have here, you can see this is just the color pattern showing the Stokes parameters, showing a clear singularity in the middle. You can also plot the Lissajous patterns. And for the simple case of circular polarization states, you get this traditional trefoil pattern in the middle. But you can use different orthogonal states and have other unusual Lissajous figures that are also singularities, but are different and not symmetric. So once we have this local form, the next question is, what exactly do the singularities look like, or how do we classify these singularities? And it turns out that we found two broad classes of fields where the Lissajous singularities, where there's a single Lissajous singularity in the center of the beam. And for lack of better description, we called one class type A and the second class type B. For type A, we have the two frequency components have equal and opposite vortex order. So if M1 is, +5, M2 is -5. And the polarization states can be any pair of orthogonal polarizations, except they can't be orthogonal linear polarizations. Things break down if they're linear. And sure enough, you can get a very well-defined set of Lissajous singularities in the center of your beam of different orders. Now, the type B case is the case where you only have one singularity in the center. So either frequency component A has no singularity, so we just set gamma 1 equal to 0, or frequency component B, we set gamma equal to 0, so that there's only one singularity in one frequency component. And you can again get Lissajous singularities here, except the states of polarization then have to be orthogonally circularly polarized. Now, We can also take a brief look and say what happens if we have what I call a non-pure Lissajous field. We can look at what happens if we don't follow those rules I just set up. Well, if you don't satisfy those rules, then you end up with the situations you're hoping to avoid. So for instance, in the first case, in the figures A and B here, we, let's see if I can remember exactly what we did there. We chose, well, let me just say without remembering the specific parameters, one situation that arises is you end up with non-generic Lissajous singularities. You end up with basically a bunch of zero lines or singular lines in your cross-section instead of a singular point in the center. And the other thing that can happen for non-pure fields is you can again get this situation that Kessler and Freund found where you get multiple singularities in the beam center. And really what we're looking at these days, part of what we want to understand and why this work is partly still preliminary is really understand under what situations and why you have one case where you have a pure singularity in the center and other cases where you don't. Now, everything that I've described so far, there are two aspects to it that are a simplification. One is we're looking at the local form of the field. So imagine we're zoomed in some finite region of the field. And so that doesn't necessarily tell you whether there are going to be other singularities in your cross section, because there could be potentially ones further out. The other simplification is we looked at everything in the source plane without looking at propagation. And beams like this are only going to be useful if they maintain that singularity in the center of the beam when you propagate them over significant distances. But the transition from local form to beams is pretty straightforward because those local forms that I chose were basically the local forms of Laguerre-Gauss beams. So we go from having a vector A and a vector B at the two frequencies to having two different fields that consist of Laguerre-Gauss modes, and a Laguerre-Gauss mode of order M, and then combined with a pure Gaussian mode, and those Laguerre-Gauss modes are of the usual type. And then we can just look at what happens to them as they propagate in free space, for instance. And I'll just show you some brief examples that, for one thing, the other thing that I didn't have to specify in the source plane is the frequencies, because in the source plane, the actual frequencies don't matter because the frequencies have no effect on the overall shape of the Lissajous figure or the location of the singularity. The frequencies only come into play when you propagate the field, because then the different frequency components can propagate differently. So we're very curious about whether these singularities, as I said, will stay isolated on propagation over significant distances. And for that case, we chose the most extreme scenario. And the most extreme scenario is to go back to what Kessler and Freund originally did. Kessler and Freund assumed second harmonic generation of the field. So you have a fundamental frequency and then the double frequency. And that's about as extreme of a difference in frequency as you can get to have in a Lissajous type beam. So we just propagated a beam of that sort at optical frequencies over a kilometer. And sure enough, if you look at both the Lissajous patterns and the phase diagram that shows the position of the singularity, we did find that these Lissajous singularities they stay, at least for some significant propagation distance, and that propagation distance is going to depend on the beam parameters. You can have these beams propagate over significant distances, which means that you could potentially use them just like we use polarization singularity beams or vortex beams for different applications. Now, the one thing that does change is the shape, the very specific structure of the Lissajous pattern changes. So you maintain a singularity on axis on propagation, but for instance, that trefoil pattern may become a fatter trefoil as you propagate it, or it may start instead as sort of a cusped triangle and evolve into a trefoil, depending on the choice of the widths of the different frequency components of the beam as you at the source plane. Now, one last thing I'll just mention, especially because we submitted this paper earlier this year as a theoretical paper, and we didn't specify a method for generating, for instance, this carrier frequency that we're introducing in the field. And there were two objections to the use of a carrier frequency in the paper. One objection was that we didn't explain how you might have this carrier frequency field. And the other objection was that with a carrier frequency, it's no longer a Lissajous field. Now, it turns out that that second objection we originally addressed in the paper, and I think the referee missed that section, because if we do include a carrier frequency in our Lissajous beams, that changes the interpretation of our Lissajous figure. Then our Lissajous figure is no longer showing you the instantaneous trace of the electric field vector. It's showing you the average, the short time average of the major axis of the polarization ellipse. So you can imagine if you have a fast carrier frequency and slow signal frequencies, you have a polarization ellipse that's going to evolve in time. And that major axis of that polarization ellipse is what's going to trace out a Lissajous pattern. And for the generation question, several possibilities come to mind, though as a theorist, I don't want to be, I'm not super confident about it because there are a lot of technical details. But one possibility is just filtering a frequency comb of a mode locked laser. We have a bunch of equispaced frequencies. If we can filter out just two or three of those frequency components, we can use those and separate them and recombine them with different polarizations. We can make a Lissajous beam. Or we could try using an acousto-optic modulator where we have a directly transmitted beam and the first order diffracted beam is going to have a different frequency, a higher frequency than the transmitted beam. And then each of those can have a polarization imparted and they can be recombined. And the clock in my home is warning me that I'm almost done, but fortunately I have reached the end of my talk. And just want to say what I've been talking about is just thinking about ways of generalizing the structured light beams that we've looked at so far. And so I looked at this idea of Lissajous singularities and looked at a class of beams that possess a single Lissajous singularity in their core. They maintain that singularity over significant propagation distances. One of the advantages and disadvantages of such beams is there are now a ridiculous number of degrees of freedom, which is why I had to spend so much time working on type A and type B type beams. And the next goal is to look at what we can do with these beams. What happens if we use them in applications of free space optical communications? Are there any advantages or not? And if I were to summarize the entire talk in a sentence, I would say there are more types of singularities out there than have been previously considered. There's more than just vortices and polarization singularities. And so I'm interested in exploring some more of those. And I'll stop there. Thank you very much. Oh, you're muted.
Thank you, Professor Gubar. So such a very nice talk. So now we can take a few questions from the audience. So I'll read the questions. The first question was that how to measure the polarization coverage of a beam.
Yes. Very good question. I mean, I think in the end, it's going to come down to measuring Stokes parameters of the field again. And the way I envision using a carrier frequency is that you have basically a carrier frequency in the optical regime, and then you probably have this first and second signal frequencies are orders of magnitude slower. So what you're going to really be measuring is like I said, you're going to be measuring the polarization ellipse as it evolves in time at a much slower rate. And so in that case, provided you can measure the Stokes parameters in the cross-section of a field relatively quickly, and I believe there's a number of techniques to do that, though, again, I won't say too much because as a theorist, I'll get myself in trouble, but I believe there are methods for measuring those Stokes parameters in that way. But it's also something I'd be happy to talk with other people about if anybody has any ideas.
So what he mean that if you consider the C point singularity that you measured, that you presented. So in that particular beam, the total polarization coverage will be constrained with your beam size, right? Or your aperture you are taking. So that how you measure.
Okay, so the question of, for instance, like the Poincaré beams, where you have a finite beam, so you're only going to get a certain amount of coverage. Yeah, that's an interesting question, and that's something else that we need to explore, because you can, depending on the choice of parameters of the beam, again, I believe you can expand that polarization pattern or compress it within the available beam space. So yeah, for a finite size beam, depending on how you choose things, you could have the Lissajous figure, the pattern crushed in or stretched out more. And I don't have a good feel for how that depends on the parameters or how to estimate it yet. That's something else I need to think about more.
Okay. One more question is there. So in the making of this Lissajous figure, you are telling you are taking electric field as one Gaussian plus vortex in omega and Gaussian plus vortex in 2 omega, right? So what if happen if I use a different L value or charge for both of the beam, E1 and E2?
Yes, I believe that if I remember correctly, those cases, I believe, end up giving you some of these non-pure type states. So if you have two vortex states that, if you have these two vortices with different charges in the beam, then you end up getting multiple singularities again. And it's actually quite interesting. Part of the reason I make sure to mention these, what I call non-pure Lissajous fields, is because I still think they're very interesting. They weren't what I was originally looking for, but they probably have their own intriguing properties that I also do not understand very well yet. So yeah, but that is definitely something you can do. And I'm assuming that if you choose different values of M1 and M2, that's going to influence the number and location of additional Lissajous singularities you're going to see popping up in your cross-section. I don't have a really good feeling for the relationship yet.
Actually, why I asked this question, because unknowingly, about 1 year ago, we made this thing in our lab, actually.
Oh, okay. Well, then we're going to have to talk about this some more.
Yeah, that's why. And what about the measuring of such beam, Lissajous figure in experimental technique? I mean, if I have a beam, I generated a beam, so how I can measure this Lissajous figure? I mean, this polarization, this point in our beam.
Right.
Can I do?
Sorry, could you say that again?
If I have a beam with this Lissajous figure, I mean, if I mix a beam with omega and 2 omega with a different the current condition. So how can I measure that particular polarizations in the beam experimentally?
Yeah.
Do you have any?
Ideally, you probably would end up measuring the Stokes parameters for the two frequency components separately. And then you would be able to reconstruct the state of polarization from those Stokes parameters. There would be, and if those Stokes parameters would leave out, there would be an arbitrary extra phase between the components that those Stokes parameters could not give you. But that arbitrary extra phase between them is going to amount to just changing your position, I believe, on the Lissajous figure. So I think it comes down to the simplest thing is to just say measure the Stokes parameters themselves and see what happens. Again, if you're designing an experiment where you're using a carrier wave and relatively slow signal frequencies, then there's also the possibility of trying to measure the trajectory of that major axis in real time somehow and seeing whether you could actually see the Lissajous pattern evolve, which I have no idea if that would be at all of any use, but it would be fun to see.
Okay. Anyway, we have one more question. The Poincare beams are the superposition of two fields and their interference. Now, if we have two different wavelengths, then how to get the interference?
Yes. So the catch is that you have to keep the the singularities are, so we have to keep two frequencies together, and they have the two fields have to remain coherent over at least a finite measurable period of time. So the coherence time has to be long enough that you actually can see the Lissajous state. And so that's where, so as far as so while this is where I talked about the possibilities of how to generate it, is you would need some sort of coherent type source that would give you a relatively long phase lock between those two frequency components, which it seems like the safest bet would be part of the frequency comb of a mode-locked laser. One thing I keep fretting over is an acousto-optic modulator in principle would be a great way to do this, because you'd have a fundamental frequency of the transmitted beam and a diffracted beam with a different frequency. But I have no intuition about the coherence times of those frequency components out of the AOM. So this is partly where I need to talk to experimentalists more, is to say, well, this is the theory part of it. Can you help me figure out a reasonable way to realize this experimentally? Or tell me that it's crazy and that I just should stop thinking about it.
Yeah. So, some sir have any? Okay, he is in attendees. I think we can discuss this after this time our email. I feel.
Yes.
And I have one last doubt also. Last question also. So then we can wind up probably this talk. So can you comment on the coherence length after the generation of this Lissajous beam? After this combining this omega and 2 omega frequency, so then it was like a combined two different wavelengths together combined. So how we will talk about the coherence of that one.
Oh yeah, this is actually kind of interesting and tricky, because if you think about the coherence length or the coherence time in traditional coherence theory is all just about a long time average. So the coherence time of the field is going to be pretty short, related to the inverse of the frequency difference between the two signals. But we're not interested in averaging over that signal. We're interested in the actual trace of the Lissajous pattern. So the question instead becomes, what is the coherence time between those two components of the field? And that's the information that I've had a hard time trying to track down. Like if I use an AOM or a mode locked laser, how long can I assume those components stay in phase so that I can treat it as a coherent Lissajous thing? So that again is something that I'm not entirely sure the answer of. I've been thinking about it and fretting over it and don't have a great answer, but I've been thinking about it.
I have the comment that you asked before. So if you use a femtosecond laser, so in the pulse width, it will be like you can consider that beam as a coherent. So it will be like in a few micrometer order. So while doing this kind of experiment, you need to specially overlap these two pulses. So if you take a omega and second harmonic generation of the beam, and if you combine that two, so in the overlapping place, this two beam, you can consider the phase will be like constant throughout the propagation direction. So while detecting that one, you can, I think, you can realize that coherence within this two beam.
Excellent. Good to know.
Okay, we can discuss more about through mail or our future discussion. So let's thank Professor Guber again, and we can move to the next talk. So now, okay, bye. Now we have a student talk by Miss Shalija Sharma. So she's currently working at NICER Bhubaneswar under Professor Ritik Das. She will be delivering her talk on rainbow trapping via excitation of optical modes in one-dimensional chirped photonic crystals. So over to you, Shalija.
Yes, hello, I'm audible.
Yeah, you are audible, and your screen is visible. Can you go to a slideshow mode? Yeah, your full screen is now visible. Yeah, your laser point also now visible. Can you change your slide one time? Yes, your slide also moving. So you can yeah, it's working. Okay. You can continue.
Okay. Thank you, Suved, for the introduction. And okay. So good morning, all of you. So I'm Shalja Sharma from NICER Bhubaneswar, and I am working with Dr. Ritik Das. And the title of my today's topic is Rainbow Trapping by Excitation of Optical TAM Modes in One-Dimensional Chirped Photonic Crystals. So this is the outline of my talk. First, I will discuss about the motivation toward this work and the introduction of the chirped photonic crystal and the excitation of multiple resonant modes in such structures. And then I will discuss the results. And finally, I will conclude my talk. So the first question arises, what is this rainbow trapping? So phenomena of slowing down or stopping a wide range of frequency in one-dimensional or two-dimensional stratified periodic medium, that phenomena is known as rainbow trapping. So this slow light has attracted much attention because of a broad range of application, including in optical delay lines, optical buffers, processors, optical filters, and sorters, etc. So in order to address the need of various applications, it is highly important to design some novel structures or to explore some new mechanisms which can significantly slow down or even stop light for a broad range of frequencies. So the phenomena of this rainbow trapping was first time realized experimentally in 2011. And the configurations which are commonly required for trapping light are mostly all metallic and hybrid metallo-dielectric configurations. Although these configurations allow very strong confinement to the light, and also there is significant reduction in the velocity, which is less than or equal to 0.1 times of C. But as you know, these plasmonic active metals exhibit very high ohmic losses, and as a result, the lifetime for the trap mode is less than 1 picosecond. And also this all dielectric geometries was also proposed by various groups, which to trap light in the visible or in the infrared band, which offer appreciably low losses, but the lifetime for the trapped mode is approximately 0.2 to 0.3 picoseconds. And the conventional one-dimensional periodic photonic crystals also work as a slow light device, but they can be applicable only for a narrow range of frequencies. So to overcome this limitation of narrow range of frequencies, what we need to do, we just chop the conventional one-dimensional photonic crystal. So this chirping can be introduced either by changing the periodicity of the unit cell or by changing the duty cycle of each layer. Okay, so in this article, so what they did, they have changed the periodicity of the each unit cell from 110 nanometer to 150 nanometer by changing the thickness of layer 1 from 80 nanometer to 120 nanometer. So we first analyze the dispersion relation for the one-dimensional photonic crystal, and which is given by this Cronin-Penny relation, which is cos k lambda equals to cos of k1 w1 and cos of k2 w2 minus half of n1 by n2 plus n2 by n1 sine of k1 w1 and sine of k2 w2, where this k1 and k2, these are the wave number in layer 1 and layer 2, and w1 and w2 are the corresponding thickness of layer 1 and layer 2, and this capital K is the clock wave vector. So if we see the variation of or the dispersion relation for this one-dimensional photonic crystal with W1 equals to 80 nanometer, which is on the extreme left of the structure, and W equals to 120 nanometer, which is on the extreme right of the structure, then we can see that there is a flat region which depicts the photonic band gap for this photonic crystal with W1 equals to 80 nanometers and W1 equals to 120 nanometers. So, and for the W, for the thickness which is lying between 80 nanometer to 120 nanometer, that also exhibit the similar dispersion curves, and but the wavelength at the upper edge is monotonically increasing as a function of W. Means with W in between 80 to 120 nanometers, this dispersion curve lies between basically A and B points. Okay. So since this group velocity, which is given by d omega upon dk, this group velocity is usually very small at the band gap edges. Okay, so if we plot the see the variation of this C by Vz as a function of this W1, then here we can see that for this wavelength, suppose this 400 wavelength, this Vg reduces near W equals to 87 nanometers. So this implies that for a given thickness, a particular wavelength is engaged, and light with that wavelength has considerably reduced group velocity in the propagation direction. So means when we are considering these chirp structures, then the light with different wavelengths is localized at different spatial positions, and this allows us to trap light for a broad range of frequencies, and this broad range of frequencies is termed as the trap rainbow. And and the next challenge is to trap the broadband electromagnetic radiation with lifetime greater than 1 picosecond. So this can be achieved in all dielectric photonic crystals through the excitation of surface states. So the states which exist at the interface between a plasmoactive metal and a one-dimensional photonic crystals, those states are known as optical TAM states. And these states exhibit very interesting features, like they are strongly confined at the metal dielectric interface, and secondly, they exhibit the parabolic dispersion curves, and they are excited by a free space coupling for both TE and TM polarizations. So we have considered a chopped geometry which consists of TiO2 and SiO2 multi-layers, and here we have changed the duty cycle of each layer by keeping the periodicity of the unit cell fixed. So the thickness of the layer 1 in the Sth unit cell is given as d1 plus S delta, where this delta is the chirp length that we have introduced in each layer, and it is 10 nanometers. So to excite the surface states in this chirp photonic crystal, we have placed a thin metal layer of approximately 30 nanometer adjacent to the TiO2 layer, and simulated the reflection spectrum for the structure using the COMSOL multiphasic. And here what we will see, the reflection spectrum for the chirp photonic crystal with metal layer, this is characterized by a sharp drop in the reflectivity within the reflection photonic band gap of the chirp photonic crystal, which is represented by this blue curve. So the existence of these multiple TAM states can also be explained by using this dispersion curve for the various photonic crystals with different D1 and D2 values, such that the periodicity of each photonic crystal remains fixed. So now what happens, these chirp photonic crystals can be decomposed into multiple one-dimensional photonic crystals with different D1s, such that D1 plus D2 remains equal to 400 nanometers, which is the periodicity of the chirp photonic crystal. Okay, so now only those one-dimensional photonic crystals support optical TAM modes for which this condition is satisfied, where this phi m and phi pc are the phases of the light reflected from metal and that of semi-infinite photonic crystal. So in general, for the reflection phase for the metal in visible and infrared range is negative. So this phi of photonic crystals should be positive in order for the existence of the optical TAM mode. So only those D1, D2 combinations support optical TAM modes for which this phase of the photonic crystal is positive. So these sharp resonances within the photonic band gap of the chirp photonic crystal are the signature of the optical TAM modes, and their mode field decays away from the metal dielectric interface. So if we see the variation of the mode field intensity of the different resonant mode, then here we can see that the field localization at different resonant frequencies are spatially separated, and the mode field at the lowest resonant frequency, that is 172 terahertz, is localized near the metal dielectric interface, and which resembles to the conventional optical TAM plasmons. And the modes at a higher resonant frequencies are localized away from the metal dielectric interface. So this electromagnetic field localization implies a drop in group velocity of the optical TAM modes. So to ascertain this group velocity of the optical TAM modes, we have performed time domain simulations and FDTD simulations, where this time on the y-axis, this represents the arrival time of the pulse peak at the respective location within the chirp photonic crystal. And here we have made a comparison between bare chirp photonic crystal and the chirp photonic crystal with metal layer for two different resonant frequencies. So in case of a bare chirp photonic crystal, so here we can see that these bare chirp photonic crystals exhibit short-lived localizations, approximately for a time period of 0.1 to 0.2 picoseconds. But similarly, at similar resonant frequency in case of chirp photonic crystal exhibit a prolonged lifetime, prolonged localization up to 3 picoseconds. So this time domain simulation directly allows us to measure the group velocity of these resonant optical TAM modes by just noting the arrival time of the pulse peak at a respective location in the chirp photonic crystal. So here we have also measured the group velocity for resonant mode at this frequency as along the propagation direction. So here we can see that this group velocity for this optical resonant mode minimizes near z equals to 10.2 micrometer, and it minimizes up to 0.22 times of c. So this Z equals to 10.2 micrometer. This corresponds to a unit cell where D1 is 140 nanometer and D2 is 260 nanometers. Okay, and the variation of this group velocity, minimum group velocity for different optical resonant mode is shown by these green diamonds, and it reduces up to 0.16 times of C. And also these time domain simulations also allows us to monitor the lifetime of the trap mode by just noting the drop in pulse peak intensity to 1 upon e square of its maximum value. So here we can see that the optical TAM modes at this 243 terahertz has a trap lifetime around 2.48 picosecond, and this trap lifetime maximizes up to 2.8 picosecond at a resonant frequency at 200 terahertz. So from here we conclude that the optical TAM modes localized near gold layer, they exhibit a longer lifetime as compared to the optical TAM modes which are localized away from the gold dielectric interface. So we have also studied the dispersion characteristics of the optical TAM modes.
Shalija,
yes.
Can you wind up your talk in next 3 minutes? Then we can take one of
I have only one slide left.
Okay.
Okay. So we have also studied the dispersion characteristic of these optical TAM modes for both TE and TM polarization. So here this K parallel is the in-plane component of the wave vector. So from here we can see that these exhibit parabolic dispersion curves, and also their polarization degeneration lifted for higher values of in-plane K vector. And this behavior is exactly similar to the conventional optical TAM modes. And also the lower energy optical TAM modes exhibit smaller splitting between this TE and TM polarization at higher values of K parallel. So we can summarize this in our proposed design. This leads to the excitation of multiple optical TAM modes at metal dielectric interface, and all the optical TAM modes are spatially localized, and the field localization of optical TAM modes results in reduced group velocity approximately up to 0.17 times of C, and the group velocity lowers for a large frequency bandwidth at infrared frequencies. And the optical TAM mode, this provides a favorable platform for lossless trapping of light with lifetime up to 3 picoseconds. And I would like to acknowledge my supervisor, Dr. Ritik Das, and my collaborator and my lab mate, Mr. Abhishek Mandal. And also I would like to acknowledge the funding agencies, DAE and SERB. Thank you.
Thank you, Shalija, for such a wonderful talk. So now we can take some questions from audience. I can read you that questions. So the first question is, how do you create periodicity in crystals on such a short scale of submicron level?
Experimentally or theoretically?
Experimentally.
Yes, there are several deposition techniques like CVD. Yeah, there are several experimental techniques. This can be easily fabricated, this structure.
Okay, so the next question is, can we utilize this effect on trapping optical modes in solar cells to increase the efficiency of solar cells?
Can you please repeat the question?
Can we utilize this effect of trapping optical modes in solar cell to increase the efficiency of solar cells?
Yeah, maybe we can use, but I'm not sure. I have to look at this part. Maybe we can use in solar cell also, but I'm not sure right now.
Okay, then you can communicate with the, Sandeep, you can communicate with the speaker later. So we can thank our speaker once again. Thank you, Shalija, for the talk. So now we have a student talk by Mr. Deepaprada Paul. He is working at ISER Pune under Professor Pawan Kumar. So today he will be delivering his talk on simultaneous detection of orbital and spin angular momentum of light through scattering from a single silver nanowire. So over to you, Debabrata.
Yeah. Am I audible?
Yeah, you are audible and your screen is in full screen mode. And can you change your slide?
Yeah, I think. Yeah.
Yeah, your slide also changing. Okay, over to you.
Yeah. Good morning, everyone. My name is Debabrata Paul. Thank you, Suvit, for the introduction. The talk that I'm going to present today is about simultaneous detection of orbital and spin angular momentum of light through scattering from a single silver nanowire. To begin with, let us talk slightly about angular momentum of light, which is very well known in the field. You can impart angular momentum in a light beam either through its spin angular momentum, which is generated when you place a quarter wave plate in the path of a linearly polarized beam with its axis aligned according to the incident linear polarization angle. You can get a circularly polarized beam, which has a spin angular momentum, or you can have orbital angular momentum. It is generated when you modulate the phase of the incident beam, and it can be done by introducing something called spiral phase split to a plane wavefront Gaussian beam, and you can have something such as helical wavefront, and that is a typical signature of the Lagrange Gaussian beams. Right. But what these two have in common is that both of this spin and orbital angular momentum correspond to a transverse energy flow. For example, if you have a circularly polarized Gaussian beam, you will have a transverse energy flow corresponding to the spin flow density of the beam, which can be either counterclockwise or clockwise depending on the helicity of the circular polarization, and it arises due to formation of small circular polarization loop in the beam intensity, and these all small loops overall add up to give you overall spin flow density in the beam. If the adjacent intensity in the point of the beam is same, they will give you 0, as you can see in the middle. But when the difference is slightly higher, you can have a overall non-zero spin flow density, and it depends on the gradient of the intensity of the beam. On the other hand, if you have a Lagrange Gaussian beam, it has a helical wavefront and a phase going from 0 to 2π for the LG10 beam, and in this case you will have transverse energy flow corresponding to its orbital flow density. So this can also be counterclockwise or clockwise depending on the sign of this topological charge, or in other words, when the phase goes to 0 to 2π counterclockwise or clockwise, where the flow direction will change. What this flow can do now is, when you have both orbital flow and spin flow density in the beam, as we all know from the previous few words, that the spin flow density on the gradient of the intensity distribution, and when you have circularly polarized Lagrange Gaussian beam, this orbital flow and spin flow can add together to give you a different total energy flow with respect to the initial orbital or spin constituent. So as we can see here, that for left circularly polarized Lagrange Gaussian beam, the spin flow at the inner part of the beam is clockwise, which cancels the counterclockwise orbital flow density, whereas the outer circle spin flow density, which is counterclockwise, adds up with the orbital flow density, gives the overall total flow density, total transverse energy flow, which is basically has the same handedness of the orbital flow, but in this case the magnitude has stayed roughly the same. Whereas what we see for the right circularly polarized right circularly polarized Lagrange Gaussian beam is that in the inner part, the counterclockwise spin flow density gets added up with the orbital flow density, whereas in the outer circle, the clockwise spin flow density cancels the orbital flow density. So what you get at the end of the day is that since this is at the inner circle, the intensity is much more of the total transverse energy flow, and you get a much higher transverse energy flow in the same, having the same handedness as that of the orbital flow density. So to detect these two constituent from the total, because when you interact with any nanostructure or anything, what it feels is the total flow, not the orbital or spin flow constituent. But to detect either of these two constituent, we have to first know that how the total flow looks like. So what it imparts on a particular object that it has is that it imparts a momentum. It can be, and for orbital angular momentum, we will have, if there is a particular object, it will rotate in a particular orbit. This opens up a new avenue of optical tweezing. And for spin angular momentum case also, you can have something spinning in the orbit, spinning in the field. And of course, the relative effect can be studied, which one is stronger and which one is not stronger in this case. And when you have both of this together, you will have something called as spin to orbit conversion. You can have something called as spin to orbit conversion, which is a very special case of spin orbit interaction, where for one case, if there is a particle like this trapped, what you can have is that in one case the particle might rotate faster and relative to the other case. So there the spin angular momentum value gets added to the orbital angular momentum value and giving you higher transverse energy flow, which is what I showed. So this opens up this mechanical momentum approach of rotating particle, opens up a new avenue for optical manipulation. And additional benefit of usefulness of studying this is, of course, the very obvious fact that these both orbital angular momentum and spin angular momentum have orthogonal states, and this can be obviously used for optical communication system, as well as what you can use this for is small position sensing. So the entire measurement depends on the symmetry. So even if there is some small particle which is slightly off axis, you can have a very interesting signature in the scattered beam, which can effectively reflect the position of the particle. So this has been shown to be useful for sub-wavelength position sensing as well. And the detection of this simultaneous measurement, very first approach was interferometric measurement, where you have a reference beam with the beam whose state you want to reconstruct, and you interfere them together, and you get a fringe pattern or interference pattern, and from that you try to reconstruct the incident state of the beam. More recent approaches involve very complicated and very nice nanofabrication techniques also, where you can have a radially placed nano antennas, and this can this scattering can depend on the flow pattern of the incident beam, which again depends on the circular polarization and orbital angular momentum state of the incident beam. And more recent work which has come out in very recent article in the Laser and Photonics review is that you have very complicatedly manufactured metasurface, and you impart a beam on it, just paraxial beam on it, and the transmitted beam will have different will transmit it to different region depending on its incident state. But all these methods are effectively tedious to some extent, because this interferometric approaches would require more complicated alignment techniques, and of course we know that the nanofabrication techniques would require equally, if not more, complicated nanotechnologies to develop. What we do is that we drop cast a single crystalline silver nanowire. These are chemically synthesized silver nanowires having monocrystalline characteristic on a glass substrate on a cover slip. and we excite this nanowire, or we scatter the incident beam, which is focused onto the nanowire with a 50x 0.5 Na objective lens, and we collect it with a 100x 1.49 Na objective lens. What this does is that since the collection Na is much higher than the incident Na, we can have much greater region in the collection scattered light, which is in the Fourier plane that we are measuring. We can have a much higher region where we can study the scattered light, which doesn't have any which doesn't have any signal due to the incident beam. It is just a scattered beam, and that scattered beam will have the characteristic of the incident beam property. And how do we do it? So there is a sample plane. You can see what happens is if there is any sample which is emitting light or scattering light, any light that is scattering into or emitting into a particular direction, if there is a lens that is placed exactly at the focal length from this sample, all of this will get focused into a particular point. This is the ray optics point of view, and each of this point basically determines the angle or the direction my beam is going to, and that is what we characterize the momentum of the beam, the k vector of the beam. And usually when we try to look at it from objective lens in a microscope, this is within the chassis of the microscope, so we cannot really measure that exactly at that aperture. So we use relay optics to project it onto a charge coupled device, and we measure the Fourier plane there. This is the optical setup that we use. We have silver nanowire on a sample plane, and laser Gaussian beam is diffracted through a spatial light modulator, and then the light is sent through the sent to the objective lens, and the transmitted light is again collected using a 1.49 Na objective lens and projected onto the charge coupled device. But what this nanowire does is that this nanowire, since this is an elongated nanowire, and in our case it is oriented along x-axis, what this nanowire does is that it breaks the symmetry of the system, right? So so depending on the incident linear polarization of the objective lens, the scattering pattern changes. For example, when my polarization of the incident beam is aligned along the nanowire, then all of the light that we get is within this particular circle, which is called the allowed region, or within the critical angle, and when my polarization is y oriented, which is transverse to the nanowire axis, then we get light within the critical angle as well as above the critical angle. This is the light which has refractive index higher than that of the air. So this is the leaked light, which can only be accessed when you're looking through the glass substrate. This is the forbidden region, or you can say when you're coming through the glass, this is the light that will go through total internal reflection, because these have higher momentum than that of the surrounding medium, that is air. So we get signal above the critical region only when my polarization is y. So what you can think is that when I have circularly polarized light, then its x component will obviously get scattered into within the critical angle, and its y polarization will have only signal in the above the critical angle. So by studying this pattern very carefully, we can obviously make an attempt to distinguish what is the orbital and the spin characteristic of the incident beam. What is also to note is that we have already done a previous work where we have used this particular critical region light to determine the state of the orbital angular momentum, and this is a previous work that we had done. What we do in this case, that we have circularly polarized beam. For this case, left circularly polarized LG10 beam, and this is right circularly polarized 10 beam. And we can, since this is a circular pattern, we will only consider the upper half of the beam for now. And we study the pattern within this inner circle and outer this circle separately. So for ky is equal to greater region, that is the upper half, within the critical region, what we can see is that the intensity distribution of LCP and RCP changes when even when my orbital flow is the same, that is LG10. But above the critical angle, it remains the same, although its preference of the scattering slightly differs from one case to other case. So by studying above critical angle and below critical angle, we can determine what is the state here. And if we quantify it using directionality, that is integrating the intensity on this side, on the two side with respect, and subtracting it from one and normalizing it with respect to the total intensity. For this case, we get positive directionality. This case, we get negative directionality. Whereas in both of these two cases, we get negative directionality. That is determining the orbital state of the beam in the supercritical region, and within the critical region, we get the spin angular momentum information that is actually changing in these two cases. And if we again consider the lower half of the case, we can obviously get the exactly opposite thing, because the upper and the lower half is exactly antisymmetric to each other. And in this case, we get positive directionality, negative directionality here, and positive directionality here. And again, the directionality of these two also gets inverted. And what is important to note here is that the directionality in the LCP case is lower with respect to my upper case, which actually shows the total transverse energy flow, which is much higher for the RCP case. Sorry. Yeah. Okay. And again, if we consider for LG -10 beam, yeah.
So
yeah.
If you can wind up in another 3 minutes, then we can take some.
Yeah, I'll wind up. So for again, we can look at what is the case for LG -10 beam. Then again, you can see for the LCP case, we get a positive directionality here, as in the case in the previous case. We can see when we are considering the ky is equal to 0, ky greater than upper hemisphere of this PFP, we get positive directionality for LCP, negative for RCP. In this case also, you get positive directionality for in this for upper for the LCP and negative for the RCP. And for the above critical region, again, the directionality inverts, indicating the inversion of the sign of the topological charge here. This is valid for even LG20 beam also, where we can see for LCP, we get directionality upper on this side. Here we get 3 fringes indicating the topological charge, because for LG N0, we get N+1 fringes in the Fourier plane. And we see that only the penultimate fringes, the extreme fringes, show this kind of inversion. So we only consider the integrated intensity of those 2 fringes only. The middle fringes have almost similar intensity, both in these 2 cases. So as we go from LCP to RCP, the directionality inverts, whereas for the supercritical region, the upper this two region, we see that the directionality remains the same, indicating that the sense of the orbital flow has not changed. Yeah, so this is again quantified by the directionality, which shows positive for this case, negative for this case, and for positive for LG20. For both of these 2 cases, we get negative directionality here. So we talked about angular momentum of optical beams and their manifestation or energy flows. We also talked about what is the polarization dependence of the scattering behavior of the plasmonic nanowire we use, which actually acts as a strip diffractor, and we talked about differential sensing of the angular momentum state of the incident beam. With that, I would like to thank my institute, ISER Pune, for supporting my research, and I would also like to thank DRL Optical Student Chapter for giving me the opportunity to present my work. I'll also thank DST and both AFRL for the funding opportunities that they give us to pursue our research. Thank you.
Thank you, Deepta, for such a nice talk. So now we have a few questions. So what about the detection of negative charges?
Yeah, I showed, right. for negative charges, this also works, because in the last case, what you see for the upper hemisphere case only, for positive charges, you see negative directionality. And for negative charges, the directionality above the supercritical angle is changing. So it actually detects the negative charge of the topological of the negative topological charge.
Okay, another question is, while you are discussing about your experimental setup, you are using some white light, right? So what is the
Yes.
use of that?
I have to visualize the orientation of the nanowire as well as the what I am scattering from, right? So for that, I need the white light to visualize. It's a conventional microscopy setup.
Okay, the last question is, for the detection of orbit, this charge, I mean, what is charge? We usually do the easy tactic to interfere with this Gaussian beam with an angle. So you'll get fork pattern, so which is a very robust method. So what is your comment on your technique over to that one?
See, that is obviously a technique that has been widely used and for many cases, and that is also one way that people try to measure the phase of the beam also. But to implement in a on-chip configuration, you need lower footprint, or you need to minimize the entire detection scheme. So our nanowires are roughly having diameter 300 nanometer, and its length can be anywhere between 10 micron to 30 micron, or even smaller than that. So it effectively minimizes the entire detection scheme. And also those interferometric measurements require slightly, although they are robust, but they require slightly involved alignment procedures, where in this case the scattering is pretty robust, whether you scatter from one end or the other end of the nanowire. It doesn't really matter as long as it is interacting with the silver nanowire.
Okay, thank you. We have one more last question. So what is meant by a negative kx by k0 that you have plotted?
Negative ky by our objective lens back aperture is always a circular aperture. So we consider that the angle that we can consider. So the beam direction is quantified by the angle, right? So it's a polar coordinate angle. So it can be either in the first quadrant, second quadrant, third quadrant, or fourth quadrant. Like in geometry, we assign positive x, negative x, positive y, negative x, negative y. Just in this case, we can assign the angle according to that, and the sign is again follows that.
I hope that answered the question. So let's thank the speaker once again, and I'm handing over to Soumya for chairing the remaining session. Thank you.
Hello. I'm Somu and will be chairing the rest of the session. As the fourth talk of this session, we have an invited talk by Dr. Wagner Tavares Bueno. Wagner is currently a postdoctoral fellow at the University of Witwatersrand. He completed his undergraduate studies in the Federal Fluminense University in Brazil. He also completed his MSc and PhD degrees in the Quantum Optics Laboratory at the same university, focusing on second harmonic generation of structured light, with particular emphasis on optical phase vortices. His current research interests includes various applications of structured light, the interaction of light with matter, as well as nonlinear photonics. With this, I would like to invite Dr. Buono to deliver his talk, invited talk titled Structured Light in Second Order Wave Mixing. Over to you, Dr. Buono.
Hi everyone. Do you guys hear me well?
Yeah.
Okay. Just gonna share my screen now.
Yeah, it is visible.
Okay. Hello, everyone. Thanks for being here. My name is Wagner Tavares Buono. I'm a postdoctoral fellow at the University of the Witwatersrand, and I'm here to talk to you about structured light in second order wave mixing. So first, we have to define what do we mean by structured light. So structured light means that we shape light in its many degrees of freedom. And by that, we mean there is an electric field. So there is an electric field here, which has intensity and amplitude. It has a transverse structure, which includes phase and intensity. It has a temporal dependence, which is the frequency or the wavelength. And it also has a path degree of freedom, which is the propagation of a laser beam. And lastly, we have the polarization degree of freedom, which is the direction of oscillation of the electric field. And all of these degrees of freedom come into play in many effects, but more specifically in nonlinear effects, they can all be intertwined and combined and have a lot of weird effects as well. So if you want to know more about the structure of light, I know there's going to be a great talk later about this, but you can also check out our review paper on the subject. Now, let's talk about frequency conversion now. It's in three-wave mixing or second order nonlinear processes. There is this very interesting phenomena, very unique, that is frequency conversion. Well, that means that we have a photon of a given energy, and this photon has an energy that depends on the frequency. Now, let's say we have two photons of different frequencies, and then we impinge them on a nonlinear crystal. They will get then absorbed by the crystal, which will emit a third photon of a different frequency. And by the conservation of energy, this is a parametric process, so it conservates energy. So that means that the medium will absorb two photons, then emit the third one, and the frequency of the generated photon is going to be the sum of the input frequencies. Now, let's say the two input photons have the same frequency. They enter the crystal and then a third photon is generated. But now the frequency, it's of course the sum of them, but since they are the same, it's just 2 times the input frequency. Now we have these two nonlinear processes. The first one's called parametric upconversion or sum frequency generation, and the second one's called second harmonic generation. And in this way, two photons are combined to create one photon of a bigger frequency or a bigger energy. But what if it happens the other way around? What if we enter a crystal with a photon of a given energy, and then the medium breaks this photon into two of different frequencies? So that can happen. So that means that the nonlinear crystal absorbs this one photon and then emits the first photon of a given frequency and then the third one of another frequency. And of course, it's a parametric process, so the total energy is conserved. Now, in the same sense, the two generated frequencies can have the same wavelength. The two generated frequencies can be equal, and that means we go to the degenerate case. And this process is called spontaneous parametric down conversion. And it's very similar to the previous ones, just the other way around, in the other direction in energy. And it's very interesting. This is how this process depends on frequency. But they also depend on polarization quite heavily. Let's take a look on, for example, a wave propagating in a nonlinear crystal, and then we want to check out the second harmonic generation of it. So lambda, which is proportional to the inverse of the frequency, gets turned into half because the frequency is double. So we have a lambda of 1064 nanometers and then enters the crystal, and then it generates wave of lambda half of it, 532, but it oscillates in the same direction as the input one. So that means this process, we call it type 0, phase matching, second harmonic generation. But that cannot be the case. I mean, generally, more common in textbooks, we have type 1 second harmonic generation, which means that you enter the crystal with a given polarization, a wave with a given polarization, and then what's generated has orthogonal polarization. And that we call type 1 second harmonic generation. But there is also type 2 second harmonic generation, where you need both vertical oscillating waves and also horizontal. And then you create second harmonic, but only in one polarization component. And that is very interesting because it couples the two spatial profiles of the two polarization components. Now, I've talked about frequency, polarization, and now path. So this can happen collinearly. So that's when the two beams are traveling together and enter the crystal. And then the second harmonic is also generated in the same propagation direction. Um, However, these can be independent processes. So I can have H and V, H plus V makes a diagonal polarization. So when I enter the crystal, let's say in two different beams in two different paths, they're going to generate different processes. But now, if I cross the two beams inside the crystal, what happens is there is the second harmonic generation of the first beam, the second harmonic of the second beam, but also a third process in the middle that couples these two beams. So it's a constructive interference of two nonlinear processes. And I will explain why this is interesting later. And and we call it type 2 non-collinear second harmonic generation. Now, so far we have talked about frequency, polarization, and path, but this is pretty much textbook stuff. Um, how can we make this more interesting? We can use the other degrees of freedom, of course. And the ones that I mentioned, intensity, phase, and even spin, I didn't mention before, but it's also going to appear here. So let's take a look at it. What's actually happening inside the crystal? Because we put up this representation of a wave, it's actually just one point in the transverse profile. And that's the time oscillation and the polarization. So it's pretty straightforward. If you have only one point in your wavefront, it's pretty fine. But now if you have a very complicated wavefront, then the outcome gets really messy as well. Now we do have to check out what's happening inside the crystal. Let's take a look. So what happens is there is a coupling of the waves that enter the crystal and the waves that get generated as well. So in this case, let's say it's some frequency generation. So we are generating omega 3, and omega 3 depends on omega 1 and 2. But omega 1 and omega 2 also have different spatial profiles. And they're also going to be generated inside the crystal just as omega 3 and omega 1, with, of course, different probabilities. And there's this flow of energy is mediated by this constant G here. Now, let's just look at quickly at the case of second harmonic generation, type 2. What happens is the generated field is proportional to the product of the polarization components of the field that enters the crystal. And that is pretty interesting because, well, let's put some weird shapes on each polarization component and let's see what happens. And it's obvious that the shape of the generated light field depends on the shape of the input light field. In this sense, we can say that in these second order wave mixing processes, light shapes light. Now, okay, what sort of structures are we interested in? Let's say a Gaussian beam, for example, it's the most common standard one, which is a plane wavefront, but we also have a donut beam, which has a helical wavefront, and that's a Laguerre Gaussian with L1. But then if we increase the L, the number of singularities, as you may have heard from previous talks, it increases, and also the helical wavefront changes in shape. And we can also increase into L3 and so on and so on. And they can also have opposite-handedness. So we have right-handed rotating a direction and left-handed rotating another direction. And this is all tied to this term here in the electric field, this azimuthal phase structure. Now, okay, so what happens when we do second harmonic generation with OEM? So there's the seminal work by Dolakia in '96, where they show that if you have an LG beam, a fundamental LG beam, when you do second harmonic generation of it, you double the OAM as well. And yeah, so inspired by that, we thought, what if we do second harmonic generation of type 2 and put different OAM on different polarization structures? Now, this is the expression for the fields that we are using, and this is a visual representation of the wavefronts. And then they enter the crystal, and then what comes out of the crystal, we assume it's also going to be helical wavefront, and then we want to measure that. We want to measure the helicity of this wavefront. So how do we do that? Well, we are going to use a technique called the tilted lens. And the tilted lens technique, you have a helical wavefront LG beam, which passes a lens that is slightly tilted rotated around the Z direction, and then it gets transformed into a Hermite Gaussian beam. And this Hermite Gaussian beam, it has singularities, and the number of singularities is related to the OAM, and the inclination of the Hermite Gaussian, it's proportional to the inclination depends on the sign of the OAM. So if it's 45, it's minus 45, it's plus. And that's how we're going to measure the output OAM that we have. Now let's look at the results we got finally. We realize that the OAM that's going to get generated is going to be the sum of the input OAMs. So we have one OAM in H, other one in V, and then we generate the sum of it in the second harmonic. So to show that, we fix one OAM and then we vary the other one. And then as you can see from the dark fringes of the Hermites, they increase and decrease with OAM. So here we have 2 and 1, and we have 3 dark fringes. And here we have 0 and 1 dark fringe. But then when we shift the sign, so when we go to L2 minus 2, and then L1, the sum of it is minus 1. So it only has one singularity, but it shifts the direction of the Hermite. Okay, that was the first. First result we got is the conservation of OAM, or the algebra, the OAM algebra that we can do in these nonlinear processes. Now we also realized the following: if you look at these results here, you're going to see that the L0 has a cigar shape, which is quite weird. So what we realized that was happening is that when you have OAM or wave mixing, and then the L's have different signs, the OAM are opposite chirality, then radial orders will appear. So this is quite non-intuitive if you think about it, because when you're going to generate light inside the crystal, you can only generate light where there is light, and both beams are donut shaped. So in the near field, that means in the crystal plane, you always get a donut shape for the second harmonic. But then if you let it propagate in the far field, outer rings are going to appear, and the number of them is related. It's related to the OAM. So as you can see here, we have L equals to 1 and minus 1, which gives us OAM 0, and then just one ring. But here we have OAM 2 and minus 2, which also has OAM 0, but then we have 2 rings. And they only manifest in the far field, and we wonder why is that, why that happens. And that's because the generated field is proportional to this product of LG beams here. And when you get to this expression here, if the L's are the same magnitude, then you don't have any azimuthal phase, but you still have the R to the power of the sum of the modules of L. So, and then this can be decomposed into LG polynomials of L0 but P different than 0. And that means that this is a superposition of LG modes of different radial orders, and they're going to propagate and gain different propagation phases. So as they propagate, they gain different propagation phases. That's why the outer rings appear in the far field. But there's something quite curious about it, because seems to be just a diffraction effect. So we can actually like generate a field like this in an SLM, and we don't need a nonlinear process to do that, and that's what we realize. So we take this field and then we generate in linear optics method. So first we compare the second harmonic experiments I just described. Now we take the transfer function that we assume is going to be in the crystal, which is the product of the two LGs, and then we code that into the SLM and do an imaging system. And basically, this is what we have. We show that this effect can be replicated, but more interestingly, we can take any product, a product of any number of LG modes, and then separate them between their chirality, their positive L's and the negative L's. They all couple together, and then if there is a different signs for L's, then we can make this product very general and show that for any products, a product of any number of LGs, this theory is still valid. So it's a chiral relation that transcends the order of nonlinearity. Any order of wave mixing is going to have that. And that's what we realize on the results in the second harmonic and on the linear optics SLM experiments, they were quite identical. Now, what other interesting things can we do from there? Now, we also studied second harmonic generation in the non-collinear regime, as I told you about. So we do have horizontal polarization coming into the crystal, vertical also coming into the crystal, and they cross inside the crystal, and then we put a half wave plate, and we see what nonlinear processes are coming out of it. So if we set the half wave plate at 0, that means that this this beam with H polarization is going to go through the crystal and not going to generate second harmonic generation, because it's a type 2, so it needs both H and V. And all the same for this V being here. But since they cross, at the points where they cross, in this specific plane, we do have H and V, and that generates second harmonic generation here. Now, if we rotate this half wave plates and then make the polarization of the beam rotate by 22.5 degrees, then we see that all three processes happen with the same probability, with the same intensity. So we generate second harmonic of this H beam, second harmonic of this V beam, but also we still generate the product of them. That means that roughly that we have two nonlinear processes happening and they interfere constructively. And then if we keep rotating these wave plates until it rotates the beams by 45 degrees, so that means diagonal and anti-diagonal, then we completely kill this process in the middle. So we make these nonlinear processes interfere destructively. And that is quite interesting because it allows for all optical switching. By rotating the wave plates, we select what nonlinear process is happening, what nonlinear processes happen, and which ones don't happen. We also studied and showed that the spin angular momentum of light can come into play in a nonlinear process. So if we have a vector beam here, and then a beam with spin angular momentum, and then we impinge those in the crystal. Now we use non-collinear setup, but we are only interested in the outcome in the middle. we show that the generated OEM is equal to the input OEM plus the spin OEM. So yeah, so whatever OEM we put in the crystal, we're gonna get that same OEM plus one or minus one, depending on the spin. So it's a very interesting interplay between polarization, spin, and propagation direction. And what cool applications can we do with that? So since we can do modulation of light inside the crystal by using light, we can also do mode detection. And that means whatever mode comes in the crystal, we can use a matrix array to detect what mode is that. And not only simple modes, but also very complex shapes as well. And recently, there, it, a lot of modes have been studied. So Hermite Gaussian, Laguerre Gaussian, Ince Gaussian, parity-defined LGs, parity-defined Laguerre Gaussians. And there's all sorts of selection rules involved, like what modes come in, given that some modes come in, what modes come out of this process. And in this paper, the authors like summed up really nicely all the selection rules involved in all these modes. And it's very counterintuitive. You wouldn't think that just by manipulating OEM, you would create radial diffraction, but it does happen. Now let's go the other way around in the energies direction. So I talked about second harmonic generation. What about SPDC? So if in SPDC, if I enter the crystal with a given wave shape, I generate two fields now. And I'm talking about the degenerate case where they have the same frequency, but not necessarily the same shape. So what we already know about it is that if the beam that comes into the crystal and generates SPDC is a plane wavefront, just a Gaussian, then it generates OAM, but of opposite chiralities. So for every L that gets generated, it's going to generate a negative L. And that is summarized by this, this plot here we call the spiral bandwidth. So given that we generate L in a signal beam, what L do we get in the idler beam? And it's anti-diagonal, which means if L is 5, LS is 5, it's going to generate -5 in the other one. But that's if we pump the crystal with a Gaussian beam. What happens? Well, how about if we want to shape this spectrum here? So we have a specific shape in the spectrum that we want, and then we think, oh, can we shape the pump to get this specific spectrum? Yeah, so again, the OEM conservation is there. So what if we want a specific shape in the output of an SPDC? Can we shape the pump, the input pin, to give us precisely that without any post-selection or without any techniques after the crystal? Well, it turns out we can by using overlap conditions, overlap coefficients. We managed to do a theoretical study where we generate high dimensional maximum entangled states right out of the crystal just by shaping the pump beam. We also did entanglements in new bases. For example, the radial bases, we generated maximum entangled states that has 3 separated radial orders. And we also managed to achieve phase control between the generated fields just by shaping the phase and the intensity of the pumping. And that was the cover of this recent issue of the Advanced Quantum Technology Journal. So in conclusion, either in second harmonic generation or in SPDC, we now know that light shapes lights and many degrees of freedom can come into play. So with all that in mind, we are still figuring out the rules that govern these processes. So at this current point, we are figuring out the rules. And as soon as we do that, we look at very interesting applications we can do with that. So yeah, that's it. Thanks everyone for watching. Oh, this is a list of our collaborators. And this is a recent picture of our group. And thanks everyone for watching.
Thank you. Thank you, Dr. Bono, for such a nice talk. We'll take some questions now.
Sure.
Yeah. From Subit, Subit asking is, while you passing in some angle, how the phase matching will affect?
So that's a very interesting question. The phase matching can change a lot depending on the angle. So the trick here, which I didn't tell, it's a technical aspect, of course, is that it's barely non-collinear. The angle of incidence, what's about 5 degrees. So they were barely collinear, and in this way, we make sure that the wavefronts are not too slant between each other, and the phase matching is still valid. So also notice that this is not a type 0 crystal, it's a type 2. So the phase matching in this case only means a slight shift in efficiency.
Okay. His next question is, instead of using diagonal, if you use anti-diagonal or circular, where there is a relative phase between H and V, what will be your comments on the results?
So I'm not sure what slides are you referring to. Let me
Actually,
go back a bit.
the matrix you have shown. No. Yeah, the next one.
This one?
The
No.
sorry, sir. Sorry, the previous one.
Here.
Yeah.
Yeah, so if I
The
use
previous.
any combination of polarization states that is non-orthogonal, then I can always decompose that same states into these orthogonal bases. So for example, if I use D and V, then this D will have a V component. And the same if I use circular. But now I think your question is more related to what if I use D diagonal polarization and then circular here. So I don't know. I mean, I don't think it would change anything in this sense. I don't think I would be able to achieve this optical switching, but I would need to see the math because that's a very interesting question.
Okay, thank you. From Satyajit, he's asking that, can you please explain the structures obtained in the slide before conclusion slide?
Okay. I think you meant these ones, right?
Yeah, the yeah,
Yeah. So
maybe Satyajit.
so here we
Yeah.
have a high dimensional maximum entangled state. So we pump the crystal generates SPDC, and now we detect OEM in the generated beams. And let's say we detect we go for L signal, and then we detect L0. We're gonna detect L0 with for Li, and that's the highest very high coincidence we get. But now if we detect LS1, we are also going to detect Li1. That's what this big yellow bar means. So we're going to get a lot of coincidences if we detect in both of these states, and they're going to have the same probability as the L equals 0. So that's what we mean by maximum entangled states, that we generate a lot of biphoton states that have the same probability by shaping the pump. And in this case, the structure, we use a different degree of freedom, which is the radial one. So if I detect radial orders on the generated fields here and here, I'm gonna have a maximum coincidences when both p's are 0, when both the p's are 1, and when both of the p's are 3. And we specifically set the P equals 2 to be 0 here, just to show that we have a tight control of these entanglement structures. And now in the third one, it's similar to the first one here, but now we also do phase control. And when we do phase control, so this is coincidence count here, and this is phase here. Now we generate state biphoton states that have the same probability, but now they have a non-zero phase between them. I hope that answers your question.
Yeah, thank you. Thanks to the speaker once again. So now our next talk is an invited talk by Professor Basudevan Roy. He's currently an assistant professor at IIT Madras, India. He has done his MS from the University of Maryland and PhD from IISER Kolkata, both in physics. He was an Alexander von Humboldt postdoctoral fellow at the University of Tübingen, Germany. He got several awards as a student and an academic. His research interest mainly covers experimental soft matter physics, high resolution imaging, and optical tweezers. He is currently studying the effect of light focusing on linearly polarized light and the focus on optical tweezers apparatus and how it may influence particle dynamics. With this, I would like to invite Dr. Roy to deliver his talk titled "Study of Soft and Biological Matter Systems Using Optical Tweezers." Over to you, sir.
Thank you so much. So can you hear me?
Yeah, you can hear me.
Okay, sure. Thanks for inviting me, for giving the talk. So I would go straight away to the sharing my screen. Share screen here. Can you see the screen?
It's coming. Yeah, it is visible.
Okay.
Yeah.
So the title of my talk today is Study of Soft and Biological Matter Systems Using Optical Tweezers. I generally work with optical tweezers and its applications to soft matter systems. So the outline of the talk is going to be like this. We are going to be talking about the basics of optical tweezers, and then I'll go into the specific details of rotations. So I specialize in rotations in optical tweezers, not just translational motions. I have done a lot of work on rotations, and I'll show you precisely what I've done. And then I'll show you some applications to cell biology systems. And then I'll show you some other applications of general soft matter systems, breaking up the diffraction limit in absorption spectroscopy, and then the nanowaves on air-water interface in sessile water droplets. So the basics of optical tweezers. So you must have heard about Professor Arthur Ashkin, who developed this optical tweezer system, and for which he was given the Nobel Prize in 2018, I believe. So what he did was he was actually looking for, he focused a beam of light tightly into a sample cell with the particles. And he found something very interesting. He saw that the particles were pulled into the focal point, and then it was pushed along the axis. He was actually trying to balance this beam by putting two oppositely aligned laser beams, and in the middle of that thing, he wanted to align this particle. He wanted to put this particle there. When he was trying to do that, he saw this. It was getting pulled in, and it was getting kicked out along the axial direction. So he reported that early in 1970. And then he certainly later on also showed that you do not need these two beams to trap the particle in free space or in water. You can actually just use a single beam itself. So that basically it forms a three-dimensional potential well, and I'll tell you precisely what is the mechanism for that. Just be aware that there are two forces involved here. One is the scattering force, the pushing force into the particle. From there, the second one is the gradient force. Now, please note this is the form. This is the form for the gradient force, and here you can see that this is the gradient of the intensity you have. The F gradient is minus some coefficient times gradient of intensity. Now, this is the polarizability of the system. So essentially, that's the main force that is acting here. Okay. Now, as I was telling you, it is the force is proportional to minus gradient of intensity with the coefficient actually. And you can actually trap it in three-dimensional well, and you can also apply torques. You can apply piconewton forces at thermal noise limit and also torques of 500 to 1000 piconewton nanometers. So I sort of specialize in this torque business. I'll show you what I'm talking about. Nonetheless, how does the optical tweezers work? So the optical tweezers essentially in this cartoon, you can see that if you have a Gaussian beam of light, the laser beam, of course, is a Gaussian laser beam, and then you focus it down tightly to a tight spot, and then if the particle is displaced from the center, more light is refracted by the particle towards from the center to the outsides, while less light is scattered or refracted by the particle towards the middle from the sides. So that there is a sort of a momentum, by momentum conservation, you can see that the particle gets pulled in towards the center of the Gaussian beam, and that's how it is trapped. Basically, that's the basic principle of the optical tweezers. The same thing happens in the axial direction as well. If you focus it down into a axial spot, and so you have a three-dimensional potential well like this. So that's the basic principle of the optical tweezers. And then if you put this sort of a system in water, it will confine the particle in 3 dimensions. Now, if you look at the Langevin equation, mx double dot plus gamma x dot plus kx is equal to some forcing term, the first thing that you will encounter is that the gamma x dot term in water is much larger, about 5 orders of magnitude larger than the mx double dot term, which means that it sort of drops out of the equation, and then you are left up with just gamma x dot plus kx equal to some forcing term. Now, Einstein showed that this forcing term is in Brownian going to be Brownian motion due to the water molecules, and then it is like a sort of a Gaussian shaped random noise. There is no correlation between the position of the particle at one instant and the next instant, but the overall form of the random noise is Gaussian. So if you solve that, you can see that it will take the shape of a Lorentzian, and here it responds up to a certain frequency. The trap actually confines the particle in free space to a certain frequency, and after that it sort of rolls off at omega to the power of -2, and till then it is a constant amplitude. And so based on this amplitude, you can actually calibrate this optical tweezers. So you can calibrate the optical tweezers by finding out what is the amplitude and what is the corner frequency. We call this the corner frequency at which it starts to roll off. So that gives you the trap stiffness, and the amplitude gives you the sensitivity of the system, the sensitivity of the optical tweezers. So essentially, if you compare with the Einstein's relation, kVt over gamma is equal to the diffusion coefficient, and you replace the diffusion coefficient with some beta squared times d volts, because the amplitude of the Lorentzian will give you d volts. So then you can find out beta square from there. Gamma is the drag coefficient in there. So kVt over gamma, you know that's the Einstein's relation. kVt over gamma is the diffusion coefficient. So from there you can find out the sensitivity of the system, as in how many nanometers per volt. If you give it in volts, how many nanometers is it? We also use it to calibrate the rotational motion. In that case, it will be how many radians per volt. Okay, and the trap stiffness is given as 2 pi gamma fc. So that's the trap stiffness. So this is a typical optical tweezer setup, and in this optical tweezer setup, there are all kinds of components in here. This is my own system is much simpler, but I'm just keeping it for schematic. Here you focus it down into a tight spot, and then sort of so sort of it focuses it down into a tight spot here using 100x objective, a high numerical aperture objective, and the light is then recollected after passing through the sample chamber by another objective, and then it goes into a quadrant photodiode. There's a dichroic mirror here, and the illumination comes in from this side. The LED illumination is collected on the camera here. So that's a basic system, and we have also detected put in some rotational elements to detect the rotational motion. Okay, I'll talk about these rotational motions in more details just shortly. So some of the applications of optical twisters is in rheology. You find out the viscosity of the medium, the viscoelasticity of the medium. If it is an active medium, how is the system behaving? Then you have equilibrium and non-equilibrium statistical mechanics. And then you have molecular biology, the study of molecular motors. You can actually also do the DNA and RNA conformational changes. You can put sort of a protein molecule or a DNA molecule in between two beads here, and then trap it with the beads, and then apply forces. The force extension curve gives you this sort of a behavior, this sort of a trend. When the protein domains unfold, the domains will unfold, and that unfolding of the domains gives it a certain kick, sort of the extension increases suddenly, and that you can use to find out the conformations of the molecule, the DNA molecule or the RNA molecule or the protein molecule, and it is being extensively studied now. That's the conventional optical tweezers application. So we thought that we'll do something different. So what do we do? Because I don't want to get into the single molecule business straight away. I wanted to study the cell biology aspects instead. So here you will be able to sort of use the optical tweezers to determine the cell properties, the cell membrane properties, the cell viscoelasticity inside the cell, and all these things. So that's what I wanted to get into. I'll show you more details about the cell biology aspects shortly. So I have, so you have an optical tweezer system. For that, you need three sort of things. One is the main goal, as in cell biology problems or molecular biology problems. What do you want to address? And then you also need the tweezers apparatus. But the third thing is also required for optical tweezers sort of study, and that is the probe. What sort of probe are you using? So I have used three different types of probes here. Birefringent liquid crystalline particles of RM257 materials, I call it BP. There are some polystyrene particles that I call PP. And there are some upconverting particles. And I'll show you some brief results from all of these three types of particles. So rotations in optical tweezers. So in the nomenclature of the airline, you can have a rigid body can have 6 degrees of freedom. You have the three translational modes, and you have the three rotational modes. In the nomenclature of the airline, you can have the roll, the yaw, and the pitch axis, the three-dimensional axis. Now, if you take it to the convention of the optical tweezers sense, the yaw motion is in plane rotation, as in the conventional rotation by using polarization of light. You apply a linearly polarized light, the particle traps in that thing, and then you turn the axis of the polarization, the particle will follow. While if you have rotations in the other two senses, the pitch and the roll, it has so far not been studied so extensively. We have done some work on that, and I'll show you that work shortly in this talk. Basically, you can take that's the take-home message for you if you want for this particular talk. So how do you do that? So we use this birefringent particles. So if you put it under crossed polarizers and you turn the particle, if it is at 45 degrees to both the polarizers, it will be a bright spot. While if you turn it and if you make it align along one of the two cross polarizer axes, it becomes a dark spot. Okay. Now that dark spot is not really perfectly dark. It has 4 lobes in it. There are 2 lobes and there are 4 lobes, and that's what I'm going to use for not only the yaw rotation. I'll show you how it can be used for pitch rotation as well. Okay. So how do you do that? So one of the first things I did was this pitch rotation. This is the out of plane rotation. The simplest possible thing you can think of is by applying 2 beams of light, and you push the focus of one of the beams in. So you keep 2 beams of light, you take an asymmetric object, and then you push one of the focus in. And that's what we have done in the left-hand side. You push the focus in, and you can see it has turned like this. That's the pitch rotation, and this is the birefringent particle here. And that you can see this is the situation here, where you can see it has sort of the color is changing. You see, that's a birefringent particle under sort of imperfect cross polarizes, and then it sort of turns in this axis. And you can use this to, we recently published a paper in Journal of Physics Communications, where we showed that this you can actually make a torque wrench out of it. So you apply, you take this birefringent particle, and then you do the same thing there, push one of the beams in, and that's how you can avoid the particle from slipping, but yet generate controlled torques, controlled pitch torques in that sense. So now that leaves a question: how do you detect this thing? Because it's, using the asymmetric particle will give you a sort of a video cue to it. So, but then the spherical particle does not give you such visual cues. So how will you find out that the particle has turned? So in order to do that, we rely on the polarization properties of light. This is one of the first papers I published at IIT Madras. So you put it under cross polarizers, you will see a 4-lobe pattern. Okay, you'll put it. You'll get a 4-lobe pattern. Now, as you turn the particle in the pitch sense, 2 of the lobes will glow brighter, while the 2 of the lobes will glow dimmer. So that can be used to find the rotational angle. If you turn both by pitch and yaw axis, as in the in-plane rotation as well as the out-of-plane rotation, you get something like this, where there is an anisotropy in this direction, while these 2 directions were sort of symmetric. So here it works till about 60 degrees of angle, after which it does not work very well, but at least it works in this sense, and you can use it to detect the rotational motion. So one of the first things we do is, how do you calibrate this sort of system? We published this thing in Journal of Optics way back in 2018, I think. And then we showed that you can actually detect the motion of a kinesin motor as it is walking on a microtubule, and how is the tilt going? How is the birefringent particle tilting? If we find that the kinesin motor, while it is dragging the particle, it does not tilt in the pitch sense as much, but there is a sort of a more effect in the yaw rotational sense. But that detail I'm leaving out because of shortage of time. But that's one of the first papers that showed the pitch rotation detection. Okay. Now you can extend it to optical tweezers. You don't have to use a video imaging technique for doing this pitch rotation determination. What you do is you take this laser beam and you make it linearly polarized, linearly polarized with a polarizer, and then send it through the system, and you detect the orthogonal polarization to the input polarization. Okay, and then you put it under a cross polarizes, sort of an edge mirror. That gives you a QPD, sort of an effective quadrant photodiode. You select the halves of the 2 beams. The beam, you split the beam into 2 halves, left half and the right half, and you detect the difference in the halves. And from there, you can find out what is the rotational angle as a function of basically like how much it is turned by, using the optical tweezers. So this is, as I was telling you in the video imaging, this also works. And we have used this for our systems. We have used it to detect membrane fluctuations. So now, in order to calibrate the system, first we put the particle in water, and then we detect the pitch rotations at high resolution using these optical tweezers. And we find that the Lorentzian system can be you can get it back without any problems, and the corner frequencies are completely different from the X, Y, and Z. And so that we use for these optical tweezers for this pitch rotation determination. And again, as I said, the amplitude of the Lorentzian will give you information for the sensitivity of the system. Like you can convert from radian per volt to you can convert from volt square per hertz to radian square per hertz by multiplying the sensitivity factor, beta square factor. That's in radians per volt. And then you can find out how many radians it has turned by. So you see, the question is, if the particle turns by, how do you know how much angle it is turned by? So in order to do that, you have to know how much is the sensitivity of the system. So this is the calibration technique. So you let the Brownian motion do a little bit of jiggling around the equilibrium point, and you find out by a certain how much is the exact amount by which it is turned by, and then from there you can find out how much is the in radians how much it is turned by. So okay, and so using that, one of the first systems we studied using the this sort of a mode of rotation. Now you can ask, this is only a rotational mode, so how is it different from your conventional rotations? Basically, is it any use of doing these systems or not? If I just put in into water, nothing happens. In bulk, nothing happens. But if you take it close to the surface, the entire thing changes. The pitch rotation has a different dynamics than the yaw rotation completely. So it is actually useful to study the pitch rotations. And one of the first things that we show to do that is to put it on a membrane and study the membrane slope fluctuations. So the cell membrane will be I show sort of a result from Gabriel Popescu's paper, where he has taken an RBC, and this RBC membrane is not static. It is fluctuating all the time due to thermal fluctuations, due to internal active motion and all these things. So it is sort of, you can see the difference in the instantaneous fluctuations is this, and you can see this is fluctuating. So people used to study the normal fluctuations because it is easy to study. You can put it under the you can put a particle on the tweezers under the tweezers and put it on the surface, and it will give you some sort of a height fluctuations. And that height fluctuation will give you information about the membrane fluctuations. But then I sort of thought, how about you introduce a new thing? We introduce slope fluctuations. How does the membrane slope behave? Instead of the height fluctuating, how does the slope fluctuate? The slope will be going like this. And so that's what we are studying with this new mode of rotations. And I'll show you the advantages of using this system in shortly. So the slope fluctuates, and the cell turns, and the cell fluctuates, the membrane fluctuates, and the particle turns. And you can study how much it is turned by precisely, and from there you can find out how much is the sort of what are the cell parameters. You can find out the cell parameters from there. How do you do that? So, well, this is also another a video from Bidisha Sinha's lab in IIT IISER Kolkata. You can see that the cell membrane fluctuates more than there is some sort of a constant cell membrane fluctuating. You can even see some particle some sort of dynamics inside the cell. While this is not static. This is the region which is sort of glass, and you can see there's a clear difference in this thing. There's something happening all the time. So that's the membrane fluctuations. It's sort of wiggling around, and that you study the slope fluctuations using this. Okay. So now using that, I sort of I thought I'll study the membrane fluctuations, and I introduce this power spectral density. So I drop the particle on the membrane, and I study the normal fluctuations, and I study the slope fluctuations. And I'm trying to see how the power spectral density compares. So I find the conventional omega to the power of -5/3 that you see in the normal fluctuations, the height fluctuations. In that I got back, I have a power law of an exponent of 1.67 here with an error bar, a pretty large error bar, but it is sort of matching pretty well with the theory. But when you do the slope fluctuations, it gives you about -1.18 plus -0.151. So you can see that this is going as -5/3 while this is going as -1. Okay, and I'll show you in a moment that it does match the theory pretty well, and we have sort of done the theory for this as well. So, and then we also try to change the conditions a little bit. We put it under a drug called latranculin B, which is actin depolymerizing drug, which means that the cell membrane now is residing on a static surface. There's no actin poking along on it. So it is residing on a static surface, static hard wall. And that gives it a power law of -4/3, and that we also recreate here using the height fluctuations. -4/3 will give you 1.33, and that's plus minus 0.175. While the slope fluctuations will give you -1 exponent, 1.12 plus minus 1.121. So you can see that this power law remains static, remains invariant even if you apply a drug, or if you don't apply a drug under normal conditions, that still remains the same. Okay, so now we go into the theory aspects of this thing. So now this is a slope fluctuation. So how you can model that is by putting in, you can imagine there are two different points on the cell membrane, and one is pushing up. So then the slope will be given as y2 minus y1 by x2 minus x1. So by x2 minus x1 being the difference in the size of the base of your particle. So that remains constant at all times, because you know the size of the particle and the base will be roughly the constant. But this y2 minus y1 is nothing but the difference in the heights of your thing, difference in the heights of the position of the membrane at that two locations, and that is nothing but the gradient of the theta is approximately equal to the gradient of the height fluctuations. And then taking the Fourier transform, you can show that this delta r, the radial gradient of this thing, is it gives you the slope fluctuations is IQ h naught d to the IQR. And if you put it back into the expression for the power spectral density, you can show that the power spectral density will have this sort of a behavior where you have a q square term here, because that IQ came outside. Imaginary time, imaginary coefficient times q, the wave number came outside in that derivative of the Fourier transform. And from there, you can find out that this is this parameter. This is the integral that you have to solve to find the power spectral density. At high frequencies, you can assume the wave number is q cubed is much higher than q, and then this q term you can ignore, and then you will get kbt over 6 alpha omega. Alpha is the bending modulus of the cell membrane. While if you look at the normal fluctuations, the coefficient is much convoluted. You have other systems, other coefficients in there, not just the cell membrane bending the modulus. You will also have the cytoplasmic viscosity in there. So this one, on the other hand, gives you one direct expression for the bending modulus, and you can straight away find out the bending modulus without having any sort of complications of the cell cytoplasmic viscosity. There's one more advantage to this. This is also since this is the gradient, it has a directionality. So in one direction it is different. It is expected to be different. I am going to do some experiments where I'll try to find out how it is different by. So one of the directions should have a different bending modulus compared to the other. That would be a first time, because AFM tips poke on the cell membrane and there is no directionality to it. You can put a optical tweezers probe on top of a cell membrane and there will still not be a directionality to it. So this is one of the ways in which you can actually find out a directionality of it. So I'm going to be doing that later on. So that's one of my dream experiments for this. So that's an application for this sort of system. So later on, so as I told you, in the case of the Latrankulin drug, I also see that the same sort of power law persists. So the same power law will persist even there. So the same kbt over 6 pi omega comes, 6 alpha omega comes in, and you can see that you can find out, even if you apply the drug, that would be the first time that if you apply a drug and the membrane softens, you will still be able to see the bending modulus as a function of time while it is sort of softening. This sort of thing is not possible conventionally with optical tweezers, because the coefficient changes completely. As I told you, the power law was 5/3 in one case, while in the case of the LAT-B it was -4/3, and the coefficient was also different. So you can't just sit there and study the power spectral density like that, and it'll be a mess. So here it is much simpler to do this sort of a thing. Okay. So now I'll go to a different sort of a system where I study the pitch rotation using convection currents. So to do that, I sort of take a upconverting particle. Now this is a special type of a particle which has a hexagonal shape, and there I will be sort of this particle, actually, if you apply 975 light to it, it glows in visible lights. It will have visible emission at blue, it will have green, it will have red. Now the idea was to actually put this sort of a particle onto a gold surface and see what is the plasmon interaction between the emitted light and sort of the surface of the gold surface. But what we saw was something very interesting. We saw that as you heat it up and create a hotspot there, the particle starts to spin around like this. So basically what is happening is that there is a sort of a hotspot created, and then it induces convection currents in the vicinity. And that convection current makes the particle turn like this. It was sort of an interesting thing. People had sort of envisaged this in the past, but they did not realize that it can be brought so close to the surface by using a gold surface. They thought that in glass, the sort of circulation would be happening halfway down the sample chamber. It's very hard to sort of see these things, or a particle trap this particle there. So it's, when you bring it close to the surface, you can easily do it. So that sort of a thing we did. And we saw the same pitch rotation here. Saw the same pitch rotation using this thing, and it is very easy to generate this thing. We can sort of see that the polystyrene particles also do the same sort of thing, and that sort of confirms the convection currents. And we have used it to turn cells for tomography purposes. You can actually turn the cell completely in 360 degrees. And that way you can actually study sort of the cell from different angles. So this was published in Biomedical Optics 6 Press. And then I'm going to intracellular rheology. The intracellular rheology conventionally, so these are two cells. One is on the left hand side is the MCF7 cell, on the right hand side is a dictyostelium cell. You can see a trapped particle inside this dictyostelium cell, and the cell is still moving. It is executing in an agar medium. It is executing locomotion, while the particle is held constant by an optical tweezer. So we can do rheology with that. So that's till now I was focusing on the membrane fluctuations. Now I go inside the cell now. So here I do rheology, and for that I had to first benchmark. See, it is very hard to calibrate an optical tweezers inside a cell, because you see the refractive index changes from one point to the other, the viscosity changes from one point to the other. So how do you sort of standardize it? So we sort of realize that there's this. So and it is also complicated by the fact that the cell membrane cytoplasm is not just a cytosol. You have filaments in there. You have microtubules. You have actin filaments. You have intermediate filaments, and there is cytosol. So when you move a particle there, when the particle is moving, it depends. People have been getting all kinds of answers. If you take the probe size, you make it large, you get humongous results from viscosity. If you put in molecules, tracer molecules like fluorescent molecules, you get a completely different result for viscosity. So it depends upon the probe size. It depends upon if you pull it actively or if you do passive motion. So how do you standardize this sort of a thing? So we thought that we'll focus on the passive motion first. We will not do active motion, because if you pull actively, you can see that it is pulling against this fiber filaments, and clearly this is going to be obstructed. The filaments are going to be obstructed here, and then you get larger values of viscosity. So we'll just rely on passive fluctuations, passive thermal fluctuations, and then we use a model called the Jeffreys model. We actually showed that this Jeffreys model comes from the Stokes-Oldroyd B model of viscoelasticity, and you can show that this comes down to this nice form. It is a variant of the Maxwell's model called the generalized Maxwell's model, so it is consistent pretty well in the literature. So, so this model, if you take and if you show that you can show that the power spectral density goes as like this. You can find out 4 parameters from here. If you make a fit to that power spectral density that you get for passive thermal motion, you fit it to this power, the power spectral density here, you get 4 parameters. This 1 plus mu p over mu s is 1 parameter, the lambda is 1 parameter, and then the coefficient is 1 parameter. And then the third parameter that you get from here is this, the fourth parameter that you get from here is this kappa over gamma naught lambda. Okay, kappa over gamma naught is the other parameter. Lambda was the other parameter I showed. So there are 4 parameters that you extract from this system, and from there you can find out the system properties directly. The trap thickness you can find out directly. You can find out the sensitivity directly from here, and you can also find out the viscosities and all these things here. Now, there was a comment that if you take a curve and you try to find out 4 parameters from there, you can actually you can put in 4 parameters and you can sort of fit an elephant And if you put in 5 parameters, you can put everything. It was actually a quote from von Neumann. But we can actually simplify the system a little better. We can not, this is a calibration factor. So we can actually not worry about, you can actually normalize it to 1 and then worry about the 3 parameters. And so you can still get 3 parameters out of the system. We do not have to worry about the 4th parameter, so to say. Okay, so that's the thing. Using that, we fitted the power spectral densities, and we find that it fits pretty well to the beyond 10 hertz. Under 10 hertz, you get active motion, so it does not fit very well in basically. And you also, this needs further study, this under 10 hertz behavior. But since it is passive thermal motion, can typically appear above 10 hertz and beyond. So you can actually fit to it, and you can find out the system properties from there. This was one of the early attempts to the right-hand side. It was published in PNAS, but it fits Maxwell's model. And one of the blunders they made was they started to move the stage actively at a certain frequency. The idea was that you know the motion of the stage, and you can from there calibrate the motion of this system from there. If you move the stage by controlled amounts, you can find out how much is the motion, and you can infer the motion of the particle from there, or the how much is the particle responding in the system. But it actually coupled the cytoplasmic fluid, the cytosol, with the motion of the stage, and then they saw this sort of a huge band of noise here, and then rendered it useless to fitting parameters. So then they had to fit from 300 hertz and beyond. They lost all this system from 10 hertz, all this nice power spectral density they lost. So we do not try to modulate the stage. We have controlled known probe sizes, and from there we can find out these parameters. Okay. And using that, we showed that this is fitting pretty well to the beyond 10 hertz. And using that, we find out the 0 hertz viscosity. As I showed you, Jeffrey's model had 2 parameters, 1 plus mu p over mu s. So if you put omega is equal to 0, then you get mu p plus mu s is the viscosity you have. And compared with the solvent viscosity of water, you can find out what is the viscosity of the cell. It varies from position to position, as was expected. It varies from position to position, the health of the cell, and all these things it depends upon. And it goes from about 2 or 1 to about 12 millipascal seconds, where the viscosity of water is 1 millipascal seconds. You can find out the relaxation times. It matches pretty well with the magnetic tweezers experiments. It is about 0.005. And the drop stiffness could also be found out from here. This is typically about, in this case, 10 piconewton per nanometers. And this is published in Journal of Physics Condensed Matter. And then I also introduced a new parameter here called the pitch rotational power spectral densities. So this is something we are working on right now, where we not only do the translations, we also do the rotational motions measurements also. And we showed that this is giving basically the same thing. It is giving a cytosol viscosity. I was expecting that since there are filaments in there, does it actually give you the filament viscosity instead of the cytosol viscosity? We find that that is not the case. And matching it 1-to-1 gives you, it fits pretty well through the origin. If you assume it's fitting through the origin, and the coefficient, the slope is roughly 1 to within the error bars. And even the pitch relaxation time is also consistent with 1, which means that it is giving you the same parameter of the cytosol, regardless of what mode you are measuring from. And we also recently found out that if you put one tracer particle in there and do the viscoelasticity measurement as a function of time, this as the cell starts to die, the power spectral density starts to go towards the noise floor. It drops. And the viscosity, basically what happens is the viscosity is going up. In this case, as you find out, the mu p over mu s viscosity is going up. And as the cell dies, the cytoplasm is we believe this is depolymerizing, and it goes, all the fibers that are in there for the cytoskeleton goes into the solution. And that increases the viscosity of the cytosol. And we find this is a work in progress actually. So this is one of the early results for this. So now I'll go into some of subdiffraction absorption spectroscopy. So one of the basic ideas is that in an FCS or something, you have a focused beam of light. You focus it down tightly into a tight spot, and then the tightest you can do is a diffraction limited spot. The tightest you can do is a diffraction limited spot. But then I had an idea. if you use one of these upconverting particles which fluoresces in visible, and the particle size is smaller than the diffraction limit, there is going to be a region of space till which it will be subdiffractive, right? The emission from there will be subdiffractive. How does that work? Because it's a dipole emitter, is smaller than the wavelength of light. It is almost like a dipole in emitter, and it will have a 45-degree cone, a cos square theta dependence. It will have a 45-degree cone in which it is emitting, and then it will be smaller than your cone of the beam of light that you brought in for tight focusing, and so it will be smaller than the diffraction limit. So that we use to do some spectroscopy. And we find that if you put rhodamine B dye in there, the color changes first off, and secondly, keeping a reference of this blue line, we show that the green line, the green is absorbed by this dye, and then you can find out the concentration of the dye. My dream is to do sort of measure the single molecules in the solution. Do sort of an FCS kind of a thing here using this sort of a system. So that's what I want to do here. So that's just briefly describing this system. And then I go on to sort of show you nanowaves on the air-water interface. So if you have sort of a sessile water droplet and put it onto a surface, it was conventionally not known if you can actually visualize the surface from there. So we find that if you we can, as the particle starts, as the droplet starts evaporating, because you're using high numerical aperture lenses, this there is a focal distance is like 200 microns as through this thing. So if you're using a glass surface cover slip that separates the oil from the water, the oil is, because it's an oil immersion objective, and it separates the water from the oil. Now that is about 170 microns thick, and so you only get like 30 to 40 microns of visibility region that you can see on the other side. So as the droplet evaporates and gets down, when you get into that range, it starts, we can visualize it. That was one of the first sort of realizations from there. But we also realized that this membrane is not static in that case. The cell's surface, the air-water surface, is not static in that case. It sort of starts oscillating. So we put in two particles and we showed that the the air-water interface actually oscillates like this. And there are sort of nano waves propagating on the surface at the nanoscale of the extent of 500 nanometers and amplitude. And this thing propagates in the axial direction by using two different modes of motion. It moves in the azimuthal direction, and it does not move in the radial direction as much. By using these two particles, you can show that if you align the particles properly, one will give you configuration of the azimuthal direction and one will give you radial direction. If this case is the particle is moving in, of the wave is moving in the azimuthal sense, it will have no phase, while the other will have a large phase difference, and that's what we see here. It's published in Optics Express. So that's, I think I'll stop here. So yeah, so briefly, we are working on pitch rotation using novel kinds of particles which have also magnetic properties. So you can actually turn put a magnet, trap the particle with optical tweezers and put some magnetic field around it. And you can use the magnetic fields you can apply larger forces. You can apply 1 nanonewton of forces, while you can use the optical tweezers to detect that at high resolution, the motion at high resolution using the optical tweezers. So that the combination, this is in the future kind of work. You can do all sorts of rotations, you can do all sorts of translations, and you can detect it at high resolution using the combined system. So, okay, I stop here. So this is my group, the postdoctoral fellows, Gunasil and M, and the 2 students that have graduated, and there are like 6 students working with me presently. So, okay, and I thank all these people for being my collaborators and helping me. Thank you.
Thank you, Professor, for your wonderful talk. We have some questions here. So, while making the 4 lobe structure for detecting rotation, how the generation of the 4 lobe is happening? Can you give me more light on this?
So the thing is, you see, the particle is a birefringent particle. It does not mean that the particle, the directors inside of the liquid crystalline material inside the thing is going to be linear. It's actually like ellipsoids in there. So one ellipsoid is here, and you can consider it sort of a multiple ellipsoids. So these ellipsoids can be, so if you put it under the cross polarizers, these ellipsoids do not appear completely dark. There is some sort of a light coming through the sides. So we model it by assuming an ellipsoidal void inside a sphere. In the case of a numerical simulation, we put an ellipsoidal void inside a sort of a sphere. So that sort of gives it the four lobes, and it happens in case of an actual particle as well. So it's basically because the directors are not completely linear. It goes from poles to poles. It's a kind of a bipolar structure. That's the reason.
Thank you. One more question is sorry. Yeah. In pitch rotation, how you are generating the hotspot in the gold surface? Is it by energy from the laser, or I think we
We
told
are
it's by.
illuminating it. So the idea behind that was that we'll illuminate it with a 975 nanometer laser, because it glows in visible if you apply 975. So the idea behind that was to trap it with 975 and see some sort of an interaction between the particle and the gold surface. But what we found was that the 975 was heating up the surface, and then it induced the convection current. So you are actually applying the laser. If you do not apply the laser, nothing happens.
Okay. And from beneath, since the trapping is happening at the focusing point when the surface membrane vibrates, how is it that the same laser point which hasn't moved is still able to keep the particle trapped? Is there a limit to how much
That's a very good
oscillation can be?
question. That's a very good question. Why is it keeping the particle confined to that same location? Sid, I'll tell you, there's also some work from, there's another guy called Yubing Zheng in University of Texas, Austin. He's also showing that if you have a hotspot, the convection currents actually are enough to trap it there. So it's a combination of the optical trapping and sort of convection currents that holds it in that location of space. Okay. So it is a combination of both.
And the follow-up question is there a limit to how much oscillation can be tackled while still keeping the particle trapped?
We have got up to 6 hertz, but I think it can spin faster. Our camera cannot detect faster rotations than 6 hertz. I believe if you make the gold thicker, or if you apply a larger forces, larger powers, you should be able to get it at the edge of that hotspot region, and then it will be sort of moving faster, spinning faster. We have to see. I don't know how fast you can go.
Okay. Thank you, Professor Roy. Let's thank the speaker once again, and moving forward to our next and last speaker.
Thanks for inviting me. Okay, see you. Bye.
Thank you. For the last talk of the session, we have Professor Miguel Alonso to deliver an invited talk. He received his degree of engineering in physics from the University of Autónoma Metropolitana in Mexico City, and a PhD degree in optics from the Institute of Optics, University of Rochester. In 2003, he joined the faculty of the Institute of Optics. He has been associate editor and deputy editor for Optics Express, chair of Spotlight and Optics, associate editor for Optica, and currently serves as an editor-in-chief of Optics Letters. He is a fellow of OSA and currently Optica. Professor Alonso's research is on mathematical aspects of wave propagation, in particular on the description and applications of beam and structure intensity and polarization distributions, optical coherence, and the connection between the ray and wave models of light. With this, I'd like to invite Professor Alonso to deliver his talk, Structuring Light, Tailoring and Measuring Intensity, Phase Coherence, and Polarization. Over to you, Professor.
Okay, thank you very much. Thank you for the very kind invitation. It's an honor to be here. So indeed, I'm with the University of Rochester, but also for the last 3 years, I've been also based actually in Marseille, in France, at Centrale Marseille. I'm working at the Institut Fresnel. I have a dual appointment, so I'm working with both institutions. So today I'm going to talk about structuring light and the structuring the different degrees of freedom of light. What are these degrees of freedom? Of course, we have amplitude and phase, polarization, the temporal profile or the spectrum, and coherence. I will mostly focus on the first two, touch a little bit on the other two, but my emphasis is going to be on the theory, on the geometric understanding of this type of structuring of the beams and some applications. Okay, So let me start with amplitude and phase. And for this, I'm gonna start thinking about something that has been of interest to me for many years, which is the connection between the ray and wave models of light. So when we want to be more correct, we solve wave propagation equations. But for many other purposes, we use geometrical optics, ray optics that give us a lot of intuition. So one might think, well, the ray model is outdated and just a very crude approximation, but I want to try to convince you that sometimes it gives us more intuition than the waves and almost as much information. So what I'm showing here is, just to motivate this, is a focus beam with some aberrations. And one thing that we often hear in classes is that the rays are normal to the wavefront. So I just want to stress that that is not always the case. For example, in this focus beam, I'm showing in pink or in purple the rays, and in green something we call the flux lines. They're the lines of the pointing vector, let's say, and those are the true normal to the wavefronts. And they look a lot like each other away from the focal region, but not at the focal region. In particular, normal to wavefronts cannot cross; they repel each other, while rays do cross. Rays are independent of each other. They don't care about their neighbors, while flux lines do. And it's much easier to trace rays. It turns out that even in this region, it's easy to reconstruct the wave field, although we cannot just say that the intensity is proportional to the density of rays and the phase is perpendicular to them. But there are many subtle mathematical methods for making this connection here. I want to point out here, I think that I'm going to mention a few times, these envelopes of rays are called caustics. Caustic is a word that comes from Greek, means something that is able to burn. Let me give you examples of caustics that you might have seen. So this is, for example, one type of caustic that we see is these envelopes of rays correspond to bright, very visible features of light. About the observation that they can burn, well, there's, of course, if we form a caustic with a magnifier, we can burn a piece of paper. There have been some other unfortunate recent examples. This is a building known as the Walkie-Talkie in London, where an architect thought it was a good idea to put mirrors on the windows and have a concave face of the building facing south. And it turns out that at some times of day, focused light formed caustics that melted plastic pieces of cars. So caustics can indeed burn. Something similar happened in Las Vegas with a building called the Dara Hotel that made the pool region very hot at some times of day because it was focusing the light. So that's just to motivate the concept of caustic. But caustics can explain some of the things, and this is just a very, very simple example of why rays, I think, let us understand some features of light better. So, for example, this is what is known as an airy beam. I'm compressing it here for illustration, so it's propagating in the horizontal direction from left to right. And a property of the airy beam is that its intensity profile is very dark on one side, it has oscillations on the other, has a maximum here. And as it propagates, it keeps exactly its profile, but it bends. It seems to defy the loss of diffraction by traveling not on a straight line, but bending, forming a curve. So one other thing that this seems to do that is a bit mysterious if we just think of the wave equations is that if we block a part of the beam like this, the main maximum here reappears. So if I unblock it and block it, if you look at here, the maximum reappears. And this is something that has been known as self-healing, that the beam somehow has the ability to heal itself. Finally, if these are idealized solutions that take an infinite amount of power. If I do a realistic solution that has a finite numerical aperture, the beam only holds its shape for some distance and then sort of dissolves. Now, all these features, the bending, the self-healing, can be very easily understood in terms of ray optics. If I think of what rays correspond to this beam, I'm drawing them here. All rays are straight lines. They form an envelope, a caustic, very near the main maximum. And what is curved is that caustic, is not the ray. So we shouldn't associate the main intensity with a thing that propagates and bends. It's just an interference pattern that happens to be curved. And of course, if we block part of the beam, we can see that, well, this part of the beam heals because the light is coming from somewhere else. Or similarly, if we only have a finite aperture, it's easy to see why we only get this interference pattern over this triangular region here. It's because only there we have light rays that are propagating and forming the pattern. So that's to give an idea of why caustics and rays can provide more intuition about what light is doing than just looking at the wave equations, which of course are correct. Also, we can use these ideas to inspire designing fields. So for example, there was work on designing analogs of the airy beams that bend non-paraxially for large angles. And people thought, well, the limit must be something like bending by 90 degrees. So I wanted to show that this is not a limit. We can do much more than that by just thinking of this analogy with caustics. And for that, I'm going to borrow a construction from illumination optics from Roland Winston. Imagine that this is a metallic bar, frictionless. I put a ring there and I tie a string there. And then I wrap up the string onto a cylinder here. And this cylinder has the shape of the caustic that I want. Then I put my pencil here and I slide it and I draw a shape. Turns out that this shape is the shape of a mirror that if I illuminate it from above, is going to create a caustic that has the shape that I want. And this caustic is going to be as large as I want it to be. So, sorry, this is backwards, but it's the same drawing. So here you see the rays coming here, forming this caustic that if I make the mirror bigger, it's going to come as close as closing a full circle. And further, if I illuminate this, say with not a continuous wave, but with a pulse laser, I would see something that resembles a wave packet that is moving on the circle. It's going around this circular path. Of course, this also seems to be non-physical, but if you calculate the center of the centroid of the intensity pattern, that would be moving on a straight line. The maximum, again, is not a physical entity; it's just an interference pattern. We can, of course, close the circle. If we go actually to 3D, I can use a generalization of the same construction and design a mirror like this, that when I illuminate it from the front, it will create a fully closed circular caustic. So this is just to give an idea that we can use these ray ideas to tailor light. Another type of beam that has gotten some attention is things like bezel beams. So these are beams that have a cross section like this, that as they propagate, they keep the same cross section. It doesn't bend, but it doesn't quote unquote diffract. Of course, diffraction is acting, but it's balancing out. And we have bezel beams of order 0, 1, 2, etc., and they're discretized. What I'm showing here in red is exactly if I'm thinking of rays to associate with a bezel beam, where the caustic would be. And it turns out that the caustic has a circular cross-section and therefore is a cylinder. So the way to think about bezel beams in terms of rays is the following. This is the caustic that I want. And I need to construct the beam in terms of all the rays that touch this caustic, just touch it tangentially, forming a given angle between the axis and the ray. So I'm going to fix this angle to something, and then I have all the rays that touch the cylinder at different directions or at different values of z. Why are the from the ray point of view, how can we quantize these vessel beams? Because we don't have any arbitrary cylinder. We only have certain cylinders that are allowed. Well, I have to see what happens with the phase. So if I paint the phase along a ray, let's say, and then if I go around the caustic, and the colors are always changing so that the phase of two neighboring rays is the same, or is as consistent as possible. Sorry. Then when I get to the beginning, the phase has to be consistent with what it was at the end, and that gives us this quantization. Now, of course, that is not limited to circular caustics. I can do whatever shape caustic I want and do the same thing, and create a beam that has a different profile, but that has the same straight propagation property. And we recently implemented this with Alessandro Zanotti and Cornelia Denz in Germany and Mark Dennis in England, where Alessandro, I don't know if it was because it's his initials or because it's the first and last letters of the alphabet, he chose AZ and created this profile using this type of theoretical description as a pattern that propagates a long distance without quote unquote diffracting. So by using these ray ideas, it's easy to tailor amplitude and phase so that it does what we do. Okay, let me now switch to polarization. So quick review of polarization and a particular tool that I'm going to use, which is the Poincare sphere. So imagine that light is coming towards you and that we look at the electric field at a given point. If the field is, the beam is monochromatic, we know that the electric field is going to trace an ellipse. And where it is at a given time determines the phase. How big the ellipse is determines the intensity, but the polarization has to do with the shape of this ellipse. And to determine the shape, we need two parameters. One is the orientation of the major axis, which I determine by this angle phi/2. So we can have, I can have something that is horizontal or vertical in orientation, or back to horizontal. And that's why I chose phi/2, because I want this angle, which is periodic, to have a period of 2 pi. And since this and this is the same, phi going from 0 to 2 pi completes the side. On the other hand, the ellipticity, I can characterize by putting this in a box and seeing what the angle here between the major axis and the line to the corner of the box is. And I call this theta/2. So if theta is phi/2, the box is a square, and I have circular polarization, let's say right circular. If theta goes to 0, I have linear. And if theta goes negative, I'm reversing the sense of circulation, and I can go all the way to the other circular polarization. But of course, because phi goes from 0 to 2 pi and is periodic, and theta goes from -π/2 to π/2, I can think of them as latitude and longitude, and assign a coordinate on the surface of the sphere, of a unit sphere, to each polarization. And that's what we call the Poincare sphere. So we can represent any of these polarizations by a point on the surface of this sphere. Now, this allows us also to describe what we call partial polarization. If there's a bit of disorder in the beam, so the ellipse is not always the same, it fluctuates and sometimes reverses direction. On average, this would correspond to the point moving on the surface of the sphere, but if we find the center of that, it's going to be somewhere that is inside of the sphere. So we have a degree of polarization that is the radial coordinate here. So this Poincare sphere definition is very elegant. It illustrates many of the intrinsic properties of polarization, including something that we call geometric phase that I'm going to mention now. So imagine that, for example, you have light with, say, right circular polarization, represented here by this helix, and then it hits a halfway plate. A halfway plate does a reversal of the polarization, so it turns right circular into left circular. And then if I put a second halfway plate, I bring it back to half circular. So I went the Poincare sphere, I started at the North Pole, then I went to the South Pole, and then back to the North Pole. The path in which I go corresponds to rotation around the axis determined by the polarization that is the fast of the axis of the wavelength. So here I put it horizontal, so we go around the S1 axis, so we go like this, and then we can come back the same way. However, if I rotate the second half wave plate, I see that the phase of my final beam, which is represented by this angle here, changes. So the polarization is the same, but the phase changes. And this is what we call the geometric phase. We can induce a phase simply by the history of how polarization evolved. This is one of the simplest cases, and it turns out that this phase corresponds to half the solid angle that we enclosed on the Poincare sphere. In this article, we discuss more general cases where the connection might not be so direct, but there's a nice interpretation as well. In the interest of time, I think I'm gonna skip it. So now let me talk to you about a very simple optical element that we've been using quite a bit in recent years, which is the stress engineer optic, or DSEO as we call it. And this is nothing but a glass window that we subject to pressure on 3 points. So there's internal stress here. It's non-uniform, but you can calculate it, the birefringence it induces, and it changes from point to point. It turns out that at the center, there's an equilibrium point, so there's no birefringence. The retardance, that is how much slower one polarization travels to the other one, grows linearly with the radius, and the orientation of the eigenpolarization rotates with azimuthal angle at a rate of -1/2. So as we go around, the fast axis rotates in the opposite direction and at half the angular speed. And this gives it very interesting properties. One of the first things we notice is that if we illuminate this with a right-hand circular polarization, for example, the central part of this, we create something that we call the full Poincare beam. It's a beam that covers all possible polarizations on its cross-section. So let's say it's right circular at the center, it's left circular in the distance. There's a circle where it is linear with all possible orientations. And inside here, we map the whole northern hemisphere of the Poincare sphere, and here the whole southern hemisphere of the Poincare sphere, according to something called a stereographical map. And this coverage is preserved largely as the beam propagates. If we illuminate a little bit more of this window, we get something that we call, that is called a bottle beam, which can be very dark at the center, but the intensity grows as quickly as possible in all 3 directions. So this stress engineer optic that my colleague Tom Brown and his former student Alexis created as a tool for creating radially polarized light. Quickly, we saw that it could do much more than that, like generate these more interesting beams. But perhaps more interesting for us is not the beams it generates, but the way, how it can be used as a measurement tool. Suppose that I have an imaging system and I want to image a distant object, a point object, with some polarization. If in my imaging system, I put this element, and then I put a right circular or left circular analyzer, the point spread function, the image of this small point that I see, will acquire a shape that actually tells me what the polarization is. So for example, I can put, if it looks like a donut, is one circular polarization. If it looks like a blob, is the opposite circular. If it looks like a croissant with some orientation, is linear. Let me show you with an animation how this works. So this here is the polarization represented by Poincare sphere. And here is the point spread function that I would observe based on the polarization. Even if we have a degree of polarization that is different from 1, I would be able to distinguish this. And this is because this point spread function that I measure is a linear superposition of 4 elementary point spread functions, whose coefficients are something we call the Stokes parameters that fully characterize the polarization of light. one example of a use of this and one application we explored with colleagues here in France, Hervé Rignon and his group, is a multi-core fiber that they use for endoscopy. So they want to make a very, very small endoscope for brain imaging, which is made of a multi-core fiber with about several hundred, well, this one has 475 independent cores. So there's very little crosstalk between the cores. And the idea is that they can inject light, they can modulate the light that they inject on one end, such that at the other end of the fiber, they can build whatever wavefront they want and say, focus the light and excite a nonlinear response, and then measure that. And they can steer the beam by just changing the phase from the entry to the multi-core fiber. However, they did not know what each core did to the polarization. So what we did is something very simple. We just injected light that we vary the polarization, and then we measure we image the output facet with a camera using this technique, using the SEO and a circular analyzer. And what we see is something like this. This is a region of the fiber, and you can see the images of each core having a different shape. And from these shapes, we could reconstruct the polarization, which I'm overlaying here. And as we vary the input polarization, those polarization changes. And we can reconstruct the paths in the Poincare sphere. So with a very few measurements, we can fully characterize each core and find what the eigenpolarizations are, what the phase delay between them is. So we have the full transmission matrix of the fiber. And this type of measurement of the output polarization could be done in real time because it's a single shot technique. We don't need any moving parts for measuring the polarization. So let me move on to non-paraxial polarization, which is something that I'm quite interested these days. And let me start with the fully polarized case. So I have a field with at each point, electric field with 3 components. I no longer can throw away the Z component. I can no longer use the Poincare sphere, which is a shame because it's a beautiful, intuitive representation that illustrates things like the geometric phase. It turns out that there are several generalizations of the Poincare sphere, and I'm going to talk about 3 in the rest of this talk. And the first one, which applies only to fully polarized light, was proposed by John Hannay, based on Ettore Majorana's representation for spin systems. And I find this representation very elegant. Unfortunately, this paper is not very well known. It has received not many citations. I think it's a beautiful piece of work. And let me explain to you how it works. So in 3 dimensions now, the polarization ellipse, that the path that the electric field traces with time is an ellipse, but it has an arbitrary orientation in 3D. Turns out that you can uniquely represent this polarization ellipse not by 1 point, but by 2 points on a unit sphere. And there are many ways to explain this in terms of the focal distances, but the one that I find more intuitive is these 2 points correspond to the 2 points of view from which I can look at this ellipse so that it looks like a right circular right-handed circle. So from here or from here. Oops, almost there. There we go. In other words, I could even measure these 2 points. If I put a small particle, a Rayleigh scatter at the point in question, and I look at the far field radiation, there are going to be 2 directions in which the scattered light is right circularly polarized. So those are the 2 Majorana points. There's some small issues with this representation. And in particular, there's the problem that there's no connection to the geometric phase. So we wanted to correct this, and I like to say that what I wanted to do is start with Majorana. So this is an image of Ettore Majorana. And I wanted to give him some features from Poincaré. So start make him look more and more like Poincaré. So what we did then is propose a variant of that sphere, which also uses 2 points to represent the sphere. These 2 points are also within the plane perpendicular to that of the ellipse and containing the major axis, but they have a different interpretation. Turns out that you have to put this ellipse in a box, and then if you take two copies of this rectangle and read them differently, like this, the 2 corners here correspond to the 2 points. And what that does is that now we can define a 3-dimensional analog of the geometric face, 3-dimensional of the geometric face. And if I consider an evolution of the polarization ellipse in time, for example, the 2 points that describe the polarization ellipse will move. And if the evolution is cyclic, I will come back to the beginning. And the geometric face I accumulated is precisely 1/2 the solid angle that these 2 enclosed. So the property that the Poincaré sphere had is recovered by this reconstruction. Let me show you an interesting aspect. So suppose that you have a strongly focused field, and this is the type of field that they used recently to observe Mobius strips of polarization. So suppose that I look at this loop for this field, and I look at the polarization ellipses, and I just look at the major axis. So this describes a ribbon. At each point, you have a major axis direction. And if I cross something that is called a C point, there's a topological transition happens, and this ribbon suddenly is a Mobius strip. So if I go back and forth, you can see that right here is where the transition happens, and I have a Mobius strip. The representation of these ellipses on the Poincaré sphere, which is the name we gave to that sphere, because it mixes Poincaré and Majorana, there's also a transition. So initially we have all the points here correspond to each one to 2 points. They each close a loop, but when I make the transition to the Mobius case, the 2 loops merge into a single one. So the topology of the path here reflects the topology of the polarization axis. Let me finish with partial polarization and an application of this. So when we have partial polarization, I can no longer talk about EX, Y, and EZ as their own, but the correlations between them. So I need to talk about a 3x3 correlation matrix. And we can generalize the concept of the Stokes parameters and define this as in terms of 9 Stokes parameters rather than 4 Stokes parameters. And since the first Stokes parameter, I used to normalize the others, I can define a vector that is of 8 dimensions. So the generalization of Poincaré sphere for partial 3D polarization is an 8-dimensional hypersphere, which is very, very difficult to visualize. It turns out that it's not a complete hypersphere. There are many constraints on the shape of this space, which is something that I've studied recently. There's an archive draft of an extended review tutorial on 3D polarization. But if you group these elements of this 8-dimensional vector in different subgroups, it's easy to see what regions of space they are constrained. And it turns out that of the whole hypersphere, only about 12%, I believe, if I remember well, is inhabitable. And when you get to the surface, the surface is not of dimension 7, it happens to be of dimension 4. But just to wrap up, let me come and use these ideas in fluorescent microscopy. So this is a collaboration with Sophie Paslet and large extent the reason why I'm working in France now. So what we're doing is using the same window, the SEO, in a fluorescent microscopy of the storm type super resolution setup. So we have a sample with many fluorescent molecules, and because they blink, we form a stack of images, and from the image of each one of them, we can locate its central position much more accurately than the diffraction limit. But what is more interesting is these molecules will not only have an X and Y coordinate, they will have a Z coordinate, and they will have an orientation. They're like dipoles. So they have an orientation in 3D. So we need two angles to determine that orientation. And even more, they wobble, they oscillate. So they oscillate within a cone, and we use the solid angle of that cone as a parameter, and we can also aim to measure this in a single shot image. So what we do is we use this SEO, but rather than using a polarization analyzer, we separate the right and left circular components and image them separately. So we have two images in parallel for each for the scene, and therefore for each molecule. What this does is let me show you here. Oh, unfortunately, oh, here it is. What this does is the following. So these are, for example, for a molecule that is at the nominal image plane and oriented horizontally like this. These are the two images that look like croissants. If I change the orientation of the molecule, my point spread functions are going to co-rotate, so I can detect the orientation of the molecule. But even if the molecule rotates off plane, this gives me a different change in the point spread functions. More interesting, if I defocus the molecule, if I make it go up or down, the two point spread functions counter rotate. So I can tell not only the orientation in 3D, but also the height. And finally, if the molecule wobbles within some angle, that produces other changes in the point spread function. And this point spread function is a linear superposition of an alphabet of 9 essential point spread functions, whose coefficients are those Stokes parameters that I mentioned. So when we can apply this to in the real world, so this is first simulation in the lab, where instead of molecules, we have fluorescent beads that are unpolarized, but we use a polarizer to induce a simulated orientation. You can see the two images, you can see the little croissants here, and we took these images for many possible directions. You can see the changes in the point spread functions, and for many possible different defocus distances. And from this information, we can very simply extract the height, which I'm representing here in color, or the orientation. This works as well with single molecules. And these are our first measurements of single molecules, where we can measure these pairs of point spread functions, match them to theory, and determine the height, the X and Y location, the two angles of orientation in 3D, and the cone of vibration of the molecule by a single shot images. Okay, how am I doing with time? I think I should wrap up. So the last thing that I wanted to talk to you about is coherence, another degree of freedom of light. This is when we look at the correlation of the field, not only for different components, but at different points, at 2 points in the field. So the basic quantity here is the cross-spectral density matrix, and this is a high-dimensional object because it's a 2x2 matrix, but it depends on 4 parameters: x1, y1, x2, y2. So measuring this is very tricky because well, the parameter space that we need to fill is very large. There have been methods that measure coherence at many points simultaneously by doing interferometry, separating 2 copies of the wavefront and changing one of them before putting them together. What we propose is something very simple. So the setup is here, but actually ignore all this. This is how we prepare the partial coherent field. All we did essentially is form an image, do a Fourier transform, but at the plane of measurement, put an object that we can control. So we put a very simple SLM here, and all we did really was put a tiny little obstacle. And it turns out that through some theoretical treatment, if you take a measurement without the obstacle, and then with this tiny obstacle that casts a shadow, and you go to the Fourier plane, you take the two measurements, you combine them, you can recover the coherence matrix for all pairs of points simultaneously that are whose centroid is the centroid of this thing. So by then finally scanning this article, this obstacle, you can recover the four components of the matrix at all spatial points around that point. So with this, I finish. So conclusions: some of the behavior of light fields is more intuitive and easier to grasp by using the ray picture. Form an analysis between their analysis between degrees of freedom. It turns out that the Poincare sphere can also be used to discuss ray structure. I didn't have time to touch on that, and there are extensions of these concepts to 3D polarization. So finally, I thank the collaborators in Rochester, my former students and my current former students also at Institut Fresnel, my colleagues at Fresnel, my colleagues at Rochester, and other collaborators that have worked with me on this, and the funding agencies. So thank you very much.
Thank you, Professor, for such a wonderful talk. We have a lot of questions. From your earlier slides, Binita asked that, is there a fundamental reason behind the repulsion of wavefronts? You talked about how for rays it's possible that, and for wavefronts it is not.
So sorry, it was a bit choppy. So could you repeat the question?
Yeah, from your earlier
I found the question.
slides.
Yes. Is there a fundamental reason behind the repulsion of the wavefronts? Okay. Yes. So the wavefronts themselves do not are not repulsed. What seems to be repulsed is the paths that are normal to them. And I think if you imagine a Gaussian beam, for example, it has the big curved wavefronts away from the focus. So the lines are the normals are going towards it. But as you get to the focal region, the wavefront starts to flatten again. And right at the waist is flat. That means that the normals to the wavefronts, rather than crossing, are going to have to bend and become parallel. So the way it's not that the wavefronts are repulsing, their normals by geometry cannot cross. And therefore, that means that if they're getting closer to each other, at some point they will have to bend. And this creates this illusion of repulsion. One thing that I like to mention is that all this connection between rays and waves in optics has a very close analog in the connection between quantum wave functions and classical trajectories. The math connection is the same. And the analog of these flux lines would be the paths of David Bohm's theory of interpretation for quantum mechanics of where you have a pilot wave and true trajectories that repel each other. So when I use the term repel, I sort of have the Bohmian interpretation in mind. But just to answer the question, it's not a repulsion of the wavefronts. It's the wavefronts must satisfy the wave equation, but their normals cannot cross, because at a given point, a wavefront cannot have two different directions that are perpendicular to it.
Thank you. Another question from her: when forming A and J structures using caustics, did the polarization change?
Very good. So, very good question. For that experiment, it was within the paraxial regime, more or less, and my colleagues in Germany use uniform polarization. So the polarization did not change there. However, if we were to do something more strongly focused, we would have interesting changes of polarization, especially at the letters. And this is an analog of something called the spin-orbit interaction of the degrees of freedom of light. I have done some work with Konstantin Biok on this. turns out that the polarization, if you change the polarization of the light that you're using to form these features, the shape of the features would start to change a little bit, reflecting the polarization.
Thank you. From Professor Gautam Samanta asked, in case of full pointer beam, the beam carries all possible polarization. Now, if we make a full pointer beam, if we can measure the coverage of the polarization, we can section.
Yes, yes.
Now,
Yeah, go ahead.
How we can measure the coverage of the polarization? It is the first question. And the follow-up question is, we can section the sphere and measure the polarization of each section. This process will be highly dependent on the size of the section, and coverage will change for different consideration. Is there any unique way to estimate the polarization coverage of a pointer beam?
Okay, yes. So yeah, very good question. So the full pointer beam at some level is a theoretical construct where you can build it with a superposition of a Laguerre Gaussian beam with one circular polarization and a Gaussian beam with the opposite one. And that will give you full coverage over the complete plane. So you have to go to find the right circle, the left circle, you have to go to infinity. So yeah, it's an idealization. If you take a fixed section of the plane, which you would have in real life, then you would not fully cover the Poincare sphere, you would cover a section. Now, it turns out that what we really measured in the lab using this window does cover the polarization. In fact, it even goes over a little bit because it doesn't write an exact full Poincare beam. It brings infinity closer and it keeps going a little bit. So you can generate beams that cover many times each point on the Poincare sphere. So the theoretical simple formula for the full Poincare beam, indeed, if you measure just a finite region, you would only cover a section of the Poincare sphere. But in real life, you can create beams that look a lot like Poincare beams, but that do cover the whole Poincare sphere in a finite region. Then there was a question of how to measure it.
The last question was, is there any unique way to estimate the polarization?
Yeah. How calculate the coverage of the Poincare beam? Well, how you cover it? There's something called the Skirm number, for example, which is a quantity you can calculate whenever you have a distribution, a field distribution that covers a parameter space. In this case, is the polarization, is the Poincare sphere, but it could be other spaces. So this is a more general concept, and this space is curved. There's something called the Skirm number. There's something you can calculate. You integrate over the region where you're measuring, and it gives you how much you are covering. We didn't do back then. This full Poincare paper is now getting a bit old. Back then, we didn't do that calculation, but I would assume that it would have been something like 90-something%. Or perhaps even more than 100, because as I said, this was not a theoretical full Poincare beam, but something we generated with this stress window. However, so that's how you would calculate it using this Skirm number. But then there's a question about if you think of full Poincare beam as superposition of a vortex and a Gaussian beam with opposite polarizations. If the two polarizations are not circular, for example, if one is horizontal and the other is vertical, you actually have exactly the same thing, except that your coverage would be a stereographical mapping of the Poincare sphere, not from the south, not with respect to the south and the north pole, but with respect to two other points on the Poincare sphere. So you would start at the center, you would have some point in the Poincare sphere, and you would start extending, wrapping around, getting towards another point. So it would be the same thing. The starting point just would be different.
Okay, thank you. Subit has another question. In your first paper of full Poincare beam, you have mentioned that we can make full full Poincare beam by mixing Gaussian beam and vortex beam with orthogonal polarization. In your experiment, you use circular polarization basis. What if we use linear basis for generating FP beam?
Yeah. Yeah. This is. I was touching on a little bit on this on my final answer. It would be if we use these two other polarizations, then yeah, the only thing that would change is what we would also be covering the whole sphere, especially if the two polarizations of the two beams are perpendicular. Then the center of the beam would be one point on the Poincare sphere, not necessarily the North Pole or the South Pole. And then as we walk away from the center of the beam, from the optical axis, we will start walking, covering the Poincare sphere, heading towards the opposite point. Even if the two polarizations for the Gaussian and the Laguerre Gaussian were not orthogonal, we would cover the whole Poincare sphere theoretically. It would be just that the way we walk around the sphere would be non-uniform, but it would start from one point and head towards the other. So the construction is robust in that if you don't get exactly two opposite polarizations, and even if they're not circular, it still covers theoretically the Poincare sphere.
Thank you, Professor. I have a question actually from as you mentioned, Bloch's paper and all the polarization, the generalized Stokes parameters in the nine generalized Stokes parameters. So if you want to mention polarization, or if you want to mention polarization, we need 9 parameters, right? So so then how it is? I mean, polarization is related to spin. So then how you can see the spin as we generally see the right circularly polarized or left circularly polarized as a +1 or -1 spin. Then how you see the spin of a general set, like for evanescent wave there are like transverse spin appears now. So how you can see those?
Yes. So the way that we're gonna do it, I mean, this how do you measure this? Measuring polarization becomes more difficult because you have these well, you have a lot more numbers to measure. So normally standard polarimetry, you use different polarizers and then you use wave plates to return. You cannot do that in non-paraxial polarization. So this is we just got funding for a project to do this, and it's precisely based on the microscopy idea I presented. If instead of having this fluorophores, we have a field and we put a point scatter, a probe at a point, and we measure the image of this point, the image is going to be, and we use our polarization filter, this SEO, to form the image. We're going to get a point spread function, an image of this point that has a funny shape. And that funny shape is a linear superposition of a basis of 9 other shapes that we know. And if we decompose it into that basis, the coefficients will be these 9 Stokes parameters. And that includes the spin ones. So, because this that will change the pattern of radiation from this sample, which at the pupil plane will correspond to a different polarization distribution that we will put appropriate filters there, we can then measure. And the idea with this is that because the point spread functions encode this information, but also keep the point spread function fairly small in size, we can measure simultaneously many points if we put many scatters. So we can do a measurement of many of the polarization, the 9 parameters, at many points at the same time. That's the idea.
Okay, thank you. And one last question. Actually, how did you get the idea that how did you conclude that the 8-dimensional hyperspace has only 4 dimensions and only 4 dimensional?
Yes. Well, so the 8-dimensional space, you would think the radial I mean, it's an 8-dimensional space, so there's still just one radial coordinate, and you would think as you go to 1, well, you get to a 7-dimensional parameter space. But no, it turns out that it's 4. And the easy way to see that is that we know that in the fully polarized case, we can use these Poincarana or Majorana representations that are 4 points on the surface of a sphere, which is 2 points, sorry, on the surface of a sphere, which require 4 parameters. So the size of the space that you need to determine full polarization is only 4. And therefore, you can see that in the limits, you have to be losing dimensions or something, or you get all the funny shape that is inscribed inside of the sphere is such that at the edge, you only have a 4-dimensional manifold.
Okay. Thank you, sir. One more question Subit wants to ask. Subit, you can unmute yourself and ask directly.
Hello, Professor. Thank you for the talk. It was a very nice talk. Actually, we were recently working on a project related to full Poincare beam. So you are the first person who introduced this one. So I'm really excited to see hear from you. So actually, while doing that experiment, so we are planning to map the polarization, available polarization in Poincare sphere. Okay, so while doing that one, we find a difficulty that so how to calculate this one in practical situation. So we have one problem, experimental problem, that our beam have slightly elliptical. The Gaussian beam we used have slightly elliptical since it's coming from a femtosecond laser, and we matched with this Gaussian beam. We are talking about first order Gaussian beam, and we used orthogonal polarization as vertical and horizontal. And then while generating that one, instead of getting any symmetry, it was like getting some points in the Poincare sphere, but there was some lot of missing points are there. So how we calculate that polarization coverage? So that was like we are finding it difficulty. So do you have any comment on that one?
Yes. Okay. So there's an ellipticity of the Gaussian or of the Laguerre Gaussian or both?
Only for Gaussian part.
Okay. So yeah, that's an interesting thing that one could do the calculation of. So if you, I'm not too worried about the fact that one is linear vertical and one horizontal. As I was saying, it's just a matter of changing who you call the North Pole and the South Pole of the sphere. In other words, you could always add a quarter wave plate at the end of your experiment and turn those into right and left circular, and it would be, you would come back to the other scenario. But the ellipticity, I do see that yeah, if you superpose a Gaussian and a Laguerre Gaussian, but the Gaussian is not the same Gaussian as in the Laguerre one, so but it's more elliptic, then it would be it would perturb things a little bit, and maybe your coverage of the Poincare sphere would be wrinkled. There might be some missing bits or others that you might be going over repeatedly or something. That's something that could be calculated. So how can I say this? That if we use two polarizations to generate all possible other polarizations, what you need to do is mix these two with all possible relative sizes between them and all possible relative phases between them. When you have a Gaussian and a Laguerre Gaussian, the real coordinate tells you the relative weight between them. At the center, you only have the Gaussian. At the edges, you only almost have the Laguerre Gaussian. And the relation between them is more or less linear. The phase is the azimuthal coordinate because the Gaussian does not have an azimuthal phase. The Laguerre Gaussian has an azimuthal phase. However, if the Gaussian is a bit elliptic, this separability sort of is perturbed, and now the relative weight is going to be not such a simple function of radius. It's going to be something more complicated. But I would assume that that would be something that could be calculated fairly easily. It would even be nice to like do a grid or a radial chart on the space, and by just using theory of an elliptical Gaussian and a non-elliptic Laguerre Gaussian, see the coverage of the sphere and how that coverage deforms with the ellipticity. But my guess is that you would still be covering most of the sphere. It would just be in a more a non-uniform way. And the other thing that I mentioned before is there's this thing called the Skirm number that you can calculate. That would be a way to estimate how much of the sphere you're covering.
Okay, so I have one more, and time is running. So I have one more doubt. I mean, actually, we were interested in the second harmonic generation of this full Poincare beam. Actually,
Okay.
this full Poincare, it is like you have all the polarization. So while doing the second harmonic generation, its phase matching is coming, and which is polarization dependent. So that kind of thing. So while doing the second harmonic generation, so what happened is that due to the beam quality of this fundamental, the pump beam, the second harmonic generations, this efficiency is varying. So due to that one, we are getting a lot of patches in the second harmonic generation. That if you project here, if you map the polarization to Poincare beam. So in that case, so we are like just confused how we will do that. I mean, we'll claim that it's still a full Poincare beam. So do you have any comment on that?
Yeah, I had not thought about the second harmonic generation thing. Let me just ask you, how do you measure the polarization at the output? Do you use an imaging polarimeter, or how do you estimate the polarization?
I'm just measuring the Stokes parameter by recording for intensities with different orientation that you may know. And then with this for intensity, I'm just doing the matrix suppression and that one. And then I am just normalizing the Stokes parameters. So from that Stokes parameter, I'm taking the orientation angle and ellipticity. And from there, I'm just, for mapping that one, I'm just taking the 3 Stokes parameter, which is normalized, and I'm just putting into a spherical coordinate.
Yeah.
Simple.
Yeah, sure. Yeah, that sounds very reasonable. Yes. So, but when you're not seeing the whole sphere, are you missing patches, or are you missing a whole patch at the end, or?
Actually, as you said, it will start from the vertical that pole, and it will go to the horizontal pole. That coverage will go. So at the horizontal part, there was some patches was there. That is well expected because of the limited beam size and the aperture size of our CCD. But in between, we are getting some random patches. So that we are expecting due to the efficiency difference in due to the beam quality. So. How to calculate that part that we are just confused.
I see. Yeah, I'm sorry, nothing is popping to mind of how to solve that, but yeah, because I think the ellipticity, like the defect on the beam that you mentioned, the ellipticity of one with respect to the other, that could play a role, but I would think that that would be fairly robust. It might just make the coverage not so uniform, but not incomplete. I mean, what could happen is that it's so non-uniform that at your sample distance, it goes very quickly through some patches, and it looks like you're not covering them. But yeah, sorry, I would have to think a bit more about it. But it sounds interesting.
Okay. Okay. Thank you, Professor.
No, thank you.
Thank you, Professor Alonso, for such a nice interactive session and a wonderful talk. Thank you.
No, thank you very much for the invitation again, and I realize I'm the last thing between you and lunch, so I will I will now let you go and have some nice food. Very good.
So with this talk, so with this talk, we conclude this session. I want to thank all the speakers for their time and participation. I thank everyone in the audience for being present here and asking wonderful questions. Now we'll be moving to our lunch, and after lunch break at 2 o'clock, we'll be starting our next session titled Quantum Metrology and Quantum Sensing, chaired by Sandeep and Satyajit Patil. I am requesting everybody to gather again at 2 o'clock IST. Thank you.
देखना अभी आ रहा है तुम्हें, सही दिख रहा है बैकग्राउंड? ओके ओके चलो।
Hello.
Hello.
How's everything going?
Yes, sir.
Good. Okay.
Yeah, just give me a minute. Sir, can you share your slides?
Okay.
Just to, yeah.
Is that okay?
Yeah, yes, sir.
Perfect.
Yeah. Should we start?
Whenever you want, I'm ready.
Yeah, I want to ask panelist.
Okay.
Yes, please start.
Okay then. So hello and welcome to the second session of the day in the Virtual Scope 2021 conference. I'm your session chair Satyajit, and the session is titled as Quantum Metrology and Quantum Sensing. Before we start the second session, there are few reminders. The presenters can share their live screen using the share screen button at the bottom right of the window. I request all the presenters to strictly adhere to the clock. And the second one is the audience can use the Q&A widget to type in your questions, as many of which will be answered at the end of the session. You can use the chat widget to communicate with other attendees and to comment on the presentations. Okay. So on those notes, let's start the second session of the quantum metrology and quantum sensing. So to start this session, first talk in this session is invited talk by Professor Daniel Facio. Currently, he is a professor in the University of Glasgow, Scotland, where he leads the Extreme Light Group and is Director of Research for the School of Physics and Astronomy. His research interests are in the areas of light in flight photography, near zero index optics, photon superfluids, and quantum sensing. Today, he will be delivering his talk on quantum holographic and photonic pair imaging. Now, I would like to invite Professor Daniel Facio to deliver his talk. Thank you, sir.
Thank you, Satyajit. Thank you for that very kind introduction. Thank you for the invitation to come and speak to everyone today. So I'll just start. So Satyajit said, I'm based at the University of Glasgow. I want to just very quickly give an overview of some of the things the group does, because I won't be talking about everything today. So I lead what we call the Extreme Light Group. This was for historical reasons, but the name just stuck. But the group is actually, our research is divided into 3 labs. So in no sort of specific order. The most recent lab actually is the Human Augmentation Lab. So examples of research that we do here involve, for example, trying to do edge computing with the human brain. So using EEG, optical brain reading technology. You can see a picture of myself wearing a recent sort of a new form of optical brain reading technology combined with AI, so trying to sort of augment human capabilities. We're also another example, these are just examples, I don't want to run through everything, but we're also working, for example, on wearable sensors for deaf-blind people. The second lab is the computational imaging lab. Examples here, Satyajit already mentioned, we have sort of a long history in working sort of imaging at 1 trillion frames per second. So that means that the cameras are fast enough to actually freeze light in motion. And we're also working on sensor fusion. Fusing together using artificial neural networks, data from different kinds of cameras for microscopy. And finally, the quantum photonics lab, and I'll be talking a little bit about some of the work that we're doing in this lab today. We have, so examples of research that we're looking at is the role of entanglement, or the generation of entanglement in curved spacetimes, and imaging of quantum entanglement. And it's this last one that I'll actually be talking about specifically today. So the title of my talk is Quantum Holographic and Photon Pair Imaging. The concept of photon pair imaging certainly isn't new. I mean, this is not sort of meant to be a complete overview of the literature, but just some sort of grouping of examples of where people have used photon pairs to obtain better imaging. And examples range, for example, for resolution enhancement in scanning microscopy, photon sparse imaging at 1550 nanometers, but actually imaging at 460 nanometers. So this image on the top right-hand corner here is their images obtained in the blue at 460 nanometers. So this is a sort of a version of ghost imaging, if you want, but the actual illumination of the sample is done at 1550. So for example, that allows you to image with a standard camera, but you can look at wavelengths where silicon, for example, becomes transparent. So these objects were hidden behind slabs of silicon. In the bottom left, classical noise removal, quantum image distillation. There are a few works on this now. There are more papers that have come out recently. I mean, one of these is ours, but the concept here is that you can use if you can distinguish photon pairs or signals that arrive in photon pairs from all other signals. So for example, classical light will not appear in the form of photon pairs, then you can, what I say, distill, but maybe it's easier to understand in terms of using the word classical, sort of noise removal. So you can separate out the quantum cat from a classical cat. The last example here is I call it imaging with undetected photons. It now goes more under the name of coherence-induced imaging. This was first introduced by Zeilinger's group several years ago, and is now actually quite an active area of research. But so why is it that there is so much focus in the quantum imaging community on the use of photon pairs? So the answer actually is relatively trivial, and it all comes down to sort of the technology, the techniques that are used for actually generating the photons in the first place. So what I'm showing you here in the top left-hand corner is sort of a very sort of simplified version of a typical setup, where you'll have, for example, a blue laser that pumps this NLC, that's a nonlinear crystal, can be BBO, KTP, or whatever. And what will happen is that the blue photons will split into a pair of what we call parametric down conversion photons, but into photons that have roughly half the energy of the blue photon. So you'll have a blue photon split off into a pair of red photons, but it was always in pairs. So, and then you'll be using, what we're doing is now using cameras, and these are becoming more and more ubiquitous, and that when quantum cameras or single photon sensitive cameras weren't available, you'd be doing these measurements just with single pixel detectors, for example, PMTs. And if you wanted to build an image, then you'd have to scan the single pixel PMT across the scene. Instead, now we have access to these cameras. I'm showing you just two examples. There are other quantum cameras around, but the most widely used at the moment is the EMCCD, the electron multiplied CCD camera. These now can come even in sort of in megapixel versions. We've been using quite a lot these SPAD cameras, So SPAD stands for single photon avalanche diode cameras. So these are based upon the same technology, single pixel technology, that has been used for many, many years in most labs around the world, but these are available now in cameras. Most of these cameras have very low pixel counts, of order 32 by 32 pixels, but there has been recent progress in making even megapixel versions now of these SPAD cameras, which is quite remarkable because each of these pixels has on it the full time correlated single photon counting electronics that is required to actually distinguish when two photons arrive at the same time. So in order to know that they arrive at the same time, you need to be able to time when photon 1 and photon 2 arrive on the sensor, and you need to do that with sufficient precision that you can be certain that they arrived at the same time and not at different times. And all of that electronics is already contained in these SPAD cameras, whereas the EMCCD does not have that capability. It's a standard camera where you just open the camera and you just collect the photons as they hit the camera. So you have to play other tricks in order to determine whether there are photon pairs or not. So what I'm showing you here in the bottom graphs is so two examples. Well, the same sort of PDC parametric down conversion generated by nonlinear crystal, which appears in a ring due to phase matching considerations. But the top row shows imaging the case of the EMCCD camera, and the bottom image is what you see, same experiment, but with a SPAD camera. And basically, because of the phase matching constraints, you will always have correlations, actually quantum correlations, in position. If you look in the near field, the photon pairs, because they're generated from a single blue photon, will always appear in the same place. In the far field, so when you propagate away, they will be anti-correlated. Okay, so if one goes off to the right, the other one goes off to the left. So for example, if I choose this white square here in the PDC and go and look for where, every time I choose this pixel, where do I see the other photons appearing? You'll see this bright spot in the anti-correlated position. If I choose another pixel of this white square here, then I will see the photons appearing at this other anti-correlated position, and so on. Okay, and you can do exactly the same thing also with the SPAD camera. You can see, because it's only 32 by 32 pixels, you can see it's a lot lower resolution, but you might also, spatial resolution, but you might also notice though, that now you have very good or much better signal to noise ratio. So this is already starting to see one of the advantages of using a SPAD camera versus an EMCCD camera. Now, how do you actually go about pulling out images from photon pairs? I don't want to say there is only one way, but the approach we are using is based on this technique introduced by Hugo de Fienne, who is currently in our group, back in 2018. And basically, and if you had the perfect camera without any noise whatsoever, you should be able to look within the same frame and do exactly the exercise that I showed you in the previous slide, where I take one pixel and then I go and look across all the other pixels. And in the absence of any noise, I will always find the corresponding photon in the anti-correlated position. Okay, this is in the absence of noise and in the absence of losses and in the presence of a detector that has 100% detection efficiency. Now, all these things, of course, are impossible. And what noise, detection efficiency, and losses create is, what they do is, instead of always having photon pairs actually detected on the sensor, you'll very often lose one of the two photons. Or noise will add what looks like a photon count. So you'll have lots of what we call singles dispersed across your sensor. These, we'll call these accidental counts. They do not correspond, or you cannot correlate them directly to a photon pair. You need to get rid of them if you want to pull out an image that only collects photon pairs. And so what this formula here is showing, this sort of intensity correlation function, the first term is what I was describing earlier on. It's the correlations within the same frame. So I fix a pixel and I go and look for correlated counts across all the other pixels. But what you then do is I'm subtracting out the correlations across different frames. So if for every pixel on frame 1, I then go and look at all the other frames and I start finding correlations there, you can be certain that these are accidentals. They're either due to noise, imperfections of the system, losses, quantum efficiency, and so on. So if you repeat this operation and average over a sufficiently large number of frames, you will get a very good and precise statistical representation of what the photon pairs are and what the accidentals are. And so when you subtract these two out, in the limit of infinite frames, you will have an exact representation of the correlated photon pair counts. Okay, so bear that in mind. So and bear in mind this is sort of the weak point of this, if you want. It becomes sort of true in the limit of infinite frames over which you perform this operation. So you need to do this operation over many frames, and I'll quantify that in sort of the next slides and show you examples. Okay, so in practical terms, this is what we're doing. So you're measuring. Let's just not worry too much about imaging right now. But let's just look, for example, at just the PDC ring and just look for the spatial entanglement that I described earlier on. So I measure the PDC and I look for correlations within the same frame, and then I subtract out the correlations across different frames. And essentially you will, and if there are no correlations, you'll just get noise. But well, you can't really see it too well in this image here, but when there is a correlation, it will appear as a bright spot in your image, which is what I was showing you earlier on. And this is the basic underlying technique, for example, for classical noise cancellation that I was describing in my very first slide. So here you see in the top left image, there's a superposition of two cats. One of these cats was obtained by illuminating a cutout cardboard, sort of basically cat shape, but it was illuminated with quantum illumination with photon pairs. And then we're superimposing, using a beam splitter, superimposing another cat that was obtained by illuminating a similar cardboard cutout, but using a classical LED source. And then by using this technique, you can pull out, just by distilling the photon pairs, you can pull out the quantum cat, which is the central image. And then by subtracting, doing the middle figure, so A minus B, you'll be left with a classical cat. Note that in the right-hand image, you can see the outline of the quantum cat. And that is because at the edge of the quantum cat, you will have some photons that will have some photon pairs that fall right at the edge. So the photon that's inside the cat will be seen as classical light, and the photon that falls out, the photon that falls outside the cat, gets absorbed. So that means that the photon pair appears as a single photon that lies right at the edge of the cat. So even if there were photon pairs, because of the loss of one of the two photons, that single photon is distilled, is pulled out as if it were classical light. And that's why you see if you want, you see the fur of the cat that remains in the classical image. Okay. So comparing now, going back to this concept of the fact that you need, in order to do this, you need lots of frames. And let's quantify that a little bit. It turns out that in order to get a good signal to noise ratio, you need to do this operation of subtracting the accidentals from successive frames over of order anywhere between 20 to 100 or even more than 100 million frames. Okay, so if you're looking at using an EMCCD camera that has maybe a 10-100 hertz frame rate, that means that a measurement can take you basically up to a day. Now, if we go and look at the SPAD arrays, although these have much lower pixel resolution, they can run at nearly 1 megaframes per second. Okay, so if I want to collect 1 million frames, that essentially means that in principle, I could do that measurement in a second. Now, most of the cameras we've been using actually run at around 100 kilohertz frame rates. And so our measurement times are typically order of minutes. But you can see a way forward here where in the near future, I think we will probably be able to do quantum imaging at video frame rates, which I think is quite exciting. So what I'm showing you here on the bottom graphs is an example where we certified the EPR entanglement. So this entanglement, the spatial entanglement between position in the near field and anti-correlations in the far field. Okay, so you know that delta R times delta K should be greater or equal to 1/2. And so essentially what EPR entanglement tells you is that if you separately measure the delta R in the position of the photons in the near field and the delta K in the anti-correlation in the far field, and you multiply these two together, actually you can violate that inequality. Okay, and what we're seeing here in the right-hand graph is that we really start to strongly violate this inequality as the frames become of order sort of around 1 million frames, as I was explaining earlier on. Okay, so now that we've understood this, what we then moved on to do was use this technique to do quantum state tomography using a camera. In particular, now what we're looking at is not only spatial entanglement, but also polarization entanglement. So for this reason, we talk about hyperentanglement in the photon pair. You're entangled in space, but now also in polarization. We take the two photons from the parametric down conversion source, and we send each one onto a different SLM. So we can have Alice's SLM and Bob's SLM. The SLMs, these are spatial light modulators, liquid crystal spatial light modulators. And what they do is they change the phase of the horizontal polarization component compared to the phase of the vertical polarization component. And we have these 45-degree polarizers after the two SLMs, and then we image on two different EMCCD. So we've got Bob's EMCCD and Alice's EMCCD. And we can do the usual trick that I explained earlier on. Forget polarization for a second. We can, for every photon that appears at the position corresponding to a wave vector K on Bob's EMCCD, we can look for correlations and find that this will correspond to a photon, the other photon of the pair, at position minus K on Alice's EMCCD. But now what we're going to do is we're going to encode images using Alice's SLM or phases, we'll come to images later on, by using this, what I call this entanglement phase that sits in the middle. So in the bottom left here, I'm explicitly writing out the entangled polarization state that we have. So it's VV plus e to the I psi HH. This psi, this entanglement phase, is the phase that you want to measure when, for example, you're doing quantum state tomography or doing measuring a Bell inequality to demonstrate that you have polarization entanglement. Okay, and so what we're doing with Alice's SLM is controlling this phase term here. So what you can do then is you can simply, this is very similar, it's just a generalization to the imaging case of doing quantum state tomography, but on a camera. So I'm going to set various settings on Bob's SLM, so 0, half pi, 3 pi over 2, 5 pi over 2, and then I'm going to work with an orthogonal sort of phase settings on Alice's SLM, so pi over 4, 3 pi over 4, and so on. And for each of these settings, I am going to do these anti-correlation, correlation measurements, but looking at the anti-correlations in the K-vector space for, across, you've got Bob's SLM and Alice's SLM. This is why you have, for each setting you have two images, okay? So this is nothing other than what you would do even if you had single pixels, so single pixel detectors, but now we're resolving the full PDC cone across the whole camera plane. So once you've got all of these images, you can pixel by pixel just apply the standard sort of Bell inequality calculations and obtain for each pixel individually a spatially resolved CHSH Bell parameter evaluation Bell parameter S. So whenever S is greater than 2, you have entanglement. And here we have an average value of 2.2 across the whole sensor, but here you can actually see sort of the spatially resolved evaluation of this S Bell parameter. Okay, so the next step then is to actually move on and do some imaging. So what we're doing is exactly as before, but now instead of imprinting just flat phases on the two SLMs, Bob will keep a flat phase. We'll need that in a moment. I'll show you why for decoding the image. But on Alice's SLM, we will put a phase image, for example, this smiley face, okay, which is shown in more detail here on the right-hand side. So we're including this smiley face again into this entanglement phase, e to the psi k. And then what you do is, in order to, so if I just look at the sort of the intensity on Alice's CCD, I will just see uniform illumination. There won't be anything interesting there. And likewise on Bob's image, it'll just be uniform intensity. But if Bob now applies 4 different phase shifts, as you would do even in classical holography, and then for each of these looks for the photon correlations across the two cameras, which I'm showing in the bottom graphs here, you can then use these images to apply this formula, which I'm showing you in the top right here, which is just the standard formula for inline holography in the classical case. You can then reconstruct the full phase image that I'm showing on the right-hand side. But the phase here is this is very different from standard classical holography. In standard inline classical holography, in order to do this, you would need to, first of all, use a coherent beam. You'd need to illuminate your object with a coherent beam. You'd need to split off part of that beam before the object, and then you re-interfere the beam that's gone through the object with the reference beam that you split off earlier on, and interfere these on the same camera. And then from the interference patterns that you measure as you change the phase on the reference beam, you'll be able to pull out an image. But in this case, we have encoded the phase not directly in the spatial phase of a beam, but in the entanglement phase. And these two photons are, in general, they're incoherent. So this is a form of incoherent holography. And most importantly, they have been detected, because this is G2, not G1 imaging, these can be detected, or have been detected in this case, on 2 completely different cameras. The 2 photons are never actually brought back into contact with each other, okay? So, and in order to prove that this is really due to entanglement, it's got nothing to do with the phase of individual photons, but it's the entanglement phase of the photon pair state. You can remove the entanglement at the source, and then when you try to do the same trick, so now using U of G as sort of letters that are where we've encoded the phase, again, single photon, so these 2 graphs in the middle show it's just the single photon images on the 2 cameras, there's nothing. But even when I start changing the phase on Bob's SLM and looking for the G2, the photon pair correlations, and as you can see in the bottom, you still see nothing. So then when I try to reconstruct the phase image in the top right-hand corner, there's nothing to be seen. I just cannot reconstruct the image if I do not use, or if I lose the polarization entanglement state. And so generalizing from what I was showing you earlier on with the cats, you can now, one of the advantages of this technique is that I can now add some classical noise. I'm showing you in the bottom here. So the classical noise was just added by using a laser and some time varying speckle, and you can see that actually it's still working fine, precisely because when I'm looking at photon pairs and only photon pairs, I'm rejecting all the classical noise that doesn't appear in the form of pairs. The other interesting thing is that I can put directly on the two photons, I can put two dynamically moving scatterers. So now I'm completely sort of scattering even the quantum photons that are passing through the system. And that still doesn't perturb the imaging capability, because remember, so what the scattering does is it changes wave vector direction, but it doesn't change, at least in this case for weak scattering, it doesn't change the polarization state. So if you want, the polarization entanglement is sort of as a decoherent free subspace. So I'm introducing incoherence on the K vectors, and that would normally completely ruin any form of classical holography. But in the quantum case, where I'm measuring the phase in the entanglement degree of freedom, in the polarization entanglement degree of freedom, polarization isn't modified by the scattering, and therefore the image is still correctly encoded and decoded by the system. Okay, so I wanted to, I'll try and wrap up sort of in the next 5 minutes. I'll leave time for some questions if there are any, but I wanted to show you something else that we're working on at the moment. This is still G2, so it's still photon pair imaging, but now what we're trying to do is image through a Hongel-Mandel interferometer. So Hongel-Mandel interference refers to the fact that if I take two indistinguishable photons and overlap them at a 50-50 beam splitter, at the output, these two photons will always emerge at the same port, so in pairs. So they will either go, in this image here, they will either emerge to the right or to the top, but they will always be in pairs. They will never separate out in different directions. They will always come out in the same direction. So in other words, if I put detectors at the two outputs that are able to detect photon pairs, I should see, when looking, for example, if I look at the coincidence probability, in the classical case, or when the two photons are out of delay, so they're not arriving at the same time in the beam splitter, I'll see a 50-50 chance of the photons going opposite directions compared to coming out in the same direction. This is just what will happen classically. But as I change the delay in the interferometer so the two photons arrive at exactly the same time, these photons will always appear as photon pairs. They will bunch together. So if I'm looking for coincidences between the two output ports, these coincidences will drop to zero. There will no be instances in which the two photons come out opposite sides. So now with our imaging technology, so I've shown you that we're able to very carefully reproduce when we have photon pairs, and that we can do this across the pixels of a camera. So we have an instrument now where we should be able to do imaging through a Hongel-Mandel interferometer. So here I'm showing you a simple example where I've got sort of like a stepped phase plate. So the red photons that go through the thicker sample, the thicker part of the sample, will have a Hongel-Mandel interference step, which will be shifted further to the right compared to these blue photons. They're not really blue, I'm just indicating them with a color blue to say that they're in a different position. These blue photons that have gone through the thin part of the sample, the dip will be shifted further to the left. So by looking at how this dip shifts across at each pixel, I should be able to pull out an image of, for example, in this case, this simple stepped sample. What we actually do is we don't scan the whole interferometer trying to measure the full dip. Instead, what we do is we fix the position where this dashed line is, for example. So we fix the relative delay, and then all we have to do is look for variations in the photon counts. So you see that the green, if I just look at this position here and just count the number of photon pairs that I see, the different thicknesses of the sample will lead to different counts at this point. Okay, so by directly imaging to the amount of bunched photon pairs that I have on my camera, it becomes a bit like intensity imaging now, but it's photon pair intensity imaging of the sample. So this is very briefly, this is the setup. You've got a laser, your BBO crystal, where you generate the parametric down conversion. This gets split in two. Half of the parametric down conversion goes down the bottom here, and through this beam split at the end is where then the two photons are made to overlap. The top photon passes through the object, which is placed in this plane P1. And then these planes P1 and the similar plane P2 are just imaged directly onto the two halves of the SPAD camera. And so if I just look at the intensity image, you only see the two halves, just showing one half here, sorry, of the image where I'm just looking for bunching. If I just look at the intensity image, there's nothing. If I look for sort of the correlations, so I'm looking to see if there are coincidence counts across the two halves of the camera, I start to see something here. So there is something in the sort of the anti-coalescence or the coincidence counts, and likewise for the photon pairs. But unfortunately, what happened here, so now remember, we only have 32 by 32 pixels. The resolution actually wasn't quite enough in order for us to image. So here we had the letters U of G imprinted onto a glass slide. So what we did was a raster scan of the camera. So we standard sort of raster scanning super resolution technique. And now you can very clearly see that we can see the letters U of G emerging from the coincidence counter from the G2 image. Okay, so I did have other slides, but I think I should stop here. So I'll skip straight to the end, to my last slide. So summarizing this method of using coincidence or joint probability distribution imaging is we're finding it's a very powerful quantum imaging technique. It does require many, many frames at the moment, up to 100 million frames per image. But the SPAD cameras are really allowing us to now move towards real-time imaging or quantum video cameras. And there's a whole range of applications. I spoke about high-dimensional entanglement certification, quantum holography, Hongo-Mandel imaging. But I think there's room also to apply this, for example, to bioimaging and microscopy in the future. So thank you very much, and I'll be happy to answer any questions. I just wanted to add that unfortunately I might need to leave early on during the session, but if you do have any questions and I'm not around, I've got my email down the bottom here. I mean, feel free to write to me anytime you want. I'll be happy to answer any questions you might have. Thank you.
Yeah, thank you. Thank you very much, Professor Facio. So there is one question by Sandeep, who is asking, what is the in-depth resolution you have achieved using fixed sample in HOM?
Yeah, that's a very good question. So in the images that I showed you just a minute ago, the U of G sort of letters were etched into a glass slide, and they had a depth of 8 microns. And we were able to correctly reproduce that depth with a precision of about 0.5 micron. So that was the sort of, because you saw there was noise across the image. So we had a resolution of about half a micron there. And we've looked also at other objects. So we've got a paper on the archive at the moment. So we also had objects which, instead of being etched in, were sort of just some acrylic that we sprayed on. And there too, we were able to sort of measure the height. There was about 12 microns with a precision of about 1 micron. So this is in the sense it's good news, because when Hongo-Mandel published their first paper proposing this as a technique for sensing, they too had a resolution of order of a micron. And typically when you and this was all single pixel, it wasn't imaging. And indeed, if you look at most other papers, the typical resolution is of order 1 micron. However, we have shown in our group that you can do much, much better than that if you accumulate sufficient data. So what people normally do is they scan the interferometer, look for the dip, and then look for how the minimum in the dip is shifting around. But actually, that's not the best approach. The best approach, because that 0 point actually is so the minimum of that curve, is the place where actually you have minimal fissure information in your measurement. The highest fissure information in your measurement is what I was showing you when you're measuring when you go to the edge of the dip, because a small change, because you have a high gradient in the signal, so a small shift of that dip will give you a very large change in the number of counts. And we've shown that if you use that approach properly, you can, at least with single pixels, we haven't shown it with cameras, but with single pixels sensing and longer acquisition times, you can get at a second resolution, meaning, so we were able to measure differences in sample thicknesses or thickness of order of 5 nanometers. So it can be made extremely precise. And where currently we sort of routinely now are getting at least 50 to 100 nanometer resolution in our measurements.
Okay, regarding to Fisher information, there is one question. Can we apply Fisher information technique in the imaging with EMCCD to go beyond the standard resolution limit?
Yeah, I mean, basically just expanding a little bit what I was saying earlier on. I mean, that's kind of the direction which we're trying to go right now. The technique requires precisely what I was saying, going to the edge of the dip and fixing the point of maximum fissure information and measuring there. And that's what we're doing here. Our resolution is still relatively low because this is sort of the first attempt, and we just need to be able to go faster and get faster, so essentially get faster cameras so that we can pull down the acquisition time and therefore, if you want, within the same time, get a lot more data. And then I'm fairly confident that we will, by using this Fisher information technique, we should be able to, I think maybe expecting to get 5-10 nanometer resolution might be hard, but I see no reason why we shouldn't be able to get 100 nanometer resolution measurements.
Okay, thank you. One more question is there by Abhinandan. He's saying it is a nice talk. The holography scheme requires polarization entanglement. So does entanglement bring any security in the holography protocol?
Yes, in principle, it should do. We should be able to use similar techniques to what are used in quantum key distribution, for example, and apply that also to imaging. That's not something that we have done, but I think it would be an interesting direction of research, trying to, instead of doing quantum key distribution or sort of quantum secure communications down a single mode fiber, but actually encode your data in the form of images. And I know there are some groups that are also working on this idea. Yeah.
Okay. So there are more 2 questions.
Mm-hmm.
So Pranav is asking, can the coincidence imaging method be extended to molecular system emitting electrons or ions to check if the electrons or ions are correlated? I think.
Yes, it can. And I'm pretty certain, I think it's the same thing you're suggesting. But I mean, there are papers where people have, actually, I think maybe my very first slide, Dan Oren's Nature Photonics paper, I was showing the top left image. I think he was looking precisely at emission from fluorophores. But yes, you can use G2 imaging to look at the, let's just say in general, looking at the statistics of the emission of even single molecules. Absolutely, yes.
Okay, so I have one personal question, like in the HOM G2 correlation, okay, what is the meaning of coincidence probability on the y-axis?
Can you repeat the first part of your question? Sorry.
In HOM holography, HOM G2 correlations, on the y-axis, what is that coincidence probability? Is it a joint intensity distribution?
Yes, and what you're asking yourself is that you've got this beam splitter and you're sending in photons, one photon from one input port and one from the other, and then you're looking at the 2 outputs. And so a coincidence here would mean, so I've got 2 detectors at the 2 output ports. So a coincidence means I see a click here and a click here. So it means that the two photons have gone in opposite directions.
Okay, but it is achieved using EMCC, right?
Yes. So what you do is you make sure you either use two cameras, or what we're doing is we're just redirecting the two output ports so they hit the camera, but in two different halves.
Okay.
Okay. And so then you're just checking. So you have Hongo-Mandel interference or G2 interference when the coincidences disappear. So I don't see a photon at one output and another photon at the other output, but both photons appear always at the same output. Yeah, does that make sense?
Yes.
Mm-hmm.
Okay, there are, okay, for further questions, you can talk to the speaker.
Yeah, I think there was a question about how we did the super resolution in the coincidence case. So basically, it's very simple. What we did was you fix the camera position, you do your measurement and pull out the G2 image. Then you shift the camera by half a pixel, repeat, and you get a second image. And then you shift down, you get a third image, you shift back, and you get a fourth image. So we only did a 2x2 scan, but you get 4 images. And then we just did a very simple, what is called shift and add. So you just interlace the 4 images together, and you get the super resolved image. So it's a very, very simple approach and technique. There was nothing quantum there in a sense. You just have 4 images, which you know are each shifted by half a pixel, so you can put them back together again.
Okay, there are no further questions. We can thanks to the speaker once again.
Okay, thank you very much.
Thank you. Next, we have an invited talk by Professor Robert Fickler. Currently, he is a professor in Tampere University, Finland, where he leads the experimental quantum optics group. His research interests are in the area of exploring complex structure of light, high-dimensional quantum photonics, light-matter interaction on the quantum level. Today, he will be delivering his talk on 2-photon interferences in special modes and ring core fibers. I would like to invite Professor Fickler to deliver his talk.
Okay, hello, can you hear me?
Yes.
Yeah, hello. Thanks for the introduction. Let's try to share my slides.
Yeah, they are visible.
And I think now you should see the proper slide, not this presentation mode.
Yes.
Okay, very good, very good. Hello, everyone. Thank you first of all, of course, for giving me the opportunity here to give this presentation, to present essentially 2 or a bit more than 2 of our recent results. And I'm very happy. I think it's a really nice conference. Unfortunately, due to the time shift, I'm not able to join the very early talks. And I have this week a lot of other things to do, but I really enjoy the sessions I'm able to join. And looking forward to the rest of this session and then tomorrow's session as well. So today I will talk about 2-photon interferences that we observed in a slightly different manner than it's usually done, meaning in path. And we've heard this beautiful talk now by Daniele Faccio about 2-photon interferences using the path, degree of freedom. And we use it essentially, we observe it in spatial modes, so along a single path, but different spatial modes. And then a very recent result where we then essentially had a ring core fiber and observed their 2-photon interferences using what is called the so-called Talbot effect. But let's get back to that later. So as was said in the introduction, our group here in Tampere University in the north of Europe, we are working on mostly, I would say, experimental quantum optics parts. So meaning that we have a few experiments going on where we investigate light-matter interactions towards the quantum domain, either for photon pair generation or for quantum plasmonics experiments. We have a classical part, essentially, of experiments that are going on. And there we investigate what can be achieved when we increase the complexity of the light field. And then we have a quantum photonics part. I would say that's the biggest part of the group, and I will just talk about two of these experiments. But coming back to the classical part, I don't have time to go into the details, but I just want to highlight a few, two of our recent results that might be of interest. So we've, in one experiment, we generated spiraling light fields, so light fields that do this essentially along the propagation over a certain distance. And we use this spiraling to measure the longitudinal distance. And I think it's quite nice to see that a single beam, and you just put a quadrant detector there, you can actually achieve quite high accuracy. So 2 micron resolution in the longitudinal direction over 2 millimeter. So in case you're interested, I invite you to look at this paper. So this is just a spatial structure that we use to perform some special measurement tasks, longitudinal measurements essentially here, or distance measurements. And then we also investigated if we now don't look into the spatial domain, but try to adapt techniques that we know from the spatial domain to others, for example, the spectral domain. So in one experiment, we generated essentially a complex polarization structure across the frequency spectrum of a pulse. And because of the strong correlation between polarization and the frequency, we could use such beams, we termed them spectral vector beams, to perform a spectroscopy measurement. And this, because you only have to do polarization measurements to gain information about the spectrum as well, you can do very fast. Okay, so in case you're interested, you can look at this recent publication. But let's go back to the main two topics of my talk. So one is about the spatial modes of light or spatial structures of light, and I will introduce it a little bit and then go into the details how we observe the two photon interferences and what they are good for when using spatial modes. In the second part, then I will introduce the cylindrical Talbot effect or self-imaging in cylindrical geometries, in our case in ring core fibers, and then at the very end, briefly mention our very recent result of two photon interference in such ring core geometries. Okay, let's start. We have to check the time a little bit. Okay, so as I said, we use spatial structures of light. So light can be, in the transverse domain, can have very complex structures, and maybe a few of you are familiar with this kind of mode types, which is the Laguerre-Gauss mode family, which is the solution in cylindrical coordinate system to a parallaxal wave equation. And there you see you have the zeroth order is the Gaussian mode. That is true for all mode families. And then higher orders have specific structures. For the Laguerre-Gauss case, essentially you have two variables, 2 degrees of freedom if you want, 2 quantum numbers. So one describes the azimuthal phase essentially distribution, and the other one the radial distribution. Okay, so these modes, especially these ones with this azimuthal phase distribution, have become very popular because this phase distribution corresponds to an optical angular momentum or an orbital angular momentum, and they are called then often OEM beams or donut beams because of the intensity. So here the intensity is the brightness, and the color, I should say, is the phase distribution. So there is this OEM, orbital angular momentum degree of freedom, and there's also this radial degree of freedom. So as soon as you have the second quantum number, this p number, if this is not zero, you have additional rings. Just for completeness, this is in cylindrical coordinates. They're very nicely matching our optics, so that's why a lot of people are using that, including ourselves. You could also use for similar tasks Hamid-Gauss modes, they have their own special feature, or then a more general mode family, Ince-Gauss modes, that are then solutions in elliptical coordinates. Okay, but we will focus on in the spatial mode part on this type of modes. And in the quantum domain, these modes are very nice because they are all orthogonal. They form a set of orthogonal states, and we can use them to encode quantum information. So we can use two modes to encode a qubit, but we can also encode higher dimensional states. That's what we are partly working on in our group as well. So what is this good for? What are these structured photons, these spatial modes of light in the quantum domain? What are they used for? So there is experiments where people, including ourselves, investigate entanglement, and they are not just two-dimensional entanglement as it is for polarization, but high-dimensional entanglement, where both photons can be in more than just two states and be entangled in the states, correlated. This is interesting for entanglement distribution, for quantum communication purposes, for example, but you can also use just the spatial modes or spatial structures to encode more information, thereby you're a bit more noise resistance. So they have advantages in quantum photonics in terms of communication. You can use them for investigating fundamental tasks or for simulation and computation. So people have used that, and a little bit I will touch this quantum computation a little bit in the later part of the talk. So they're very, like, the field essentially got established with the start. I think the quantum part got established essentially around beginning of 2000, where it was first presented that photons can be entangled in this degree of freedom. Yeah, since then it has exploded, and many people are working on that, and it's a very nice area to work on and be part of. Okay, so our task at one point, we realized, well, if you want to do certain things, for example, simulation and computation, you need to be able to do mode transformations. And there was not really a technique, very few, very limited techniques were around. So we looked into that. And then we figured out that actually in the beginning of 2000, there was, I don't know, I hope it's still working because my computer does weird things. Okay, so let's think about a simple mode transformation. Let's say you want to realize that, which in quantum language, this is a Hadamard gate. I have to briefly check if. Can someone give me feedback if it's still working, because my computer does very weird things? If you still hear me?
It is working, sir.
Okay, good. Okay,
Yes.
sorry. Okay, let's continue. So let's say we want to do a certain mode transformation, which is then quantum information language is called a Hadamard gate, meaning that if we send in a certain mode, in this case +1, we want to get out a superposition of this mode and the other mode that we could also send in, a -1. Okay, so the superposition would look in the spatial mode domain like this. If we send in then the other mode, the -1, the plus and -1 corresponds to the orbital angular momentum. If we send in the second mode, we then get a superposition with a different phase. So this is essentially this Hadamard operation. There's no simple device actually for this. There would be lenses, but we want to keep it general. So is there a device, or we asked ourselves, is there a device or a way that how we can do that? And then we came across this paper in 2010. Actually, we came across that much later when it was described how you actually do that then. But these people figured out that if you use multiple planes, in this case 3, and you modulate only the phase of the light, you can actually do such mode transformations. Okay, so how does it work? This is described then, and we took up on that in this paper in Nature Communications a couple of years ago. So you used what is called wavefront matching. I will not go into the mathematical details, but essentially it is you take your input mode or the set of input modes, and then you, in the computer, in the simulation, you propagate it through your system. And at any given plane that you allow yourself, here it's the 3 planes, here you allow a phase modulation. And to determine this phase modulation that you want, you just compare the input and the output modes, and then try to match the wavefronts by just modulating the phase. You propagate and so on. And if you do that following this formula, it's relatively simple. Modulations, and if you send in this state of light and you propagate it through, it's quite nice to see that it's slowly, this propagation is required to also modulate the amplitude of light, the intensity structure. Okay, so this technique of having multiple planes and you only modulate the phase of the light, in between it allows you also to modulate the amplitude. So in principle, this is essentially a complete unitary slow kind of transformation. And surprisingly, it works with a limited number of phase modulation planes. So as I said, it's for multiple modes. It's a unitary mode conversion or a unitary operation that is actually required in quantum operation tasks. Since we have more modes, and I said we want to use high-dimensional states, this works also for more than 2 modes. In this case, that would be the example for 3 modes. And in our simulation, then we saw That works with near perfect visibility, so there's nearly no crosstalk, and very high efficiencies, already with only using 3 planes. So of course, then we set out to do that in the lab, and we started by just using a laser and then single photons to see how good we can actually implement it in the lab. And without going into the details now, we did many of these operations that are like fundamental operations, fundamental gates in quantum computation for OEM modes, for these radial modes, and using both degrees of freedom, we even did a controlled operation on single photons, and it worked quite nice. So in case you're interested, you might want to look into this publication. And in case you still does not have, you're still more interested in quantum operation and quantum gates, because we were at that time, we developed then based on other ideas as well, a quantum card game where you essentially play cards and thereby perform these operations. And overall, you have to essentially program this overall quantum computer in the way that is favorable for you, get the highest state possible. So in case you're interested, there you can look up these. There's an archive paper, you can download these cards, and there's a program evaluating your state because it's rather complicated. But it's really nice. After a few games, you get a bit of a feeling, essentially, what these quantum operations do. But yeah, this was not the main part of this talk today. We wanted to look into 2-photon interferences. So when we go back to this very first modulation that I started with, so the Hadamard, I called it Hadamard operation. A Hadamard is nothing else than a beam splitter if you have 2 modes. For high-dimensional, then it's a high-dimensional beam splitter. So if you look closely, this would be, if you compare it to the usual beam splitter and you consider this is one path and this is the other path, then you end up with a superposition of the 2 paths, just like what a beam splitter is doing. Photon in one input, and there's a superposition of the possibilities of the two outputs. And if you send a photon in from the other input, it will get the same superposition, but with a different phase. Okay, so when we realized it, of course, we said, okay, we want to see that photons are also, 2 photons are also interfering in this degree of freedom, not in a path, but in the spatial mode degree of freedom. But let's back up. We heard already about 2-photon interferences. So a very brief recapitulation, since we are all on the same page. So if you have a normal beam splitter and you send 2 photons in, you expect classically to have 4 possibilities that can happen. Either they come out in the same output port here or in the same output port here, or they come out in different output ports. But if you do the calculation, the quantum mechanical calculation, you will see that actually these 2 possibilities destructively interfere away. So you only have essentially this kind of these 2 possibilities. And in a quantum state, this is described like that. In the experiment, we heard it already, but now also with a picture, what we usually observe there is we send the 2 photons into our beam splitter. We delay the arrival time of one of the photons. So we scan that. And while doing so, we observe correlations between the 2 outputs. Okay, so and if we are far away, so if the 2 photons are not impinging on the beam split at the same time, then we get a certain number of correlation clicks, coincidences. But as soon as we actually, if they arrive at the same time, they interfere. So these correlations between the 2 outputs will vanish because these 2 possibilities essentially that I depicted here destructively interfered away. So when you scan this delay, what you usually get is this typical Hongo-Mandel dip. So that's this Hongo-Mandel interference. That was in the last talk, was essentially used in nice imaging experiments. Okay, so this is the typical dip that we want to observe, just that you understand then a bit better what you will see in the next slides. But as I said, we don't want to do it in the usual path domain, but we want to use our spatial modes. So we have our unitary that performs essentially the same operation. And then if we put our 2 photons in, one in this mode, one in this mode, and we send it in our unitary, we expect 4 possibilities, but 2 are actually destructively interfering away if our system works quite nice. Okay, so we get a state in the end where the 2 photons are always coming out in the same spatial mode. Instead of the spatial path is up here in the same spatial mode. I want to say that there has been experiments with using normal beam splitters in spatial modes, where they observed already some interference involving spatial modes, but there the spatial modes were just essentially a knob to interfere or turn the interference on and off. One can say it like this. Very nice experiments, but in our case, it was really just along a single beam line. So we didn't use beam splitters. Okay, so saying that, you see in the sketch of the setup, we actually have beam splitters. There was, let me explain you the setup, and you see what I meant. So we have to start with photon pairs. We use the parametric down conversion process, very standard. There we have our delay line that I mentioned earlier. We put the two photons into single mode fibers to spatially filter them, and then we use the spatial light modulator using holographic techniques to shape the modes of the two photons. And then we now have to bring them first onto the same path. There's other ways of doing that with perfect efficiency. We used the most simple. We just brought them on a beam splitter. They had different modes so that there was no interference going on there. But now we had both, at least probabilistically with some losses, we had both on the same in the same path. And here is now our unitary device, our so-called multiport for spatial modes. So here we actually then observed two photon interference in the spatial mode domain. So after that, we expected to have, or we expect, and we will, we had this kind of interfered state where both photons are either in the plus or in the minus mode. We have to measure that. So then we used again another beam splitter to split the two photons probabilistically. This could be done better, but it's the simplest case for us. And then we use holographic techniques again to measure the structure of the modes. That functions essentially that you have a certain transformation that together with a single mode fiber acts as a mode filter. Okay, and then we look for correlations. So do they actually come out in the same mode or in different modes? So by just switching our holograms here, we can test for both. And these are the results. So as you see before, so the blue line corresponds to if they come out in different modes, and if the delay is 0, they are not, which is good. But as I said, we can also test if they actually come out in the same mode. This is then the orange line here. And you see, yes, we get an increase of the coincidence counts if we look if the photons arrive in the same mode, if both of the photons arrive in the same mode. So the visibility was quite good, of course, can be improved. But for first test, we were really happy with the results. The nice thing about spatial modes is that you can now actually simply even test if they come out in superpositions. If you choose the eigenbasis, for example, of your beam splitting operation, you don't see any interference. So that would be the same for path, but for path, it's very, very challenging to actually measure a superposition of two paths. So you have to use or construct an interferometer. That's a big advantage for spatial modes because we can just project on a different spatial mode. And similarly, at the input, we can also send different superposition input states and observe the same effect. So this is a very big advantage in terms of spatial modes because we have very powerful generation and measurement techniques. But as I said, this is not just this unitary operation is not just working for two input, two outputs, normal beam splitters, but also for higher dimensional ones. And then we, of course, we wanted to observe that as well. So we essentially made an analog to what people then usually do in multiple paths. So this is a higher order beam splitter for path. We have tunable beam splitters and phase shifters, or in an integrated way that is investigated or has been investigated or is still investigated in many groups around the world over the last decade, I should say. We essentially do something very similar, but along a single path. Okay, so instead of many paths, we have just multiple planes to modulate the beam and many modes along a single beam line. And of course, this doesn't have to, like, it could be a complementing technique. So one can combine both and multiplex back and forth. So I think it's really a nice additional degree of freedom. Okay, but so we essentially, with the spatial modes, we have the possibility to build small linear optical networks. And we tested this, so we allowed ourselves 3 modes. We saw then, like, the dashed lines are always the theoretically expected scans, essentially, or coincidence counts when you scan the delay. And for different input and output modes, our measurements here, these are the dots, following quite nicely. We also can then do more complex, a slightly rotated unitary operation where we even see an anti-coalescence. Not go into the details, you can look that up also in this recent publication. And then we also went on to the four-dimensional state space, where essentially you can tune in your unitary an internal phase that you don't really observe classically in an easy manner. But then in the two-photon interference, it can completely change from essentially coalescing to anti-coalescent if you look at the right input and output modes, or no interference at all. So that's quite nice. It's known for 4 dimensions that it is working. We've also observed it. But you see here that now we would need to include more phase modulations. So in principle, you need roughly the number of phase modulations as the number of modes you want to use. So here we use 3 modulations, and for 4 modes, it's already a bit at the limit. Okay, but let's go back to what we actually do when we generate, or when after Hongo-Mandel interference. What we actually create is a so-called noon state. Like following the name is quite clear, I think. So you have n photons in one path and 0 in the other, in the usual path description, or 0 in this first pass and n photon in the other. Why are they interesting? So it has been shown that they actually have the possibility to be super phase sensitive. So compared to the classical limit, they scale essentially with 1 over the photon number and not 1 over the square root of the photon number. So in experiments, when people observe that, what you usually do, you use your classical beam splitter, then you have your noon state, you put a phase shift in one arm, and to observe this phase, you have to look into interferences. So you essentially put another beam splitter in, you close your interferometer, and then when you change the phase, essentially you see a faster variation depending on the photon number. So with 2, it's a 2 times faster variation of the interference down here. So in our case, we have now this noon state in the spatial modes, okay? And we verified that in our experiment. This is an entangled state. We tested how good it is entangled with an entanglement witness. So we are very close to the theoretical value of 3. So we have generate a very, very good quality of the state. But what does this now mean in the spatial mode domain? So let's say we have our device, we bunch our photons, we have our twisted noon states, as we called it. So noon states in the OEM degree of freedom. Now we have a phase shifter in here. So what does it mean, a phase shift for these OEM spatial modes? Actually, this means a rotation of the mode. So if you just add up a certain phase, the mode is essentially rotated, or vice versa. If you rotate the phase, the mode, you actually imprint a certain phase. And this is also scaling with the OEM value. Let me depict it a little bit for you. So if you have a +1 and you rotate it, let's say by 45 degrees, this corresponds to a phase shift of plus pi over 4. If you have a -1, it's actually a minus pi over 4. So it's just the inverted, or you just have the negative sign. So the same rotation corresponds to different phase shift for 2 different modes. And for higher orders, the same rotation, for example, +2, corresponds to even a bigger phase change. Okay, and when you kind of cut it a little bit, then you will see that these, maybe I hope you understand that these spatial mode noon states, in terms of rotation, are twice sensitive. So they are, on one hand, if we have more photons, because the phase change is enhanced, we are more sensitive because of the photon number. And at the same time, because we have this OEM quanta, this OEM value, they can be more sensitive if we use higher order modes. So you have this 2 times special quantum scaling here. And of course, we wanted to observe that. How do you observe it? As I said earlier, you have to close your interferometer. And when we were at that point, we said, well, we need another MPLC system. But then we realized, or this multiplane light conversion system, but then we realized it's actually much simpler, because we have this powerful technique of generating superpositions. So we can put this unitary in the generation, and then just essentially, so here we have already our unitary in the generation, and then bring the 2 photons together on the path. And then we actually already have this state. So for this specific case, for 2 photons and our approach, essentially this works. It's not as general as what I explained before. The same holds, however, also for the detection. So we can put the unitary in the measurement. And then even better, since we use spatial light modulators, we don't even have to rotate our light field. We can rotate essentially the generator, the detection mechanism, the detection system. So by just rotating our holograms. So that simplified, of course, the setup a bit, and we were able to go to higher values. And how high? Let me show you here. So the black line is essentially for single photons, and you see if we rotate the state, so we generate it and we rotate it over 360 degrees, we essentially get one fringe. For 2 photons, we get two photons. So then over 360 degrees, we get 2 fringes for 1 photon, so we get 4 fringes for 2 photons. Then we continued increasing the OEM value. We have still 1 photon or 2 photons, and you see here it looks very similar, but let me point you to the x-axis. So it's now a factor of 10 smaller. So we have a rotation, so we see the 2 fringes already after 36 degrees. And we went on, that was the highest number of OEM value we could generate and measure properly in the lab. And then we were able to see the same effect. Already after 3 degrees. So if you're interested in, this is described in more detail in this now accepted paper, so far in the archive. We investigated it also in terms of Fisher information, where do we have the best angular resolution essentially, and then did it for many different modes. And this is essentially everything combined in one graph. So the solid line is essentially what you expect for single photons, the dashed line what you for 2 photons, and we get relatively close with our measurements to the expected values. This is mainly due to losses and errors we have in our system, and you see the higher OEM values deviate quite a bit for the low values. So this is a zoom in here. We are essentially around what we expect in terms of angular sensitivity that we have in our system. But now for the last maybe 5 to 10 minutes, let me go to the second part of the talk. And I'm not sure if everybody is familiar with this fundamental optics effect called Talbot effect, which is a self-imaging effect. So this is essentially an effect was discovered many years ago by Talbot, and it's a lensless self-imaging. He realized that if you have a periodic, essentially, or you have intensity arranged in a periodic structure, and you let it just propagate, then due to interference, after a certain time, you essentially get what is then a certain propagation distance, after a certain propagation distance, you get the same pattern as you had in the beginning. After one of these Talbot lengths, we called it, or it's called, you get the same pattern but shifted, and after twice this Talbot length, you get exactly the same pattern. So it's a self-imaging effect purely due to propagation and interference. And this is the formula where do you observe this Talbot length. So it's a very nice effect, and it has been observed for optics, of course. It's also where it was discovered, and it has been observed for electrons and atoms and molecules and so on. So this is a known effect. But we at one point then asked ourselves, is that also, can you transport it also to other geometries? And yes, interestingly, this is exactly the same. Slight differences. You can observe the exact same thing on the surface of a cylinder. Here, the periodicity is actually replaced by just having a periodic, so the periodicity that you usually have in your multiple starting beams is replaced here by the periodicity of the angular coordinate. So it makes it much simpler, because this classic Talbot effect here only works perfectly if you have an infinite extent of your light field, which you never really have. So here you get this essentially for free, because you have this periodic angle. It only works then perfect if you have your light or your wave confined to one particular radius here, R. I think later I have capital R, but it's the same R. But of course, in experiments, you're never able to only confine it to a single, but very close, as you will see in a second. So when we looked into that, we said, okay, how can we do that in the lab? Now you see it's a capital R, but it's the same. So how can we do that? And there's people working on ring core fibers. So that's the experimental implementation of that. We can confine light to essentially a surface of a cylinder by just having this kind of index distribution. So there's an index change between this ring core and the cladding around. And these were our values that we chose following some simulations to have essentially a reasonable Talbot length to see this interference effect. Okay, maybe it's instructive to first look into the simulations. That's what we did back then. So this is the pattern. If you just roll up your cylinder, you see a similar Talbot pattern that you know from the normal, like 1D or plain Talbot effect. And when you, let's say, propagate your light through, it's quite nice to see what's going on. I hope the movie works, at least for me it does. So if you launch your light into one single input spot, you see that it's distributing around the whole ring. And after fractions of the Talbot length, essentially, you see that it's interfering to only 4 spots here, and then soon we will have only 3 spots. And so on. It's nicely working. You see the light. Of course, that happens on a very short distance. So for us, this was essentially 6 centimeters. And here you see now just 2 spots. So you're not just getting the image of itself after the Talbot length, which we will have here at the very end, but you also get in the fractional distances, you get essentially twice the image or 3 times the image, 4 times, and so on. So this is a feature of the standard Talbot effect, just as it is a feature of this cylindrical Talbot effect. Let's wait this few more seconds. You see already in this pattern here that the experimental imperfections, that's a simulation, but we included them, not having a perfect, essentially, ring, but a certain width of the ring, or not an infinitely thin ring. You see that the light is coming out at the opposite spot. So this is after 1 Talbot length, after 2, it would come out at the same spot. But you see it's slightly stretched. It's not as perfect as it was at the input. But in simulation, it worked quite nice. So we went to the lab. This is the setup, the first part, essentially where we used it, just investigated it classically. So we used the laser field. We controlled where we launch our light into the ring core by a spatial light modulator, because we can flexibly program them or cut out the light in the way that we want. We used an S wave plate or vortex wave plate to generate the light field that has a radial polarization, because that's where the effect works the best. And then we launched it into this ring core fiber, and we imaged the output with another objective. So these are just 2 objectives by a camera. So let's see what we obtained. So for our full Talbot length, we launch it into 1 input, and that's what we get at 1 output. That is the simulation, that's the experiment. So it matches quite nice. For half a Talbot length, so we cut the fiber essentially in half, or used another fiber, half the length. We see that it's coming out at 2 output spots. And also then a third of the Talbot length, 3 output spots. And since we are not able to cut like micron by micron the fiber, but we can essentially scan, nevertheless, the Talbot effect a little bit by using a wavelength scan. Because the Talbot length is wavelength dependent. So by changing the input wavelengths over the range that our laser allowed it, we could actually scan a little bit of this Talbot carpet. And these are the results. So you see, this is the simulation. And you see that we have a quite nice agreement in the experiment. There's a few things that you see additionally that you don't observe here. And we verified that with other simulations. So this is mainly due to the imperfection of not having a perfect ring. Okay, so it's slightly elliptical, and then the light stays a little bit more on the where you essentially launched it in. So you see that it's a bit brighter here. But these are just technical, slightly technical limitations. But then, as you see here, at half Talbot length, you essentially get 1 input and 2 output. Okay, so it's a natural thing that you say, okay, that sounds like a beam splitter, so let's try to reverse that. Let's send into this fiber length, half Talbot length, 2 inputs. So that's what's depicted here with the right phase between them. You will get only 1 output. So the 2 light fields coherently interfere into 1 output. If you change the phase between the 2 inputs, they're not interfering, or if you flip the phase completely, then it's interfering on the other side. So it's actually working like a nice controllable or a coherent beam splitter. And since it doesn't matter which input essentially spot you choose, you could also have multiple beam splitters. That's what we did here. So we sent 3 inputs at the same time in, and you see here they split just on opposing sides at the same time. The quality gets a bit low, but you have this one ring core fiber and you can have 3 beam splitters at the same time working in parallel. And we showed that also by controlling the phase between these 3 inputs, that you still get this interfering at this effect. And of course, the same holds also for a third of the type O length fiber. You have then a beam tritter, and you could coherently combine 3 beams. But we then went on to the quantum domain. As I said earlier, beam splitters, usually we tend to think in, oh, let's see if there's photons interfering. But first we verified that the effect also works for single photons that have a much broader bandwidth than our laser. And when we send in a single input, there we don't have this nice cameras. So we just essentially made a slit and rotated it around. And then we see at 2 angles, we get a lot of heralded single photons events. And if we then interfere these, this was using just a normal sensitive camera. It's not really single photons. It's more like just the singles. So the single photons out of down conversion are only proper single photons if you herald them. But here you at least see that there's interference going on if you interfere these 2. So verifying that there is phase coherence between the 2 outputs. And then we just made 2 slits at the dark and the bright fringe and measured the visibility properly, heralding single photons, and we achieved 96%. So that works perfectly for single photons as well. And then the very last thing that I want to mention today, we send in 2 input spots 2 photons. And then with the same logic as we discussed earlier, the 2 photons should interfere. When you measure then a correlation between the 2 output possibilities, and you scan your delay again, you should see that there's this homo-Wendel dip appearing. And that's exactly what we observed, really good visibility. So the effect works really nice also for in the quantum domain. If you want to know more, this is the recent paper that has also just been accepted. And with this, I come to the conclusion. Hopefully, no, there is a few minutes left for questions. I think I'm happy about that. So yeah, I showed you that this multi-plane light conversion, MPLC, can be used in the quantum domain, can be used to have quantum gates. I very briefly mentioned that. And then I introduced a bit more that we can observe using these unitaries 2 photon interferences along a single beam path in the spatial mode domain. And if you pick certain interferences, then you get Noon states. And these are in terms of spatial modes of OEM carrying spatial modes. They give you an enhancement in the angular resolution. Okay. And finally, we investigated the effect if we send light into a ring core geometry, ring core fibers, and we saw that this is like doing the cylindrical version of the Talbot effect, and it can also be used in the quantum domain. And we are currently investigating how far we can push that there. Of course, it's not done by myself, mostly actually by the students. So the first part was mainly done by Markus Jäckämäki, a PhD student of mine. And the second part, the cylindrical Talbot effect, was mainly done by the gentleman that is displayed here that unfortunately couldn't join when we did this group picture, Matti.
Hello. Professor Fickler, there is some audio problem. Hello. There is a network issue. Sorry, Professor Fickler, there was some network issue that we couldn't
There was
hear.
a network issue. I think my screen is now gone, but let me share it again just for the very last slide. I don't know if you heard, it was anyway just a recap. I just wanted to mention the very end, next year there's the ICOM, the International Conference on Optical Angular Momentum, happening in Tampere. By the end of the year or beginning next year, the submission will be open and you're all very welcome to come to the north. With this, thank you very much. Sorry for the interruption. My computer does weird stuff.
Yeah, it's okay. Thank you very much, Professor Pickler, for such a wonderful talk. Now we will pick some questions. First one is from Vardhan, like up to how many beam splitters were you able to achieve via ring core fibers?
So the ring core fiber is generated by our collaborators, this Yuri Jamorovsky in Russia, and they are generated in the way I understand it, very similar to normal fibers. Actually, you have a preform that has where you already imprint this refractive index profile that you want, in our case a ring, and then you really just pull it and you get a long fiber, just like you warm it up and pull it. At least that's my very simple understanding of how this works. So this is done by our collaborators, and it's the same process as for normal fibers, but starting with a more complex preform, the thing that you then pull to a fiber. I hope that makes sense.
Okay. Another one is like, what are the advantages of one gate while using one photon and photon pair in Talbot imaging over laser?
So, the single photon was for us just a test. Does it also work for single photons? The results are exactly the same for single photons and the laser. It's just that the single photons have a broader bandwidth, and that since the effect is like the laser is, I don't know, a few hundreds of megahertz or gigahertz bandwidth, and the photons are much broader, 1 nanometer or something. So we just wanted to see, because the effect is wavelength dependent, if that really how badly it influences, and it works quite nice. For 2 photons, that's then a quantum interference effect that we wanted to observe in this kind of very complex interference that is going on, that it still works on that then the outputs, and it worked quite nice. And why? It could be a way, for example, to have what people now have on a chip in multiple waveguides. There you have it on one ring, so you just launch in your photons in multiple input spots, and then you have a small linear optical network. So the problem there is, or the challenge for the future, and we already thought about it, let's see what the future brings, but you have to make it, of course, somewhat controllable. So you want to then generate or make different, with the same fiber, just like they have with the same chip, different modulations. So in our case, we would need to be able to essentially locally change the refractive index a little bit by heating or so. That's what they do, at least in waveguides. But this is future, so we first wanted to observe that this is actually working on the quantum level as well. Okay.
Okay. Next one is, what was the direction of the fibers to see the cylindrical Talbot images?
The direction of the fibers. So the fibers have to be very straight. So that's the challenging part. If you bend the fiber, it's not fixed into a proper cylinder geometry anymore, and the effect changes quite a bit. But it would be interesting to, I mean, we just saw it that when we touch our fiber, the effect is like the interference in the end goes a bit nuts. So, but it would be interesting if it gets very challenging, I assume. It would be interesting to have a proper controlled bending, and maybe you can do something there in terms of the output. But this is then not as simple anymore, both in terms of experiments and theory. But the fiber itself was, in our case, just lying on a piece of metal straight.
Okay, thank you. Next one is, why radial beam is the best for generating cylindrical Talbot effect? Is it anything related to the symmetry of the system?
It is the symmetry of the system in the end. So you have this cylindrical symmetry, and I think so in our case, we wanted to observe this, or you can observe this Talbot effect on the surface of a cylinder. In our case, it was this ring core fiber, because cannot easily guide a light on a surface. But it's actually, I think it was more out of a discussion to, okay, in the usual Talbot effect, you have this infinite, you need to have a grating structure, grating a periodic essentially structure in the beginning that extends to infinity to have it working perfectly. And this, on the cylindrical geometry, you can use the periodicity of the angle essentially to get around that. And that was the inspiring first part. You don't really need radial beams. You just need to launch in your photons in certain input spots to observe that. And it doesn't matter which input spots you choose, just one, and you get the effect in the end coming out.
Okay, thank you. Next one is, what is the significance of the relatively smaller dips on the either sides of HOM dip, as the HOM must only happen at the point of relative zero path difference?
Mm-hmm. So I don't know exactly what on either side means. So we have pretty good visibility. If I go back to this slide for just a beam splitter, maybe if I understand the question correctly, like if you have a high dimensional beam splitter, then you get even in theory smaller dips. So that's just, you have multiple output ports and you just, like in this case with 3 modes. For a beam tritter, classical one would be also 3 different paths. So if you just look in a subspace, just look into 2 outputs of the 3, you get an interference signal, but it can be either like the coincidence increase if you look into the same output modes, normally to the factor by a factor of 2, but the dip essentially just goes half, because the other the photons they also have other possibilities to get out, not just the 2 in a classic homomandel. So this is in theory expected and known. For 4 dimensions, you can also have then a perfect interference, but it's depending on the dimensionality on your unitary, what you expect. I'm not sure if I answered the question correct, but this was different depth of the dip. You're mute now. I hope I'm not. I don't hear you anymore. Yeah, now.
Yeah, sorry. Yeah, sorry. There are 2 more questions. Can we observe Talbot effect with pulse laser or optical frequency combs?
Very good question. Nice question. Yeah, I think it should be observed. It should be able to observe it with pulsed lasers as well. But again, then depending on the bandwidth, it might wash out. So if you have a very short pulse and you have a very broad bandwidth, then it might not look as clean as sweet, but it should work as well. For frequency combs, I think the cylindrical one should be definitely observable, but again, there's different frequencies, so it might be more complex. The pattern that you get out, the interference should still be there. Interestingly, people have observed this Talbot self-imaging also in the temporal domain. I'm not sure if they use frequency combs, but you can also, we put it to the cylindrical geometry, you can also put it to a complete different domain, like to the temporal domain, and you see that, or frequency domain. So it's a very general interference effect.
Okay. Last one is how you are generating such a large LG beams.
Okay, this we did just simple with the SLM. So and that's why it's also limited to this 100. I mean, the beam's getting bigger and more challenging, but with the SLM, our resolution at one point is of course the limiting factor. But as you saw, you can generate quite clean plus minus 100 beams with the SLMs that we have that have 8 micron pixel size and full HD resolution. So that relatively simple, just with the SLM imprint the face or use hologram.
Okay. So I hope Professor Robert have answered all the questions. Further questions?
Hello.
Yes?
Sorry to interrupt. There is a question in the chat box. Can you please read it?
Yeah, sure.
Is that the chat box? I think it was more an answer. Was it? If you have the very good CCD, then yes.
Hello, Anirban?
Yeah.
But I was kicked out, so maybe I don't see the question. So
We have a very good CCTV.
Okay.
Thank you, Professor Robert, for such a wonderful talk and having conversation with us.
Thank you very much. So in case there's further questions, you can contact me also on
Yes,
this
sure.
page. So thank you. I will now stop sharing.
Thank you very much.
Not delay further.
Yeah. Next, we have a student talk by Mr. Isaac Knapp. Currently, he is doing his PhD at University of Witwatersrand, South Africa, under the supervision of Professor Andrew Forbes. Today, he will be delivering his talk on a method of characterizing high-dimensional entangled state. I would like to invite Mr. Isaac Knapp to deliver his talk.
Hi, can you hear me?
Yes.
Okay, great. So I'm trying to share, and it says host disabled participant screen sharing. Great, thanks. Can you see the screen?
Not it.
Okay.
Yes.
How about now? Okay, great.
Yes.
I guess without further delays, I'll start. So good day, everyone. It's like midday here, sure it's like afternoon, everywhere else, and morning somewhere else. I hope you're all well. My name is Isaac Knapp, and I'm a PhD student at the Structure Fact Lab, which is led by Professor Andrew Forbes. Today I'll be presenting on this technique that I've been working on for the past year. It's designed mainly for characterizing high-dimensional entangled states in a fast and a practical manner. And this work was done in collaboration with Taiwan University and some colleagues from Harriet Ward. So before I begin, I'm pretty sure most of you guys already know, but just to familiarize some of us, what does it actually mean to have high-dimensional entanglement? I mean, suppose you have two photons that are generated by some entanglement source, spatially separated. If they're not entangled, they're separable, and that just means that you can write them as a separate product of the individual states describing the subsystems. If they are entangled, you can write them as a superposition that's not separate. For example, consider this two-dimensional case. So each photon lives on a two-dimensional Qubit space, and you can construct this kind of superposition here, which is just a symmetric belt. Now, if I want to increase the dimensions, in other words, the size of the Hilbert space that each photon stays on, and also have entanglement, I simply have to add more terms to the superposition here. So I'll add more basis states to the Hilbert space of my individual photons and construct these two photon product states and add them into superposition. In general, I can do this for many states, and D would be the number or the dimensionality of that entangled state. And these two photon states, which are linearly independent, we can call them a Schmidt basis. And these coefficients here in this decomposition are called Schmidt coefficients. Okay, now in photonics, like Professor Fittler said now, most people like using these beams that carry OAN because you can encode information in the azimuthal component and also in the radial component. And if you do that, you get like the Legier Gaussian spatial profiles or the Bessel Gaussian spatial profiles. And for entanglement, you can generate photons that are entangled in either one of those two mode families using spontaneous parametric down conversion. This process, all it does is you have a high energy photon, which impinges on a nonlinear crystal, and then you produce pairs of photons. Okay, and this process conserves energy and momentum. And as a consequence, you also conserve orbital angular momentum. So the orbital angular momentum of the two individual photons that are produced must add up to the orbital angular momentum of the photon that entered the system. Okay, and because the OAM basis is unbounded, and we can characterize it with this topological charge value. We have an infinite set of modes with which we can work with. Obviously, in the lab, you're limited by the resolution of your systems. And yeah, so if you were to project these generated photons onto the OAM basis, you typically get like a very strong diagonal or anti-diagonal in this case that looks like this. And that's just saying that you're just conserving the OAM. And this is just a special case when the OAM of the input photon is just 0. And we can estimate the number of modes that contribute to this state using this parameter k, which is 1 over lambda, which is the Schmidt coefficients to the power 4, just sum up them. And then you get the effective number of states or non-zero states to describe the state. You can go read more about progress in this field and how these kind of spatial modes are used in this review paper I listened to with my supervisor. Anyway, moving on. You may notice that the decomposition we use now was actually mainly for pure states. So you have a simple pure state vector that describes your system, right? In most cases, you do know what the Schmidt decomposition is, and you have a second component which then contributes noise. So all the basis states which live inside your entanglement system are encroached in noise. Okay, for example, here I have a case where I have a lot of noise. I still have so I have low noise. I have low, where you see you have low background counts and still maintain a strong diagonal. But in this case, you have high noise. And using this decomposition, you can represent these two cases with this parameter P, which is the probability of producing the pure part of your state, given that you know what the Schmidt decomposition of it is. Okay. And P, again, if it's very low and particularly like close to 1 over d plus 1, where d is the dimensions, you have separable or mixed states. And if P approaches 1, then you have a pure state because you have very little noise contributions. The impact of this in most experiments, for example, in post imaging, which was presented earlier, is this affects the resolution of your images. For example, detector noise can add noise to the single photons that you detect. In other words, add more unwanted single photon signals. And this would reduce your ability to like make out what these digits are here. Another impact, which you usually don't, negative impact, which you don't want, is in quantum key distribution or quantum communication channels, where the noise can cause unwanted detected signals that encroach also the signal, that drown the signal that you're trying to transmit. And this can lower the capacity or performance of your communication system. And so it would be nice to have a technique that can give you P and K immediately so you know how to optimize your quantum system. Now, most conventional techniques for characterizing quantum entangled states in high dimensions are also like typically using quantum state tomography, like using projections onto different superpositions, which are of course, which have to be over complete. And then you use that information together with maximum likelihood algorithms to determine the state which produce the measured signals, okay? You could do this with like arbitrary superpositions, or you could use mutually unbiased basis states. Alternatively, you can also characterize your entangled states and know whether they're good or not, or in other words, are of good quality or not, by using entanglement witnesses. And if you look at the complexity of the measurements as they scale with dimensionality, they're normally like quadratic. And so if you have hundreds and hundreds of dimensions in your system, the measurement procedures can take time. But of course, these procedures are more favored because they are more concrete and information theoretically complete as well. So what we looked at doing is instead constructing a set of measurements that return information about the state, and mainly making use of the fact that you know what the decomposition is. And I'm going to use the isotropic state as the example. So suppose, in our technique, we construct these superpositions here, where J is just your basis state. Okay, it doesn't have to be the OAM basis, it can be any particular basis you like. The main focus is on the relative phases and amplitudes. I don't have time to really explain how we construct these relative phases and amplitudes, but the main focus is this parameter here, this n. What n does is, if I look at the spectral decomposition in my bases, as I increase n, I'm controlling the sparsity of these modes and the spacing between them. So in other words, it seems as though these analyzers are actually probing various parts of your Hilbert space. Even more interesting is when you take these analyzers and you place them in front of your two entangled photons. Okay, for example, in the OAM basis, if I construct them, the analyzers look like this. And I must also add that they're actually related to fractional orbital angular momentum states. Okay, now if you take these analyzers and then measure coincidences as a function of the relative orientation of them, okay, you find that you get these sinusoidal periodic fringes, okay? And these just indicate that you have some kind of quantum interference or non-local interference in your measured detection probabilities. And as you change n, the frequency also changes. More interestingly is that the visibilities are very sensitive to the number of dimensions or the effective dimensions of your state. For example, here for n equal to 5, the k equal to 3-dimensional state, k gives us almost 0 visibility. So the peak and trough, the relative distance between them is basically 0, whereas here when I have like larger than 30 dimensions, you find that the peak and trough relative distance is quite high, and therefore there's a visibility of 1. Okay, even more interestingly, if we use the isotropic state before, when you plot the visibilities for various n's, okay, and look at them as a function of the effective dimensions k and p, the probability of producing a pure state, you find that they scale monotonically. And in fact, the sensitivity increases as you increases this n parameter that I showed you earlier. For example, here, 100-dimensional entangled state would give you visibilities close to 1, whereas for n equal to 55, the visibilities are like close to 0.5. So it means that these visibilities carry information about what's happening for different dimensions of the state. Now, let's say now you produce your entangled photons in the lab and then apply our technique, okay? We showed that like with high noise, in this case here, high noise, the visibility scale monotonically with the n parameter, okay, which confirms the sensitivity to the dimensions n to n that we spoke about. And also if you increase P, the visibilities improve, showing that you're also very sensitive to the amount of noise that's present in your system. Now, interestingly, you can take each of these visibilities for the specific n and then intercept it or find the curve that intersects the plane corresponding to the measured visibility with the theoretical model. And when you combine those curves, okay, where here the thickness is just the uncertainty in the visibility measurement. So for each of those n curves intersected with the planes, when I combine them and look at them under my parameter space, okay, and P, I find that where they intersect corresponds to the dimensionality of the state. Another way to confirm whether this is true, you can just use least squares fitting, okay, where you just minimize a quadratic cost function, which is just the difference between your measured visibilities and the visibilities for a theoretical model. Where this is maximized is where your state lives. And these two procedures give the same result, which confirm that actually the visibilities that you measure are strongly related with the parameters that define the state, in our case being P and K. And we did this for both the low and high cases I showed before. And when we confirmed it with another technique, we found that actually they match quite well. Now, we also did this with the pixel position basis. Okay, again, all you do is you just pick the basis states of your system and then construct the superpositions with the amplitudes and the relative phases which we subscribe. And then these are what the phase must look like. So you still have this spatial nature in the your basis states. Okay, the pixels separate as you increase this n parameter. And when you apply them, measure the visibilities, and then minimize your chi-square or quadratic cost function, you find that where the state gives you the peak, this is just 1 over the chi-square. Where you find the peak is where the dimensions of your system actually lives. And as you can see here, we did it for 80 dimensions. In the paper we wrote, we also tested it for 100 dimensions, and you can find the measurement values there. This work we recently published in Nature Communications. So if you want to find out more details about how the technique works, and yeah, I'd like to thank you all for your attention. I'd also like to thank the collaborators that we work with in our group. This is a nice picture of our group here in South Africa. So if you do ever visit, you'll see a lot of nice friendly faces. And yeah, thank you very much.
Thank you very much, Isaac, for the wonderful talk.
It's a pleasure.
Yeah. So anyone, if you have a question, please put in the Q&A session. Anyone have a doubt, please, they can also raise their hands. Just wait a minute. Yeah, there is one question. Can you explain the bandwidth of OM modes?
Like in SPDC. Well, let me just. So if you look at the SPDC state, you can decompose it in the OAM basis, because the OAM basis is actually a valid Schmidt basis for the SPDC states. And what you normally find is that the higher order modes have a very low contribution in terms of how much energy is sent into them by this down conversion process. So the largest OAM number that you can find a non-zero probability for sets the bandwidth of your system. So for example, in that diagonal plot that I showed, if you just measure the full width of maximum of that, that's effectively close to the dimensions. But if you really want to like do it in a more concrete way, you have to calculate the Schmidt rank, and there's several procedures to quantify it. I think in my second slide, I showed the 2MUB procedure, which allows you to also witness the entanglement dimensionality of your state.
Okay, thank you. Is it a question, Vardhan, like lambda dependence on you mentioned it? Okay, that was just. So if there are no further questions, let's thank the speaker once again. Thank you, Isaac.
Oh, I see a question, Ravindra. Well, sorry.
Yeah, just wanted to ask one question. Whether this this dimensionality you are asking, it's not monotonic increase with like sometimes the 3 dimension you have visibility very bad, then you go higher dimension, visibility increases. So whether it is monochromatic function, this visibility, or like whether it is monotonically increasing function, or it is changing, like how you are going to fix that visibility, at what dimension it will be maximum.
So in the construction of the analyzers, if you know what the Schmidt decomposition of your state is, and you assign the basis states in order of states that contribute the most in the Schmidt decomposition, then the visibilities are always monotonically increasing.
Okay, that was confusing. At 3 it was very low, then some high dimension it has increased. So That curve was slightly confusing. I was not.
Pardon, I'm not getting the question.
You had some curve where for dimension 3 it was very bad visibility. Then you increase the dimension, it increased. And
Yeah.
then dimension 1 it was very good, something like that.
Yeah, so
that
it's because each of those visibility curves, the analyzer that you use to project, to get them, change the sparsity of the modes, so the mode separation. So if your state has very few modes and the mode separation is quite high, you shouldn't get any detection signal because the modes you're projecting onto in the analyzer are not present in the state. Hence why the visibilities are so low. But when you do increase the dimensions, you have more modal contribution. So the visibilities should go high because you have non-zero probability of detecting a signal.
So it was experimental like limitation, or it is theoretical? It's experimental limitation. What do you think that, or it is?
Well,
scientific?
it's not even a limitation. It's actually like one of the key it's one of the key things that make this technique good because it's very sensitive to the dimensions. That's what you want. You want a measurement procedure that can tell whether is there anything in this subspace or whether there isn't. And if my system is low dimensional, should I detect something as compared to when it's high dimensional? So our measurement technique makes use of this. The fact that the analyzers are each sensitive to a specific set of dimensions makes them ideal for probing various subspaces and various dimensions. So we want this sensitivity. Yeah.
Okay, fine. Thank you. I will see the paper. Read more carefully.
Right. Cool. Thanks. Yeah.
Isaac, there is one more question.
Okay.
Yeah. Have you used CG-LMP inequality to calculate S value?
With this technique, no, because firstly, the superpositions are sparse, therefore they violate like fair sampling, right? And that's one of the main conditions for demonstrating a valid Bell violation. So no.
Excuse me, Isaac. Can you repeat because there was some audio issue?
Oh, sorry about that. Our analyzers are sparse in nature, and so they violate fair sampling. So it wouldn't be good to use them for Bell violations because I think that's one of the conditions you need to be able to demonstrate a valid Bell inequality violation. Yeah.
Okay, thank you.
Cool.
So there are no further questions. Thank you very much, Isaac, for having
Thank you so
conversation
much.
with us. Yeah, thank you.
Cool.
So next we have an invited talk by Professor Joy Ghosh. She is currently working as an associate professor in the Department of Physics at IIT Delhi. Her research interests are in the area of exploring the spectral property of SPDC-based photon pairs and electromagnetically induced transparency. She will be delivering her talk on single photon entangled photon sources for quantum communication. I would like to invite Professor Joy Ghosh to deliver her talk.
Thank you, Professor. Am I audible?
Yes.
Is this full screen?
Yeah, we can see your slides.
Yeah, okay. So thank you. I would like to first thank Scope and the organizing committee for giving me this opportunity. It's a pleasure to come and talk in this forum. So before actually sending my abstract and title, I was in two minds what I should speak about, if I should focus on one particular problem and talk about it. But then rather I chose, seeing the time, I chose that maybe I could give an assortment of activities that are going on in our group and basically interest of our group. So that's why it's a little bit of a broad theme, but I'll be touching upon various things that are going on in the group. So I'm from IIT Delhi, and yeah, so I'm going to speak on single and entangled photon sources, primarily for quantum communication. So ours is a small group, quantum photonics group, which is based in the Department of Physics in IIT Delhi. And the key interests of our group are quantum and nonlinear photonics. And so there are various activities that are going on. We started with very basic things initially, but now recently, because of our sponsored projects and other kinds of activities.
Excuse me, Professor Joy.
Yeah.
There is background noise coming in from your side.
Background noise. Actually, I'm not using a microphone.
Maybe fan or something is running.
Actually, I'm not using the microphone.
Okay.
Is it clear now? Problem. Maybe I should speak loudly. Is it clear? Is it clear now?
Yes, it is clear, but there is some like repeatedly background noise is there.
Okay, maybe just 1 second. I will just get back.
Yeah.
Okay, is it full screen now? I hope the noise, the background noise will decrease. So I'll try and speak also loudly. Is it full screen and you all can see the screen?
Yes.
Okay. So, sorry, I don't have an earphone here today. So I'm just using the computer audio and I hope it works. So actually, so based on our projects, actually our group also has interest in fiber-based quantum communication, guided waves, where we, and that is towards a multi-user quantum communication scenario. We also have interest in free space quantum communication, where we use photons with slightly different properties, utilizing their spin as well as orbital angular momentum. Then towards this direction, actually, initially we started our research with simple entangled photons in the telecom. And then we started exploring waveguides for the first time, because before that we were only working with crystals and we have that experience. So that's another area. And so something which is different is coherent light matter interaction that roots from my doctoral work. And so we also explore electromagnetically induced transparency, and we have an experiment currently in rubidium vapor cell. So this is a topic which I will not have time to talk about today. So I only chose a few of them and talk about. So all these three broad areas, these are all dependent on the workhorse technique of spontaneous parametric down conversion, which is a Day2 nonlinear optical technique, second order one. But there's also third order nonlinear optical processes such as four-wave mixing and spontaneous four-wave mixing, in which we can also produce single entangled photons, single paired photons. And that has, so one of our activities is to explore this process in nano waveguides of silicon. So that we'll try to update on that as well. And we also have interest in detection of squeeze light. So this is like in a nutshell, and these are random picks from the lab, just to show you this busy lab, and there's some more space that's coming up and with more equipment. So we have a nice group. I mean, so this is the backbone of our group, right? I mean, it comprises of many PhD students and postdocs. Some of the names worth mentioning are Ramesh, who's already defended his thesis. So Ramesh and Vineet, they were mainly working on theoretical stuff. Shivani works on the four-way mixing silicon nanowave guides. Om Shankar is with the hybrid photons. Vikash is with the fiber-based quantum communication. Akanksha as well. Bharti Kaustav, these are new students. Rajni is another student on the EIT as well as Bharti in Rubidium. Dr. Mitali Sisodia is a new postdoc hired by the group, and she's an expert on theoretical quantum information. So earlier we were lucky to have postdocs like Dr. Ringo Nosuke. It's worth mentioning because he helped us set up the EIT experiment in Rubidium. So the EIT experiment is still not there, but the basic setup is there and we're working on it. And we also had Dr. Arun Patel sometime back working with us on the GST Quest project. So yeah, this is the outline that I've chosen. So I will be briefly introduce what I'm going to talk about. I mean the audience already knows about it, but nevertheless, just a little bit here. Then we will go on to the techniques of producing single entangled photons, also which I'll try to cover briefly. And then the main portion that I'm going to elaborate on is upcoming endeavors based on our projects and recent studies from our group. And if there's time, we'll talk about an iron photon kind of quantum network scenario, which is an experiment from the past, but it is important and it is fantastic challenging work which showed interaction of light and matter at a single quantum level. So yeah, so like everybody knows, the trends for enhancing computational power are twofold basically. First, you can have several units interconnected in order to make a large computational network, or you can individually have the components smaller and smaller such that you can densely pack number of components, so more number of components on a chip, for example. That is like hardware for any computer. So here's a small picture to show that these are molecular transistors. This one particularly is a molecule size transistor that can reportedly control the flow of single electrons. So we have actually how small these components can get to is a question that is continuously challenged, and people are working for it. There are researchers working in this forum and they're making it small and small. Till we hit the limit of a few molecules, which is already reached, and a few atoms, which has been also reached. And so there is this famous Moore's law, which tells you how many atoms do we need to encode one bit of information. So we are here and beyond, and we are already in this few atom per bit limit, where actually quantum effects start playing an important role and allow new applications to come forward. So rather than treating it as a problem, which is a quantum limit, right? Why not start taking advantage of these quantum effects? And so with this motivation actually gave rise to the field of quantum information processing, as you all know. And various researchers and various groups across the world explore in this particular regime. So just to compare a little bit, people know about this, but so a classical bit is a two-state system, and it's dichotomic. It can exist in 1 and 0, and that's it. So if you have n number of bits, there are 2 to the power of n states. Whereas in comparison, a quantum bit is a quantum mechanical. Usually, the physical system is always a quantum mechanical system. For example, it would be. So I'll elaborate on that, but it is basically again a complicated state system, but it can exist in two. There are two basis states, which is defined by this 1 and 0, and we usually picture the quantum state on this sphere, which we have different nomenclature. For example, it is called a Bloch sphere if you're talking about atoms. It is called a Poincare sphere if you're talking about photons as the quantum object, like the system. Like that. So in addition to 1 and 0 basis states, it can exist in any other superposition of 1 and 0. because quantum mechanics comes with this principle of superposition among many other things, which is an important thing. So these quantum bits can exist also in these superposition states. So if there are n qubits, it means that there are 2 to the power of n basis states, but in terms of those 2 to the power of n basis states, you can write down infinite number of superposition states. And in that sense, actually quantum information utilizing qubits actually exponentially expands the state space of operation, and it is tremendously powerful because of this parallel computation processing that can go about in comparison to classical computation. Now, example of the qubits from the lab or from real systems, right? Like I mentioned, so photons are a favorite. They are flying. They can act like flying qubits because of their mobility, and there are different properties of photons like polarization, orbital angular momentum, the presence or absence of a photon, the frequency of a photon. All those things are different properties by which you can encode a qubit. For example, if you take the example of a polarization. This is a two-dimensional information system based on polarization. So the basis states are horizontal and vertical, but there could be different kinds of superposition resulting into different circular polarizations or diagonal polarizations, and therefore this is good enough for encoding a qubit. There are higher dimensional systems, for example, orbital angular momentum, higher dimensional properties, right? It can exist not only like here it is, there are only 2 options, H and B, and in terms of that, here the basis states could be many. And so that's another property in which you can encode a qubit. If you talk about atoms, there are 2-level atoms, and there could be different superpositions of those atoms. You can so that is also another quantum system. Then there are electronic spins. There could be upspin, downspin, and various superpositions of that. So these are various systems, and there are many more actually. So I've just talked about only a very few basic ones, but there are others. So classical versus quantum information. So if we have to compare, so classical information processing depends on 2-state classical systems, on and off, that they can exist in. These are called bits. Local operations are performed through logical gates like AND, ORs, and NOR and other things. The classical communication depends on cables, buses, and networks, and this is how things look like. You can also interconnect several units, make them smaller, and stuff like that. Quantum information processing, on the other hand, relies on these 2-state quantum systems or qubits, and another powerful hand, which is not there in classical systems, is the existence of superposition states. Operations are based on unitary operations on the qubits through quantum logic gates. And in addition to all of this, there is also the property of entanglement, which is only there in quantum information and quantum mechanical, and like it is only valid for quantum systems. This also gives you a powerful tool in communicating information and various other things, which is not present in case of classical matters. Now, of course, technologically, if you see it inside a lab, I mean, interconnecting any of these units, or making photons or interact with atoms, or any kind of a quantum network scenario, or anything else for any other application, let's say, it is quite technologically challenging, and the lab looks quite complicated. But nevertheless, researchers are now, as we all know, things are getting miniaturized, and we're trying, like there are lots of efforts in building compact systems, also including ones that are the activities that are going on in PR Ahmedabad, for example, right? So yeah, so this is the direction. Now coming to the technique of producing single entangled photons. So the workhorse technique is spontaneous parametric down conversion. This is, as I mentioned, it is a Day2 nonlinear optical process, that is the second order nonlinear optical process. So it exists in medium which are non-centrosymmetric, where Day2 is non-zero. So typically in this process, a pump photon is incident on the medium, and there is this parametric process that the medium undergoes in order to generate a signal and ideal photon pairs, and these photon pairs are supposed to be correlated. So they're correlated primarily in time as well as frequency. So there is energy conservation in this process. The frequency of the pump should be a sum of the frequency of the signal and the idler, as well as there is momentum conservation in this process, whereas the wave vectors should all match. Now this looks like a perfect world, but usually there is, because of dispersion effects in real systems, in real crystals and all, you can never have the momentum conservation perfectly fulfilled. So there is always a small momentum mismatch, and there are techniques in nonlinear optics by which you can actually get rid of this, such as birefringent phase matching or quasi-phase matching, and one can build a system in order to phase match and have a particular process out. What do you mean by a particular process out? It means, let's say, this particular nonlinear optical process, but the signal and idler photons of a particular frequency, particular polarization, etc. Right. So once you have these photon pairs out, right, and you can also, so you can restrict or you can control your experimental system in some way, at least in some manner, in which you will have only the paired photons being released and not multi-photon. So you have to keep your powers down, and there are other criteria for that. So let's say for a particular type of phase matching, depends on fuzzy phase matching, you can have signal idler photons which are orthogonally polarized. And then by some experimental technique after this, or sometimes even before this, so we'll talk about it. So let's say you can map these two signal and idler photons into an entanglement state, something like this. This is a singlet state, let's say a bell state, which is like HB minus gauge. You can also have HB plus gauge. So there are different techniques to come about that. So this is one technique. And some of the intricate properties of this, like you can have non-collinear generation as well as collinear generation. So this is like the picture. So the photons, if it is a non-collinear SPDC process, it is the photons are usually emitted in cones. This is a non-collinear, non-degenerate. So there are two different distinct cones, one for the signal, other for the idler. If it is a non-collinear degenerate process, these two cones actually merge with each other. And you can also have this process collinear, in by which all the wave vectors, which is Kp, Ks, and Ki, they are all more or less parallel, and you can have, so there are different applications of each of these different things. Right. So now, as I just briefly mentioned, I talked about type 2, but actually in general, there are different types of phase matching also possible. Type 0, in which the pump signal idler, all of them are of the same polarization. Type 1, in which essentially the signal and idler are of the same polarization, but they are orthogonal to the pump. And type 2 is in which the signal and idler are of orthogonal polarization. Again, these different, based on different types, you have different kinds of applications and different kinds of entangled states that you can have the different photons out. So why am I talking about all of this? Because this has a very huge application. So all these photons, particularly because these are flying qubits, right? And so they are essential for, photons are like flying qubits, so they are mobile, so they are essential for any kind of communication experiment, right? And usually, so they are very, very relevant for quantum communication in the optical band as well as the telecom band. There are two different categories. Particularly for free space communication, the optical band is chosen. It is also relevant for satellite communication. And here, actually, in this particular band, actually your laser sources, detectors, all of these are quite well established. The detection efficiencies are not bad; they are good, and so those are the things. On the other hand, the telecom band photons, they basically find applications in fiber-based quantum communication. And here the detectors have a problem in the sense that they are not so efficient, at least the India's SPAD detectors. But nowadays, everybody knows that there are these superconducting nanowire-based detectors, which are quite efficient, but they are also very bulky and they are expensive. So there are different kinds. So this is just like an overview. So when we start with a particular project and experiment, we have to keep in mind all these scenarios and what all are the available sources and detectors and stuff like that. Now coming to some of the upcoming endeavors from our group and the projects. So currently we are working on one project, which is a QUEST project, which is to have integrated So integrated sources of entangled photons for quantum communication and quantum information application. So this is this is a fiber-based, WDM-based, a small compact kind of a source that we want to have, again based on SPGC, which we want to use for multi-user quantum communication. And some of the, so we use a type 0 PPLN crystal in this one, and we are basically running our characterization here. So we've done, so the first step in order to check your waveguide as well as your sources and detectors and everything. So the first thing is to do second harmonic generation, because second harmonic generation is actually the reverse process of SPDC, which I forgot to mention here. So in the forward direction, actually you put a pump, you incident a pump and you have the signal amygdala. But you can also think in the backward direction. So if you have classical laser fields at signal amygdala frequency, you can you can incident them into a crystal, and with the same phase matching of the crystal, like polling period, etc., you can have the second harmonic generated at the pump frequency. So in order to test, we first tested with classical processes. So the classical process is second harmonic generation. So that is what we tested. We have a good signal from our type 0 PPLN. So type 0 means you have signal and amygdala at the same polarization. So here the input field is 1550, the output is 775, which is your second harmonic, and this is second harmonic power as a function of temperature. We've also theoretically calculated, and we have a conversion efficiency of about 30% per watt. And this is at a pump power of a few milliwatts, less than 20 milliwatts. So next step is to see the photon count. So now you pump in the forward direction, but you start with a laser which is 775 nanometer. So these are the relevant photon counts. So this is a type 0 process. So we will not be able to separate it with the with any kind of polarization controller like PBS or anything. So what we use is a CL band splitter, because these are broadband photons and centered at 1550 degenerate, but they are so they have quite an amount of things before 1550. So at 1550 is the center, but before 1550 we collect with one output, and beyond 1550 we try to collect with the other one. Although the CL band splitter is not an ideal one because it does not exactly dissect at 1550, but a little bit beyond it, and due to that we actually lose on our coincidences. I'll talk about it. But let's say if you have the CL band splitter after the waveguide, then on the C band we just started. So these are like the first data, and the input power is very small. It is only 40 microwatts of power. Of course, if you go up high on the power, because of the dead time of our detector, it actually saturates. But if you enhance the power, of course, you have more and more amount of photon counts, and that was only at 40 microwatts. So these are just single counts, and this is a coincidence count, which we have seen with 2 different resolution times. There is a coincidence counter. So condition of the detection of the first detector where the second detector flips, and most of these counts should be coincident because these are paired photons which are produced at the same time. So these are our coincident counts per minute. So as you can see, the L band in this, these are single photon counts. The L band is little higher up compared to the C band, and the coincidence counts as you increase the resolutions. If you increase the width of the window in which you are trying to detect the coincidences, because the number of coincidences enhances. So again, this is with an input power of only 1.3 microwatt and at 775 nanometer. These detectors are actually not at all good. These are simple APDs, which are only 10% quantum efficient. So actually, there are many more coincidences, but we are not being able to detect based on the detection efficiency of each of these detectors. So another endeavor of the group is to explore quantum technologies with hybrid photons. And this is again for secure communication and quantum information. And basically this is for free space quantum communication, utilizing the property of photons based on polarization as well as orbital angular momentum. And in order to have rotationally invariant hybrid photons, so which are alignment free. So basically, we utilize orbital angular momentum and combine it with polarization. So there is a smart OM manipulator that helps us to do that. And this idea is an old one. This is there in this nature communications, but we are also trying to develop an experiment based on that, but with some other differences. And basically, we use this OM manipulator, which is a Q plate, in which if you start with, let's say, a left circularly polarized line, which is with OM 0. Then you, after this Q plate, you result in a right circularly polarized light with OM +1. So the RCP actually has -1 H cross as its eigenvalue, and the OM of +1 H cross, when you add with it, the total angular momentum becomes equal to 0. Which means that these photons, they become rotationally invariant in the sense, and this is particularly important for free space communication, where let's say Alice and Bob, among which the information is sent, they don't have a shared frame of reference. When they don't have a shared frame of reference, if you encode your qubits in terms of polarization, which is frame dependent, then these qubits get distorted, and you might not be able to transfer the full information that you have started from one location to another. But particularly if the two parties rotate with respect to each other. But if you have your information encoded in hybrid photons, utilizing this property, then this becomes resonant, or this becomes insensitive to any kind of frame rotation. So anyway, we are starting our experiments on that. We have a P2P crystal in that regard. Again, just like the other experiments here, we start with seeing first the second harmonic generation, because we have to characterize our crystal. We've run that. And this crystal, it is a type 2 crystal, so it's not that efficient. The nonlinear coefficient is not that high in KTP for type 2. And nevertheless, we understand what we see. So this is SAG power versus temperature. This is more or less an asymmetric, slightly asymmetric sync function. We are trying to do better with our spatial filtering and focusing in order to make it more symmetric. Then we have also scanned the pump power, we have also scanned the pump power and seen the effect of the SAG power. And as routine, it has a quadratic dependence. So we also did one interesting experiment, starting with inhomogeneous polarization. So when we talk about all these experiments, these are all with homogeneous polarization. It's with a Gaussian beam starting from laser, and we don't do much in that. But suppose in the path of the light, in the pump beam, if you have this two plate incorporated, it transfers, like it converts the homogeneous polarized Gaussian beam to an inhomogeneous polarized radial polarization beam. So the radial polarization looks something like this, and these arrows tell you the polarization along different radial direction. And as you can see that since it changes, the polarization, if you go around the radial direction, the polarization changes. So it is an inhomogeneous polarization that is spread across the wavefront. So this is so with such a pump beam, if you shine incident it on the KTP crystal, then we see its effect or its impact on the second harmonic light that is produced. Right? So this is because this is a type 2 phase match crystal. So for that, actually in the reverse direction for the signal and the idler, you need let's say H and V or Y and Z for signal and idler in order to give you a SAG at H, for example. Right? So this kind of a criteria will be fulfilled only when you have polarization that is diagonal, where you have equal components of H and V. But if it is a pure horizontal or a pure vertical photon, right, or pure vertical pump, right, then of course this SAG criteria, type 2 criteria is not fulfilled. So this is exactly what we see, because in the output you see these 4 lobe structure in the SAG signal. So there are intensity null in this cross-line position, which only shows that actually in these positions the polarization is either vertical or horizontal of the input beam, and it is not diagonal, so it does not satisfy the type 2 phase matching process. So this is a small, very, like a proof of principle experiment, a very fundamental thing, because we started testing our Q plate, and this is done by our student Om Shankar. And very recently, he's also tried to calculate, do his theory in order to explain our experimental results. We need more actually, but nevertheless, we understand this also from theory, and this is exactly the reason why it happens. So, so that was about SHG in this particular experiment. Now, in the forward direction, we also pumped it with a 400 nanometer and resulting in regenerate photons, which are emitted at 800. And again, this is a type 2 process. And first, initially, because it's not so efficient, this particular process, and it's a single pass PTKTP crystal, and we are also using very low pump powers. We first want to see it imaged with our MCCT camera. As a function of temperature, actually, we saw something very nice. So as a function, so there are two things here. So there is a half-wave plate here. So as a function of the half-wave plate, because this half-wave plate is important in, again, satisfying that particular type 2 criteria. So for SPDC, you need an H, let's say, for the pump, and in the output, you will have H and B for the signal and ideal photon. So this half-wave plate actually controls the input polarization. So when you have half-wave plate 0, which means it is H polarization, you see some photon being imaged on the UMCCT. When it is 45 degree, you see that means that the polarization has been turned to 90 degrees. So it is vertical polarization pump. Of course, you don't satisfy the type 2 criteria, and no photons are released in this, and you don't see any. So there is a general illumination on the UMCCT. So this is as a function of that, which shows that we are on track. And similarly, we also wanted to see, because this crystal is also temperature sensitive, so as a function of the temperature, the counts. So the phase matching temperature is somewhere a little less than 30 degrees centigrade. But when you keep on increasing the temperature, we see that the counts are decreasing. The photon counts are decreasing. So this panel shows an effect of varying the pump wavelength, because these are all phase matching criteria. So if you change even the pump wavelength, it has an impact on your photon beam. So the phase matching wavelength for the pump was around 400. So if you go lower than 400, the top panel, or if you go higher than 400, the effects are different. And the next slide will actually explain this. So yeah, as you can see, so this is, we try to record the normalized counts as a function of the pump wavelength. So this is actually the phase matching wavelength, somewhere here, 400.1 or 400.2 is your phase matching wavelength. And here actually the photons are supposed to be degenerate and they're supposed to be collinear. But beyond that, when you go beyond 400, so let's say 400.5 or 400.1, of course, this is not a perfectly phase match process, because our polling period does not satisfy a full conversion of it. Nevertheless, you see the photons, but something that is more interesting, these photons become non-collinear. So at this point, the generation is collinear, but in this regime, as you can see, so this is you're approaching, so this is 400, so you have that, and this particular video tells you that if you're approaching, if you're going higher up on the wavelength, this is like a ring. So it is like which I tried to explain in one of the introductory slides, that the photons are now emitted in a cone, and so you see this ring kind of a structure in the EMCCT. Similarly, as a function of temperature, you can see similar behavior, right? I mean, the counts of course decrease, and they depend a lot. If you go beyond the phase matching temperature, if you increase it, the counts get affected. So one more step beyond this is, since this is a type 2 process, we can separate with PDS, and we try to see the correlation. So this is also part of the characterization that we are doing. And we see that the photons, so let's say this is signal and this is either. So this is of vertical polarization, this is of horizontal polarization. And as a function of this half-wave plate, we see that these photons are also perfectly correlated. Because this is when we rotate the half-wave plate, the photon counts that we see in this direction and as we see in this direction, they are perfectly correlated, and they show that there is a decrease. So there is a sinusoidal kind of a behavior. So this is like a first step to show that these are polarization entangled photons. By the way, this experiment just shows that these are correlated. The photons, the signal and the island in these two arms are correlated not only in frequency but also in polarization. So yeah. Another project that was based on the telecom photons but in free space utilized these PPLN waveguides. So this was one of the first things that we started our group's activities with. And this is another type 2 PPLN. And again, it produces 1550 billion rate type 2, so orthogonally polarized photons in this process. So we have lots of quite a few work related to that. The experiments are also cranking up slowly. But some of these works actually we analyzed our waveguides pretty well. So we tried to, this was a multi-mode waveguide, and we tried to study several things. For example, the different spatial modes that are generated, that could be generated when you start with a fundamental pump beam, when you start with an antisymmetric pump beam like an HG10 or HG01 beam. And there are important things that one can have in this particular waveguide, and if you have more kind of structures that are fabricated, utilizing biperiod or cascaded polling and stuff like that. So I'm skipping some of these slides. So one interesting study that we do in when we want to characterize or study our waveguides or crystals is this joint spectral amplitude analysis. People might be knowing about this already, but it depends on two source functions. One is the pump envelope function, which depends on the pump properties, and it's basically an insinuation of the conservation of energy. There's also the phase matching function, which is an insinuation of the conservation of momentum. It basically depends on the delta theta or the delta k. Now, inside the waveguide, since the size is truncated on both x and y direction, we usually call it delta beta LMN. So these LMN actually tell you the pump, signal, and idler modes that contribute in a particular SPDC process. So compared to a free space crystal, in a bulk crystal, compared to that in a waveguide, these modes are pretty, like, they are discretized, right? So there are only certain eigenmodes that can propagate through the waveguide, right? So those modes, as a combination of different pump, signal, idler, we can call them as mode triplets that contribute to a particular SPDC process. So we characterize our waveguide also based on that. Now, depending on these two functions, the pump envelope and the phase matching functions, we can, as a product of that, we can write out the joint spectral amplitude of the biphotons, which are the signal and the idler. And we write it this way, and we also try to plot it and see. So there are different characteristics that we can see as a function of this JSA. So this is the joint spectral amplitude, particularly if it has this negative, if it is oriented with a negative angle, like for example, this is, let's say, minus almost 43-degree angle with respect to these two axes. So these two axes are the idler wavelength and the signal wavelength. Because it is joint spectral amplitude, we plot it as a function of the idler wavelength and signal wavelength. And this negative orientation tells you that this is so these photons are supposed to be highly correlated, and there's a probability that if you do something with them, they could be entangled. Like, of course, it depends on the experimental technique in which you want, like, to project it onto an entangled.
Yeah, sorry to interrupt. Can you please wind up within 3 minutes?
Okay, yeah. So so this is so we also explored the same, and then we did one interesting study. So instead of using a Gaussian pump beam, if you use an HG10 pump beam, right? In terms of that, then there are interesting spatial properties that come up as a result of that. So a spatial 10 pump beam can actually result in photons because of parity criteria, right? So it could be that the signal is in a fundamental mode, whereas the idler is in the antisymmetric mode, or vice versa, right? And let's say this is a non-degenerate process that we are looking at, right? And these two processes are, let's say, equally probable. Now, this is for a particular polling period, let's say λ1. Let's say suppose if your waveguide is biperiodically poled, which are commercially available solutions, or cascaded polling is also possible. So there is, on top of that, there is another polling which is lambda2, let's say a different polling. In this, again, your 1, 0 thing. So if this polling actually takes care of the fact that now your signal will be vertical and your idler will be horizontal. The first polling period takes care of the fact that the signal is horizontal and the idler is vertical. So again, in a similar fashion, because of parity criteria, these two processes are actually equally probable. So in total, that there are 4 processes that are more or less equally probable. So you can study and optimize your waveguides, particularly the width and height of the waveguide, the polling periods, the wavelengths in which this criteria is fulfilled, and you can have all these 4 processes going together. Right. So then in the phase matching function or the phase matching intensity, you see that there are 2 pairs of these processes. So these pairs of processes are these ones. And you can have the dimension of the waveguide and the pump properties in such a manner that these processes actually intersect at one common point. And let's say if the pump properties are also good enough and it intersects at the same point, then you can have a JSI, which is a joint spectral intensity from these 4 processes, but they are all overlapped. And the overlapped bandwidth actually looks something like this. So of course, they are not all perfectly overlapped, but there is a common overlap region in which we can define hyperentanglement of these photons. So when we found this was like very interesting. And this is hyperentanglement, means in more than one property, the photon pairs are entangled. They're entangled in polarization as well as in spatial properties. When the signal is fundamental, the idler is antisymmetric, and vice versa. So this is the spatial property, and polarization is the HB plus VH kind of property. So this is the hyperentangled state. So this is something that we studied, and yeah. So such kind of crystals, such kind of waveguides are also like there is a cascaded or bifield fabrication that is done, and one can have this fabricated and see if such a thing can be useful for hyperentanglement. So more studies from that, and there are also several other studies based on. So instead of post-selecting the photons, you can already have them after the waveguide. Right, so if you have these biperiod or multi-period polling in the waveguides, right? So you can have these entangled states already out of the waveguide. You don't have to post-select them through some coincidence detection or something like that. Right, so these are interesting in terms of teleportation experiments or different other quantum information and communication protocols. So we studied several of these structures, both in KTP as well as lithium niobate. And there are several, some of these studies have resulted in nice papers. I'm just flashing them. So more actually, we basically study in order to see the entanglement properties. Of course, we study the joint spectral intensity, and we also do the concurrence or the von Neumann entropy. We also see the overlap of the photon bandwidth for these processes. Because only within the common overlap bandwidth you can define entanglement or hyperentanglement. So this is one of the latest work in which we have shown that all different 4 belt states can be, so there is a structure like this in KTP which you can actually fabricate by masking or there are different techniques. So these are biperiod polling. So one distance is, one length is having a particular polling period, consecutive length is having a different polling period, and photons are generated throughout this entire process, but there are differences in these two, and this can result in a post-selection free entangled state, which is, let's say, the psi plus state. Then similarly, you can also have psi minus, phi plus, and phi minus. So these are all the 4 belt states. So these are some of the recent studies from the group. So all these have to do with SPDC, but as I also mentioned, we also work on 4-wave mixing. So we are also exploring silicon nano waveguides. And we have certain designs of silicon nano waveguides which we have worked on. Shivani, our student, is working on that, and in a collaboration with IIT Madras, we have also seen it experimentally like generated through our design and our structure. But the group of Professor Vijay Krishnadas helped us in fabricating these nano waveguides, and we have seen our classical four-wave mixing signal. And we are also in the process of experimenting more with these structures. So I'm not going into more in this. So these are details of that experiment where we have seen classical four-wave mixing signal centered around 1550, starting with the 1550 pump. Then another update is about the rubidium vapor experiment. So this is again a small experiment that we are building, and it has advanced quite a bit. I don't have all the results here, but nevertheless, we are actually exploring the duty line of rubidium. So we work at 780 also for this. We have a good laser in which we can see the Doppler Gordon spectroscopy. We have seen a saturated absorption spectroscopy, and we are in the process of setting up an EIT experiment in which so this is all at room temperature. We can also have higher temperatures. And although this problem is already studied, it is not a very new thing, but we want to do certain variants of that, and we're exploring that in the video. I don't think we have time to talk about this, so maybe I could stop here and go for more questions. But just maybe just one slide. So one application of these SPDC photons, and actually in the past I had also the opportunity to work with trapped ions, right? So this is the main motivation is to set up a quantum network kind of a scenario. A network consists of a node comprising of stationary qubits like atoms, and the channel, the quantum channel, could be satisfied by a flying qubit like photon, right? And this was from Kimball's idea. So with that particular motivation, actually we, in a nutshell, we had an experiment which looked like this. So this was in one lab where we had an SPDC source, but these photons were very particular to the ion which was in a different lab. It was an ion trap experiment in which a single ion of calcium was trapped, and we were interested in making the calcium ion interact with this with SPDC photons at 854 nanometers. So one partner photon from the source came and interacted with the calcium trap, whereas its other, which is the signal photon, passed through a set of filtering cavities, and they were detected by the APD. So let's say if you optically pump and have the calcium in a particular state, which is this D5 state, for example, and then of course, then a lot of things have to be controlled, because this ion trap experiment is again extremely challenging. There are lots of lasers which are driving it, cooling it, and also optically pumping and keeping it stable in the D5 manifold. So let's say once you have the calcium ion here in the D5 manifold, in a suitable case, the photons that are being transferred from the source side to the atom side, they are coming and they are tightly focused onto this calcium ion. And it could happen that the calcium absorbs such a photon, goes to the P3 state, and when it absorbs and goes to the P3 state, and after spontaneous emission lifetime, it might get re-excited, and that is when it will emit spontaneous fluorescence, right, at 393 and then 397, because this is also continuously cooled. The atom is continuously cooled. So these blue photons are then caught by the photomultiplier tube, and this is actually correlated with a click on the APD that catches the partner photon, and the partner to this photon that got absorbed by the ion. So these coincidences or correlations are what this experiment banked on, and we did several studies on these correlation measurements. So this particular experiment showed the ion photon interaction at the level of a single quanta. And later on, actually using the ion as so this was the first experiment, and later on using ion as a detector, we could, like a quantum detector, we also characterize the entanglement of these photons. Of course, we have to split it with a beam splitter instead of a polarizing beam splitter. And then on one arm, you have the polarization analyzers, and on the other arm, you have the ion, because the ion is sensitive to particular polarization when it is optically pumped in a particular way. And it can also exist in superposition state. So using ion as a quantum detector, we characterize and did a full polarization tomography and characterize the polarization entanglement of these photons. Right, I would, I think
Excuse me, ma'am.
Yeah.
Yeah. Yeah. Okay.
So questions?
Yeah.
Right,
So there are two questions. Yeah, there are questions.
Okay.
Are the signal and idler photons generated at the same time in picosecond time domain via vacuum fluctuations?
Sorry, 1 second. Once more.
Are the signal and idler photons generated at the same time in picosecond domain?
They are generated at the same time in a 0 time domain. But when we do in the experiments, there are certain resolutions that these time correlators come with. The best I know is 1 picosecond or let's say 4 picosecond from a particular company. And that defines actually your coincidence window in which you can do this, thing. And it also depends on actually the arm length in which the two photons are traveling. For example, if you split the photons and take it through different distances, by that also you can control. Because sometimes, yeah, depending on the resolution of your photon counter, it will be important to understand that.
Thank you.
Yeah, but they are supposed
Which
to be
types
coincident.
Yeah. Which types of resources used to constructed entangled state of quantum internet? I mean, photon source or NMR or superconducting qubit would be better, and why?
Superconducting qubits have actually done. So the question is about photon source as well as NMR. Sorry, what was it? Which is a better source
Which
for?
types of resources? Yeah, resources used to construct entangled state for quantum internet. Are they NMR or superconducting qubit? Which one is better? Like
So there are different. So for quantum computing, actually, the superconducting qubits have actually won the race. So there are different criteria. So for example, for quantum computing, there is this De-Vincenzo criteria. I mean, people must be knowing about it while researching in this. So there is the question of scalability. So all these systems like atoms and so they are not so scalable, right? I mean, ion traps, they're beautiful. Those are like perfectly. So if there is one, let's say one ion, like a natural ion, for example, calcium that I was talking about, right? So it has its exact replica in nature, which is another calcium ion, right? So this is the one property, but when it comes to scalability, maybe it's not that great. So there are different properties. So it's a little difficult to say which one is better in terms of that, but quantum internet, as if if you're talking about the quantum network scenario, right? You need actually you need a stationary qubit as well as a flying qubit. So I don't understand. You need both kinds actually. And quantum network must be at the heart of any quantum internet. So you need both kinds in that.
another one is like what kind of detectors are you using for the detection of 1550? What is the background noise count you are getting in the measurement?
Okay. So the 1550, actually we don't have SNSPT detectors. They would have been very good with low background noise and everything. We are using simple in-gas APGs, and there the detection efficiency is actually pretty low. It is 10 to 15%. Only 10% quantum efficiency actually gives us good results, because there is also, so when you go higher up on the quantum efficiency, it somehow also At least these detectors are somehow also related to the dead time. So the dead time of the detectors tells you how many maximum counts are possible. So if you are low on the dead time, your detector can get in more and more counts. If the detector has a higher dead time, then of course you're saturating, so it's not being able to detect so many photons, right? So there is always balancing and take care of that. But the background, so the dark count, if you that's what you mean. The background count is so you have, so after you tackle everything on the experiment, you have a dark room and you tackle everything else, all kinds of other noises. So you try to cover your detector and everything. So then still you have some dark counts which are 100 or 200 counts, something like that. So that is something that you cannot beat. So 100 counts is like a minimum. These are not great detectors, but nevertheless, they are very portable and easy to work with. And you can always back calculate and talk about the generated photon pairs.
Last one is, what is the motivation of SHG of the radially polarized vector beam?
Motivation for SHG for the radially polarized. Yeah, we just know that was just like a nice experiment to test two things, because we wanted to of course test SHG and see how our crystal was working. This is also we have to see if everything is working, the phase matching temperature that the company talks about, and there are different crystal orientation, alignment, all of that. So we test our crystal with that. But we are also like a new group working on orbital angular momentum, so we don't have a lot of experience there. And this Q-plate was a new tool for us, and we wanted to understand how it affects it. So that was the motivation to understand, if you just insert the Q-plate, how your beam would get affected and what impact would it have on the SHG.
So there are no further questions. Let's thank the speaker once again. Thank you, Professor Ghosh.
Thank you.
So moving towards the last talk of the session, which is a student talk by Muthumani Maran. He is currently doing his PhD at IIT Bombay. He will delivering his talk on a near deterministic weak value metrology via collective non-linearity. I would like to invite Muthumani Maran to deliver his talk.
Yeah, good evening. Can you see my slides?
Yes.
Yeah, okay. And I'm audible, right? Okay, thank you.
Yes.
So yeah, thank you, student chapter PRL, for giving me a chance to deliver this talk here today at the student conference on optics and photonics at PRL. So my talk is, the title of the talk is Parameter Estimation via Collective Interactions, and my name is Muthumani Maran. I'm a third year PhD student right now at IIT Bombay. I'm working with Professor Sai Vijanapati here at IIT Bombay. So the overview of the talk is, it's a theory paper. I'm just giving you a heads up. Okay, the overview of the talk, I'm going to talk about a specific metrological protocol called weak value amplification technique. So in this technique, what we actually do is we take unknown parameter a small parameter called G, and we amplify it and measure it, right? So typically it consists of two parts. One is called a system and another one is called a meter. And the system, usually the system and the meter are initialized with, in some state, pure state, and they are evolved according to this evolution operator given by U, which contains the information about the small parameter that we are trying to measure, which is G. So after the evolution, then we post-measure the system alone with some post-measurement state psi of F, so that we can define something called post-measurement probability, which is the probability that this post-measurement succeeds. Okay, so if the post-measurement succeeds, then what you actually see is at the meter state evolves with the effective Hamiltonian given by this effective coupling GAW, and this AW is called the amplification factor. Suppose your value, the unknown parameter value that you're trying to measure is of order 10 power minus 12, then if you don't have any apparatus that can actually measure 10 power minus 12, what you can do is you can do this weak value amplification technique, and if you can able to amplify this value 10 power 2 times, 100 times at least, and you have a measurement apparatus of 10 power minus 10, then you can actually measure this value. That's the technique here. And the weak value here is defined in equation 1. As you can see that this weak value and the post-selection probabilities are inversely related. The weak value is actually inversely related to the square root of the post-selection probability. So as you try to amplify this value, the post-selection probability decreases, right? So if the post-selection probability decreases, there is a very less success that you actually measure this. You actually get success in obtaining this post-measurement state, right, at the end. So previously, there has been several techniques to improve the trade-off between these two quantities. Earlier, let's say that you're trying to amplify this in an experiment, that you're trying to amplify this weak value using a number of qubits. And here the small n indicates the number of qubits here. Let's say that you're trying to amplify this weak value as you increase the number of qubits, but then the post-selection probability actually decreases exponentially, really badly, as you increase the number of qubits. So in 2014, there is these two people called Pang and Brun came up with an idea that why not use entanglement as a resource to improve this trade-off between these two quantities. So the blue shaded figure, as you can see, the Pang and Brun suggested that if you fix weak value using entangled ancillas, entangled resources, qubits, resources, Pang and Brun showed that if you fix weak value to be some constant, they actually showed that the post-selection probability increases quadratically as you increase the number of qubits. And but you cannot further improve weak value amplification in this problem. Weak value in this problem. So Pang and Brun suggested another protocol in which if you make the post-selection probability to grow linear in in the number of qubits, then the maximum you can get is a weak value that grows sublinear in n. It actually grows as square root of n. So you cannot, you have to either give up your post-selection probability or weak value so that you can show enhancement in the other quantity. That's this is where that our result we investigated and whether we try to better off this trade, to enhance this trade-off further. So the yellow shaded one is our result, where we actually, by introducing nonlinearity in this problem, we actually showed that by fixing weak value to grow linearly in n, we actually showed that the post-selection probability will also grow quadratic in n as you increase the number of qubits. We actually showed simultaneous enhancement in both quantities. Okay, so this is the overview, and let me go to the talk right away. So the weak value amplification technique, typically it consists of two parts, as I said before. We usually consider a bipartite Hamiltonian of this form in equation 2, where A is called a system and B is called a meter, and G is the small parameter that you're trying to measure. Then the protocol is as follows. You prepare the system and meter in some initial state, which is phi I and psi I and phi, and you evolve the system according to the Hamiltonian given in equation 2. So after a short time, what you do is you post measurement onto some final state, which is nearly orthogonal to the initial state. Why nearly orthogonal? I will explain that in the next slide. But the point is, you will at the point of post selection, what the meter actually experiences, the effective coupling GAW, evolution with effective coupling GAW, right? And with weak value defined in equation 5, and there is a trade-off between these two quantities, as I mentioned before, right? So let me show you how you can actually improve, amplify this weak value using the number, using qubits and all. Suppose if you consider, in equation 5, I just want to say that this weak value depends on three quantities majorly. One is the choice of initial state that you're choosing, and the what kind of Hamiltonian, which is A, what you're choosing, and the final state, right? So if you consider, let us consider the following example. If you consider as your system Hamiltonian to be sigma x, and the initial state and final states of this form, with theta being very small, you can actually show that the weak value grows as 1 over theta. Suppose your theta is of order 10 power minus 2, you can actually show 100 times amplification in the weak value. You can actually amplify this value 100 times, right? So suppose your weak value is, suppose the small parameter that you're trying to measure is actually of order 10 power minus 12. And by doing this process, you can actually amplify it to 10 power minus 10. which is 100 times better. But the post-selection probability decreases first. Earlier it was 10 power minus 15, but at the point of post-selection, it further decreases, which is something not desirable, right? Can we amplify this value further? Yeah, there is a way. All you have to do is increase the number of qubits in the system. If you increase the number of qubits, then what you have is the the enhancement by adding more qubits in the system. So so the weak value is also increased linearly as you increase the number of qubits here. So by fixing weak value, as your weak value grows linearly as you increase the number of qubits, your post-selection probability actually decreases exponentially as you increase the number of qubits. So this is something really bad. So this is where Pang and Brun in 2014 came up with this idea. Why not choose entangled resources, entangled ancillas as a resource for enhancing this trade-off between these two quantities. So they consider an entangled ancilla described in equation 9, and they and the maximum and the minimum eigenvalues are proportional to n and minus n. J is actually proportional to n and minus n here. I will explain the notation when I come to the work. So I'm using this J notation here because when I'm going to my work, I have actually introduced a Dickey Hamiltonian where this J notation is pretty common. That's why I also use J and minus J here. And the J and the minus, the J is actually equal to n over 2 actually here. And the minimum eigenvectors are all spins pointing down, and the maximum eigenvectors are all spins pointing up. So Pang and Brun suggested two procedures. In the first one, what they suggested was you first fix the weak value. Remember, there are two quantities here. One is the weak value, and another one is the post-selection probability. So Pang and Brun in the first procedure suggested that you first fix the weak value. Once you fix the weak value, you find the final state with some procedure, and once you know the final state, you can actually find the optimal probability. So the calculation leads to equation 11, which says that the maximum of post-selection probability is actually related to the variance of the system Hamiltonian with respect to the initial state. And we in the first procedure, it is assumed that the weak value is held constant. So all you have to do is maximize this variance so that you will get a maximum probability. So the first trick they used was using, they used this, since the choice of Hamiltonian is already fixed, they used entangled ancillas as the resource. So they chose known state as the initial state to maximize this variance of this quantity, because the known state shows a very greater advantage when it comes to quantum metrology in phase, protocols when it comes to phase estimation problems, that it can achieve Heisenberg scaling. So using known state as an initial state, they showed that the maximum of variance grows as n square. So since maximum of variance grows as n square, your post-selection probability also grows, proportional to n square, which is what graphically depicted here. In the first procedure, if you fix weak value to be some constant, your post-selection probability increases quadratically as you increase the number of qubits. The problem here is you are actually you cannot enhance your weak value further because you are actually this is the trade-off still exists here. You have to either give up your post-selection probability or weak value here so that you can see an enhancement in the other quantity. That's why this is a drawback with this procedure. So Pang and Brun suggested another procedure in which they want us to fix the probability first and fix the final state and find the optimal weak value. So by doing this, once again, what they found was the maximum of weak value, which turns out to be, related to the variance of wave with respect to the initial state, which is given in equation 17. So once again, choosing the same choice of Hamiltonian, same initial state, this variance grows as n square. By fixing the post-selection probability to grow linear in n, they showed that the maximum weak value grows sublinear in n, right? They actually given up, the post-selection probability so that they show some growth in the weak value here, right? So there is no simultaneous enhancement here. It's still AW is sublinear in n. there is no enhancement. I would say there is no advantage here, because even in the unentangled strategy itself, we already seen that the weak value grows linearly in the end, right? So there is no advantage here also. So this is what leads us to examine whether we are able to have a better trade-off compared to the previous, existing protocols. Can we able to improve this trade-off further? So this is what lead us to introduce nonlinearity in our problem. So small digression here, we introduced a system called decay system, which is nothing but a collection of atoms inside a cavity. So what happens is, due to multipartite entanglement, all these atoms goes to the ground state, simultaneously, so that the amount of creates a collective, shows a collective behavior, and this collective behavior shows a very greater advantage when it comes to quantum metrology. So this leads us to introduce a new Hamiltonian called a single squeezing Hamiltonian, which is written in the first line, which is written on the first line, where single squeezing Hamiltonian is a nonlinear Hamiltonian. So when it comes to quantum metrology, nonlinear Hamiltonians also shows very greater advantages in phase estimation problems, such as it can even beat Heisenberg scaling. So we proposed a Hamiltonian of this form, and the maximum and the minimum eigenvectors are defined on the second line. So the maximum eigenvector is equal number of upspins and equal number of downspins, and the minimum eigenvectors are all spins pointing down. And once again, I repeat that the maximum of post-selection probability and the maximum of peak value depends on the variance of A with respect to the initial state, right? So by choosing this Hamiltonian and the same initial state as before, which is the superposition of all spins up, maximum and the minimum eigenvalues, we showed that this variance scales as quartic N, which is n power 4. So by fixing the weak value to grow linear in n, we show that the maximum probability can be scaled to n square, which is simultaneous enhancement in both these quantities, right? Earlier it was you have to either give up one quantity so that you can show enhancement in the other quantity. But in our protocol, we showed that in our procedure, we showed that we can actually improve these quantities simultaneously. And also, we also showed that by choosing a protocol in which a post-selection probability is nearly deterministic, we also obtain a nonlinear scaling, which is a quadratic scaling in a weak value. So you will almost get successful post measurement. Simultaneously, you will also have n square enhancement. Suppose if you have 10 atoms, 10 qubits in your experiment trying to amplify this value, you will actually get 100 times an amplification in your, you will actually get at the point of post measurement, you actually get 100 times amplification. And the equation 20 and equation 20 are the final states that you have to post-select onto, so that you have to see the scaling. And once again, I'm graphically, this is graphically, graphically drawn here, which is as you increase the number of qubits, the weak value grows linear in n. The post-selection probability grows quadratic in n, which is a simultaneous enhancement in these both quantities. And finally, conclusions. So earlier there was a problem that as you increase the number of qubits, your post-selection probability becomes really bad. So this people, Pang and Brun, came up with an idea that if you give up one quantity, if you fix one quantity, then the other quantity can be scaled. It can be enhanced, but there is no simultaneous enhancement, and your probability can never reach nearly deterministic. So we introduced a nonlinearity and the decay physics, which shows collective enhancement to show that we can actually show simultaneous enhancement in this weak value as well as post-selection probability. And also in the second case, we showed that by choosing a nearly deterministic protocol, we obtained a weak value that grows quadratic in it. Yeah, and this is you can find this results in our paper, which is in archive. Comment below. Yeah. Thank you.
Yeah, thank you very much for the nice talk, Muthumani madam. Yeah, there is one question. Can you comment on the experimental realization of your measurement technique?
Experimental realization on the measurement technique. Okay, how can we experimentally measure this, right? So how do you measure weak value? So in our problem, we proposed a way to realize this Hamiltonian, actually, this nonlinear Hamiltonian that I showed, by having a cavity QED in a cavity QED setup in which it experiences a Bloch-Shiger like shift, so that this magnetic field that it produces actually displaces the energy levels in the atoms. So this displacement in the energy levels can be realized as weak values actually in our experiment. That's a short answer.
Okay. Are there any further questions? Okay. So if not, let's thank the speaker and thank you. And this brings us to the end of this second session as well as the second day of the scope. Hope you have enjoyed the day, and we will meet tomorrow at 9:30. Yeah, thank you for joining. भाई कैसे